Hello and welcome back. If you're here, maybe you had a long day. Maybe your mind is still spinning with thoughts, tasks, plans, or maybe you're simply drawn to the quiet wonder of the cosmos, that feeling of smallness that somehow makes everything else feel manageable. Whatever brought you here tonight, I'm glad you're listening. Tonight we're going to explore something both familiar and strange, the Milky Way, our home galaxy, that pale river of light you might have seen on a dark night, far from city lights. For the next little while, we'll drift through facts about this cosmic structure we're embedded in, this island universe of hundreds of billions of stars, one of which you're orbiting right now. Before we begin, if you enjoy these journeys through science and space, consider leaving a like. It helps others find their way here. And if you'd like to join us again, subscribe. There are endless topics to explore, endless questions to contemplate as you drift off to sleep. Comments are welcome too, though there's no pressure. This is a space for rest, not demands. Now let's begin. Let's talk about home, the Milky Way. It's a curious name when you think about it. Not the Star River, not the celestial path. Milk. The name comes from the Latin Via Lactea, which the Romans borrowed from the ancient Greeks, who saw this band of light across the sky and called it Galaxias Kyklos, the Milky Circle. The Greeks told a story about it. They said the goddess Hera was nursing the infant Heracles, but when she discovered he wasn't her child, she pulled away suddenly. Milk spilled across the heavens, creating this glowing band of stars. It's a strangely intimate origin story for something so vast. A divine accident, a moment of surprise immortalized in light. But the Greeks weren't alone in their interpretation. Other cultures saw different things entirely. Some saw a river, a path for souls traveling to the afterlife. Others saw a crack in the dome of the sky, through which the light of heaven leaked through. The Norse imagined it as a bridge. The Chinese saw a silver river separating lovers, crossed only once a year. In a sense, every culture that looked up at night found their own story written in those stars. What's beautiful about this is that none of them knew what they were really looking at. They saw something mysterious, something that demanded explanation, and they created myths to hold the mystery. The truth that we're looking at the combined light of hundreds of billions of distant suns that were inside this structure looking out, wouldn't be discovered for thousands of years. But perhaps the myths weren't entirely wrong. Perhaps there's something worth preserving in the idea that the Milky Way is, in a sense, the spilled milk of creation, the accidental beauty of the universe made visible on a dark night. And maybe that's enough for now. Just the name and the ancient eyes that looked up and wondered. Here's something that's difficult to hold in your mind. The Milky Way contains somewhere between 100 and 400 billion stars. That's not a small margin of error. We're uncertain by hundreds of billions. But even the lower estimate is almost incomprehensible. Let me try an analogy, though it won't quite capture it. Imagine every grain of sand on every beach on Earth, all the tiny particles in all the world's ocean's edges, from tropical shores to Arctic coastlines. That's roughly how many stars we're talking about. One star for each grain of sand. And most of those stars you'll never see. Most of them are too distant, too dim, or hidden behind vast clouds of cosmic dust. When you look up at the night sky from a dark location, You might see a few thousand stars if conditions are perfect. That sounds like a lot, and it is, in its own way. But it's such a tiny fraction of what's actually there. You're seeing perhaps 0.003% of the galaxy's stars. The rest exist in darkness beyond your perception, burning and dying, and being born in regions of space your eyes will never reach. There's something oddly comforting about this limitation, isn't there? The universe doesn't require that you see it all. It's content to be mostly hidden, mostly unknown. You're allowed to look up, see a handful of lights, and call that enough. The other 100 billion stars will continue without your gaze, indifferent to whether you know they're there. And perhaps that's the point. Scale this large isn't meant to be grasped all at once. It's meant to be appreciated in pieces, in moments, like right now, as you lie here considering the simple fact that most of the galaxy is invisible to you and always will be. The Milky Way is old. Not as old as the universe itself, that's about 13.8 billion years, but close. Our galaxy formed approximately 13.6 billion years ago, just 200 million years after the Big Bang. In cosmic terms, that's almost immediately. The universe was still young, still hot, still figuring out how to make structure out of primordial gas. Try to imagine that span of time. 13.6 billion years. The Earth is only 4.5 billion years old, roughly a third the age of the galaxy. Modern humans have existed for perhaps 300,000 years. Civilization, maybe 10,000 years. Your entire life, every moment you've experienced, every human who's ever lived, all of it fits into the tiniest sliver at the very end of a timeline that stretches back more than 13 billion years. The Milky Way has been spinning through space for nearly the entire history of the cosmos. It's been here through epochs we can barely name. It watched the first stars form and die. It witnessed the creation of the elements that would eventually become planets, oceans, people. It was here before Earth existed, before the sun existed, before anything in our solar system was even a possibility. And it's been changing the whole time. The Milky Way you see tonight, or would see if you could see the whole thing, is not the same galaxy that formed all those billions of years ago. It's grown through mergers with smaller galaxies. It's formed new stars and lost old ones to death. Its spiral arms have wound and unwound. The galaxy is more like a river than a monument, always the same entity, but never the same configuration. In a sense, the Milky Way is a cosmic elder. It's seen almost everything the universe has had to offer, and we're living inside it, inhabitants of an ancient structure, our entire existence a brief flicker in its long, long story. The Milky Way measures about 100,000 light years from edge to edge. That means if you could somehow travel at the speed of light, about 186,000 miles per second, faster than anything with mass can actually move, it would take you 100,000 years to cross from one side of the galaxy to the other. Let's sit with that for a moment. Light doesn't wait. It doesn't slow down. It's the universe's speed limit, the fastest thing there is. And even at that incomprehensible velocity, crossing our galaxy would take longer than all of recorded human history. Longer than humans have been humans. Longer than most species survive. Here's another way to think about it. When you look at a star on the opposite side of the Milky Way, if you could somehow pick one out from the crowd, you're not seeing it as it is now. You're seeing it as it was 100,000 years ago, when our ancestors were still figuring out how to make complex tools, when the Earth was in an ice age, when the world was fundamentally different from the one you're lying in right now. That star's light has been traveling toward you all this time, crossing the vast emptiness between there and here, and it's just now arriving at your eye, or would be if your eye could detect it individually. The star itself might have changed dramatically in the interim. It might have expanded into a red giant, or exploded into a supernova, or collapsed into a white dwarf. You wouldn't know. You're still seeing its ancient light, a postcard from the past that took 100,000 years to arrive. Distance in space is also distance in time. The farther you look, the further back you see. The Milky Way isn't just a structure in space, it's a structure in time, each region showing you a different moment from the past, a cosmic album of photographs arranged by distance instead of date. And all of this is just one galaxy, just our home. There are billions more, most much farther away than 100,000 light years. But for now, this scale is enough to contemplate, just the width of the Milky Way, and the strange truth that space and time are tangled together in ways that make now a complicated concept. If you could leave the Milky Way, truly leave it, travel thousands of light years above or below the galactic disk, and look back, you'd see something magnificent. A flat spiral, like a cosmic pinwheel, with graceful arms curving out from a bright central bulge. It would look, perhaps, like a hurricane seen from space, or a whirlpool frozen in stars instead of water. But we can't do that. We're inside it. We're embedded in the disk, about halfway out from the center, surrounded by stars and gas and dust. Trying to understand the shape of the Milky Way from our position is like trying to understand the shape of a forest while standing among the trees. You see trunks, branches, leaves, but the overall structure, the pattern of it all, that's hidden by your immersion in it. For most of human history, we didn't know the galaxy was spiral-shaped. We didn't even know we were inside a galaxy at all. That realization came slowly, over centuries, as we developed better telescopes and mathematical tools, and eventually the ability to observe in wavelengths beyond visible light. The spiral structure wasn't really confirmed until the 1950s, when radio astronomers found ways to peer through the obscuring dust that blocks our optical view. It's a humbling thing, isn't it? We live inside this vast, beautiful structure, and for thousands of years we had no idea what it looked like. We were like characters in a novel, unaware they were in a story, unable to see the narrative structure that contained them. Only recently, cosmically speaking, did we gain enough perspective to glimpse the larger picture. And even now, our view is incomplete. We can infer the spiral shape, map it with radio waves and infrared light, build models from what we observe. But we can't step outside for a clean look. We're forever inside, forever piecing together the whole from fragments and angles and indirect measurements. Perhaps that's as it should be. Perhaps the universe prefers to be understood slowly, patiently, through effort rather than given as a gift. We live in the suburbs of the galaxy. That's really the best way to put it. The solar system is located about 26,000 light years from the galactic center, roughly halfway between the center and the outer edge. We're not in the crowded downtown, where stars are packed close together and the supermassive black hole holds court. But we're not in the sparse outskirts either. We're in what you might call a comfortable middle distance, in a smaller spiral arm called the Orion Spur, nestled between two major spiral arms. This location matters more than you might think. If we lived closer to the galactic center, things would be different, more dangerous, perhaps. The star density there is much higher, which means gravitational interactions would be more common. Close encounters with other stars could disrupt the orbits of planets, including Earth. Radiation levels would be higher. Supernovae would occur more frequently nearby, bathing the solar system in high-energy particles that could strip away atmospheres and harm life. Out here in the galactic suburbs, things are quieter, more stable. The nearest star is over 4 light-years away, close in galactic terms, but far enough that it poses no threat. Supernovae happen, but usually at safe distances. We orbit the galaxy in relative peace, experiencing the cosmos at a gentler pace than the stars closer to the center. There's something appealing about this, isn't there? The idea that we're not at the center of things, not in the most dramatic or extreme location, but in a kind of cosmic neighborhood. A place that's interesting without being overwhelming, eventful without being chaotic. Perhaps this moderation is one reason life emerged here at all. Enough stability for evolution to work over billions of years. Enough resources to build a system of planets, but not so much chaos that it all falls apart. We're halfway out in the suburbs on a spiral arm named for a constellation. It's a specific address in a galaxy of hundreds of billions of possible locations. And maybe that specificity, that particularity, is part of what makes it home. The Milky Way weighs approximately 1.5 trillion times the mass of our Sun. That's a number so large it stops meaning much in the usual sense. A trillion is already difficult to conceptualize. A million millions, a 1 followed by 12 zeros. Multiply that by 1.5, and you're talking about mass on a scale that dwarfs anything in everyday experience. But here's the strange part. Most of that mass isn't in the stars you can see. It's not in the gas clouds or the planets or the dust. Most of it, perhaps 90%, is something called dark matter, and we don't really know what dark matter is. We've never directly detected it. It doesn't emit light. It doesn't absorb light. It doesn't reflect light. By every measure we have for detecting normal matter, dark matter is invisible. So how do we know it's there? Through its gravity. When astronomers measure how fast stars orbit the galactic center, they find something odd. The outer stars move faster than they should if only visible matter was present. In fact, they move so fast that without additional mass, they should fly off into intergalactic space. The galaxy shouldn't hold together, but it does. Something invisible is providing the extra gravity needed to keep everything in place. We call that something dark matter. It's a placeholder name, really, a description of our ignorance rather than our understanding. It's dark because we can't see it. It's matter because it has mass and exerts gravity. Beyond that, we're uncertain. It could be exotic particles that don't interact with light. It could be something else entirely, something we haven't even imagined yet. What's remarkable is that this invisible substance outweighs everything we can see by a factor of 9 to 1. The stars, the gas, the planets, all of it is just the visible tip of a much larger, invisible structure. The Milky Way is like an iceberg. What we see is a small fraction of what's actually there. The rest remains hidden, holding the galaxy together from the shadows. An invisible scaffold supporting the visible cosmos. And we live inside this mystery, orbiting a galactic center through an invisible ocean we can only detect by its effects. It's enough to make you wonder what else might be there, invisible but real, shaping the universe in ways we're only beginning to understand. The Milky Way is vast, hundreds of billions of stars, 1 trillion times the sun's mass, 100,000 light-years across. It's almost too large to comprehend. And yet, in the cosmic census, it's just one galaxy among approximately 2 trillion in the observable universe. 2 trillion. That's 2,000 galaxies, each one a vast collection of stars and gas and dark matter. Some are larger than the Milky Way. Many are smaller. Some are spirals like ours. Some are ellipticals. Some are irregular clouds of stars without clear structure. But each one is a galaxy, a gravitationally bound system, an island universe separated from its neighbors by vast expanses of mostly empty space. If you were to count one galaxy per second, it would take you about 63,000 years to count them all. If each galaxy were a grain of sand, they would fill thousands of Olympic swimming pools. These comparisons fail, of course. They always do at this scale. But maybe they help frame the enormity of it. The Milky Way is a single grain of sand on an endless beach of island universes. And here's the strange thing. The farther out we look, the more galaxies we find. We used to think the Milky Way was special, perhaps unique. Then we thought it was one among millions. Now we know it's one among trillions. And that number might increase as our telescopes improve. The universe keeps expanding in our understanding, revealing more structure, more galaxies, more everything. Yet despite this vastness, or perhaps because of it, the Milky Way still matters. It's home. It's where you are. Every human who's ever lived has lived here, in this galaxy, orbiting this star, on this planet. All of our stories, all of our history, all of our dreams and fears and hopes, they've unfolded here, in this one galaxy out of 2 trillion. In a sense, the Milky Way's cosmic ordinariness makes it more precious, not less. It's not special in the universe's eyes, but it's special to us. It's the context for everything we are. And maybe that's enough. Maybe being one among trillions doesn't diminish the importance of being home. If you could shrink the Milky Way down to the size of a pancake, say 6 inches across, the disk would be thinner than a sheet of paper, perhaps as thin as a playing card. It's a vast structure, 100,000 light-years wide, but remarkably flat for something so large. This thinness is the result of billions of years of rotation and gravitational sorting. When the galaxy first formed from a collapsing cloud of gas, it was roughly spherical, but as it spun, conservation of angular momentum caused it to flatten, the way pizza dough flattens when you spin it in the air. Material that wasn't moving with the general rotation fell toward the center, or was flung outward. What remained settled into a disk. The stars in the disk orbit the galactic center in roughly the same plane, like cars on a flat highway. There's some vertical motion. Stars do bob up and down through the disk as they orbit, but it's minor compared to their horizontal motion. The overall effect is a remarkably two-dimensional structure in a three-dimensional universe. But the Milky Way isn't just a disk. There's also the central bulge, a spherical collection of older stars around the galactic center, and the halo, a roughly spherical distribution of old stars and globular clusters, extending far beyond the visible disk. So the galaxy is really a combination of structures, a flat disk embedded in a diffuse sphere. Still, when we talk about the Milky Way, we usually mean the disk. That's where most of the stars are, where most of the action happens, where we live. And that disk, despite being 100,000 light years across, is only about 1,000 light years thick, a ratio of 100 to 1. Thinner, relatively speaking, than paper. There's something aesthetically pleasing about this, isn't there? The idea that such a massive structure could be so flat. It's elegant in its own way, not the chunky three-dimensionality you might expect, but something more refined, more geometric. A cosmic disk spinning through the void, thin and vast and ancient, with us embedded somewhere in its middle, orbiting in the general flow of billions of other stars. Here's a way to think about the Milky Way's stellar population that might help the number land. There are more stars in the galaxy than there have been seconds in the entire history of human civilization. Let's do the math loosely. Modern humans have existed for perhaps 300,000 years. Civilization, cities, agriculture, writing, maybe 10,000 years. Even if we're generous and say 300,000 years, that's roughly 9.5 trillion seconds. The Milky Way has between 100 and 400 billion stars. So we're not quite to more stars than seconds of human existence, but we're in the same ballpark. And if we're talking about recorded history, maybe 5,000 years, then yes, there are definitely more stars than seconds. The point isn't the exact numbers. The point is the scale. Every second that has passed since the first humans walked upright, every heartbeat, every breath, every moment, all of that time still doesn't add up to as many units as there are stars in our galaxy. Each star is like a second in deep time, a discrete unit in a vast collection that stretches beyond easy comprehension. And each of those stars is potentially a sun to unknown worlds. Most stars probably have planets. We've learned that much from recent discoveries. Some of those planets might be rocky, temperate, orbiting at the right distance for liquid water. Some might even have life, though we don't know. We haven't found it yet. But the sheer number of possibilities is staggering. Hundreds of billions of stars, perhaps trillions of planets, and we've examined closely only a handful. Most of those stars orbit in darkness we'll never penetrate. They're too far away, too faint, lost in the crowd. We might catalog them someday. Automated surveys are already counting billions, but we'll never know them individually. They'll remain statistics, points in a database, their stories untold. And perhaps that's okay. Perhaps the universe doesn't require that we know everything. Its content to be mostly unknown, mostly mysterious. We're allowed to appreciate it from a distance, to marvel at the numbers, to contemplate the scale without needing to examine every detail. The Milky Way holds more stars than seconds in human history, and most of them will remain forever beyond our reach. That's not a failure. That's just the nature of living in something so vast. The Milky Way rotates, but not the way a solid object rotates. If you spin a coin on a table, every part of the coin turns at the same rate. The edge and the center complete one rotation in the same amount of time. That's solid body rotation, but the Milky Way doesn't work that way. It rotates differentially, meaning the inner parts spin faster than the outer parts. This might seem strange at first, but it makes sense when you think about gravity. Stars closer to the galactic center experience stronger gravitational pull from all the mass concentrated there, so they orbit faster. Stars farther out experience weaker pull and orbit more slowly. It's the same principle that governs the planets in our solar system. Mercury whips around the Sun in just 88 days, while Neptune takes 165 years. This differential rotation has profound effects on the galaxy's structure. It's what creates and maintains the spiral arms, those graceful curves you'd see if you could view the Milky Way from above. The spiral arms aren't made of the same stars rotating together like spokes on a wheel. Instead, they're density waves, regions where stars temporarily bunch up as they move through, like a traffic jam on a highway where the cars change but the jam persists. Imagine stirring cream into coffee. At first you get distinct spirals, but if you stir continuously, those spirals wind tighter and tighter until they disappear into a uniform blur. The Milky Way's spiral arms should do the same thing. They should wind up and vanish after a few rotations. But they don't, because they're not material arms. They're pressure waves, patterns that persist even as individual stars flow through them. This means the spiral arm you're in right now, the Orion Spur, isn't a permanent structure following you around the galaxy. It's more like a wave you're passing through. Eventually, the Sun will exit this arm and drift through the space between arms, then enter another arm millions of years later. The arms themselves will remain, but they'll be made of different stars. It's a bit like a wave on the ocean. The wave travels across the water, but the water itself mostly moves up and down. The form persists while the substance changes. That's the Milky Way's spiral structure, a persistent pattern created by differential rotation, beautiful and ephemeral at the same time. Our solar system takes approximately 225 million years to complete one full orbit around the galactic center. Astronomers sometimes call this a cosmic year, one full trip around the Milky Way, our galactic birthday, if you will. Think about what that means. In the 4.5 billion years since the solar system formed, Earth has completed only about 20 orbits around the galaxy. 20 cosmic years, that's all. When the Sun and planets first coalesced from a collapsing cloud of gas and dust, the Milky Way was in a different orientation. The stars that were our neighbors then are scattered elsewhere now. We've drifted through different spiral arms, past different stellar neighborhoods, witnessed the galaxy from 20 different positions along our long, slow path. During the last cosmic year, the most recent 225 million years, life on Earth went from the early dinosaurs to today. The supercontinent Pangaea broke apart, the Atlantic Ocean opened, mountains rose and eroded, species emerged, flourished, and went extinct. All of human history, from the first stone tools to space telescopes, happened in just the last millionth of a cosmic year, a cosmic eye blink. And we're moving fast, by everyday standards, about 514,000 miles per hour as we orbit the galactic center. That's fast enough to cross the United States in about 5 seconds, fast enough to reach the moon in about half an hour. Yet even at this tremendous speed, it takes 225 million years to complete the circuit. The galaxy is simply that large. What's interesting is that we don't feel any of this motion. You might feel the Earth rotating beneath you if you're on a playground carousel, or feel the car moving as you drive. But the solar system's orbit around the galaxy? Nothing. We're in free fall, following the curvature of space-time carved by the galaxy's mass. There's no acceleration we can detect, no cosmic wind in our face. We're simply being carried along, participants in a vast orbital dance we can only detect through careful measurement. In another 225 million years, Earth will return to approximately this same point in the galaxy. Though everything else will have changed, New stars will have formed, old ones will have died, the spiral arms will have shifted, and humanity, if it still exists, will have experienced whatever changes 225 million years bring. It's a time scale beyond imagining, yet it's just one tick of the galactic clock, one orbit among the roughly 60 the solar system will complete before the sun dies. Right now, as you lie there listening to this, you're traveling through space at about 514,000 miles per hour. That's the speed of the solar system as it orbits the galactic center. Over 500,000 miles per hour, hurtling through the cosmos like a bullet, though a bullet on a very long, curved trajectory. To put that in perspective, it's about 700 times the speed of sound, fast enough to circumnavigate the Earth in less than 3 minutes, fast enough to reach the Moon in about half an hour, or Mars in a few days when it's at its closest. It's a speed that would vaporize any physical object trying to move through Earth's atmosphere, a velocity that exists only in space, where there's no air resistance to slow you down or burn you up. And yet you feel absolutely nothing. No wind, no acceleration, no sense of motion at all. That's because you're in what's called an inertial reference frame. You're moving at constant velocity through space, and without something external to compare against, there's no way to detect the motion. It's like being in an airplane at cruising altitude. Once you reach constant speed, you can't feel that you're moving at 500 miles per hour. You could pour a drink, and it would pour normally. The same is true on a much grander scale with the solar system's galactic orbit. But we're not just orbiting the galactic center. We're also moving in other ways. The Earth rotates on its axis at about 1,000 miles per hour at the equator. It orbits the Sun at about 67,000 miles per hour. The Sun orbits the galaxy at 514,000 miles per hour. And the galaxy itself is moving through space, falling toward the center of our local group of galaxies. And the local group is falling toward larger structures. Add all these motions together, and we're moving through the cosmic microwave background, the closest thing we have to a universal reference frame, at about 1.3 million miles per hour. Every motion nested inside another motion, like Russian dolls of velocity. And through it all, you lie still, feeling none of it, carried along by momentum older than the Earth itself. The galaxy's rotation has been carrying us for 4.5 billion years, and it will carry us for billions more. We're passengers on a cosmic ship, moving through an ocean of space and time we can barely comprehend. The name Milky Way has an etymology worth lingering on. It comes from the Latin Via Lactea, which means Milky Way or Milky Road. The Romans borrowed this from the ancient Greeks, who called it Galaxias Kyklos, the Milky Circle. And from that Greek word galaxias, we get our modern word galaxy. Every time you say galaxy, you're invoking milk, the same metaphor that named our home. But why milk? The Greeks had their myth about Hera and Heracles, the spilled milk of a goddess creating a river of light. But there's something more fundamental at play. When you look at the Milky Way with the naked eye on a dark night, it does look milky. It's not individual stars. Those are too faint and too numerous to resolve without a telescope. Instead, you see a diffuse glow, a pale luminosity stretching across the sky like someone spilled cream on black velvet. Different cultures use different metaphors, of course. In Chinese mythology, it's the Silver River, separating the weaver girl from the cowherd, crossed by a bridge of magpies once a year. The Norse called it the path to Valhalla. Some Native American tribes saw it as a seam in the sky, or a pathway for spirits, or the backbone of the universe. Each culture looked at the same phenomenon and found different meaning, different stories. What they all shared, though, was a sense that this band of light was significant. It wasn't just a random pattern of stars. It was a structure, a feature, something that demanded attention and explanation. They were right, of course, though they couldn't have known how right. The Milky Way isn't just a pattern, it's the galaxy we're inside, the structure that contains our entire visible universe until very recently in human history. There's something poignant about the fact that we named our galaxy after milk, after something domestic and nurturing and familiar. We could have called it the stellar disk, or the galactic plane, or used some technical term. But instead, we kept the ancient name, the one that compares the cosmos to something you might pour in your coffee or give to a child. It's a reminder that our understanding of the universe grows from humble metaphors, from trying to describe the unknown in terms of the known, from looking up at incomprehensible vastness and saying, "It looks a bit like milk, doesn't it?" On a perfectly dark night, far from city lights, with excellent eyesight and clear skies, you can see perhaps 3,000 to 4,000 individual stars with your naked eye. If conditions are absolutely ideal, desert darkness, high altitude, no moon, you might push that to 6,000 or so. That seems like a lot. It is a lot in the sense that 6,000 distinct points of light is more than you can easily count, but the Milky Way contains at least 100 billion stars, probably more like 200 to 400 billion. If we take a conservative estimate of 100 billion, and you can see 5,000 of them, you're seeing about 0.005% of the galaxy. If we use the higher estimate of 400 billion stars, it drops to 0.0125%. The exact percentage doesn't really matter. The point is that you're seeing an almost incomprehensibly tiny fraction of what's actually there. Think about that for a moment. Even on the darkest night, in the most remote location, with perfect eyesight, you're glimpsing just the tiniest sliver of your galactic home. The rest is hidden by distance, dimmed by intervening dust, or simply too faint for your eyes to register. You're like someone standing at the edge of an ocean, able to see only the first few feet of water, while miles of depth stretch beneath you unseen. And even that tiny fraction you can see is skewed. The brightest stars are overrepresented in your vision. Most of the galaxy's stars are dim red dwarfs, too faint to see from Earth even if they were relatively close. The stars you can see are disproportionately the rare bright ones, massive blue giants, luminous supergiants, nearby neighbors. You're seeing the galaxy's highlights, not its typical members. There's something both humbling and freeing about this limitation. Humbling because it reminds you how small your perceptual bubble is, how much of reality exists beyond your senses, but freeing because it means you're not required to see everything. You can look up, see a few thousand stars scattered across the night, and let that be enough. The other 100 billion stars will continue their existence, whether you perceive them or not. They don't need your attention to exist. The galaxy is vast beyond comprehension, and you're allowed to know it through the tiny fraction you can observe. You're allowed to be small, to have limited senses, to see only the nearest and brightest while the rest remains forever in darkness. That's not a failure of perception. That's just the nature of being a small, finite observer in an immense cosmos. In 1610, Galileo Galilei turned his newly improved telescope toward the Milky Way and made a discovery that would begin to unravel centuries of speculation. The pale band of light that stretched across the night sky wasn't a cloud or a crack in the celestial sphere or some kind of cosmic vapor. It was made of stars, countless individual stars, too faint and too closely packed to resolve with the naked eye, but clearly visible through his telescope as distinct points of light. This was revolutionary, though perhaps not in ways that were immediately obvious. Before Galileo, people had theories about the Milky Way. Democritus had speculated it might be distant stars, and others had proposed various ideas, but no one knew for certain. It was one of many celestial mysteries, a phenomenon that demanded explanation but offered little evidence for any particular theory. Galileo's telescope changed that. Suddenly, you could see for yourself that the Milky Way was composed of individual stars, densely packed. It was empirical evidence, the kind that settles arguments more effectively than philosophical speculation. The telescope revealed a structure where the naked eye saw only smooth luminosity. But Galileo still didn't understand what he was seeing. He thought he was looking at a distant collection of stars, perhaps part of a larger stellar sphere. He had no concept of galaxies, no understanding that the Milky Way was a disc-shaped structure and that we were inside it. That understanding wouldn't come for another 300 years. Galileo had revealed the stars, but the true nature of the Milky Way, our embeddedness within it, its spiral structure, its place among billions of other galaxies, all of that remained hidden. It's worth pausing to appreciate this. One of the greatest observational astronomers in history made a crucial discovery about the Milky Way, and yet he still had no idea what the Milky Way actually was. He saw deeper than anyone before him, and it still wasn't deep enough to grasp the full picture. That's not a criticism of Galileo. It's a reminder that understanding comes in layers, that each discovery reveals not just answers, but new questions, that the cosmos is patient in revealing its secrets. We know now what Galileo couldn't, that those countless faint stars he saw are our fellow inhabitants of the galactic disk, that we're looking at the densest concentration of stars from our vantage point inside the structure. But in 1610, it was enough to know they were stars at all. Sometimes, progress means just resolving the next level of detail, even if you don't yet understand what you're seeing. For most of human history, tens of thousands of years of anatomically modern humans, thousands of years of civilization, centuries of scientific astronomy, we didn't know we lived inside a galaxy at all. That realization came shockingly recently, in the early decades of the 20th century. Before that, the concept of a galaxy as we understand it today didn't really exist. People saw the Milky Way, of course. They created myths about it, observed it, even studied it with telescopes. But they didn't understand that this band of light represented our view from inside a vast disk of stars. They thought the universe was much smaller, that the stars they could see were perhaps arranged in some kind of sphere or cluster, with the Milky Way being either a separate phenomenon or just a denser region of stars. The story of how we came to understand our galactic address is long and involves many astronomers making incremental progress over centuries. But the key moment came in the 1920s with the work of Edwin Hubble and others. when it was finally established that some of the fuzzy nebulae visible in telescopes were actually other galaxies, separate islands of stars far beyond the Milky Way. Once you knew other galaxies existed, you could work backward and realize we must live in one too. This shift in understanding, from thinking of the universe as a single collection of stars to realizing we inhabit one galaxy among billions, might be the most dramatic expansion of cosmic perspective in human history. It's comparable to the Copernican revolution, which displaced Earth from the center of the universe. But whereas Copernicus expanded our understanding of the solar system, the discovery of galaxies expanded our understanding of the universe itself. And it happened within the lifetime of people who are still alive today, at least in terms of its full acceptance and elaboration. Your grandparents or great-grandparents lived in a time when we were still mapping out the basic structure of the Milky Way, still discovering what it means to live inside a galaxy. This isn't ancient history. This is recent understanding, fresh perspective, the kind of knowledge that hasn't yet fully filtered through the collective consciousness. There's something both exciting and unsettling about this. Exciting because it means we're still in the early stages of cosmic understanding, still making fundamental discoveries. Unsettling because it makes you wonder, what else don't we know? What basic facts about our reality are we still missing, waiting for the next conceptual revolution to reveal them? On April 26, 1920, two prominent astronomers, Harlow Shapley and Heber Curtis, participated in what's now known as the Great Debate at the Smithsonian Museum of Natural History in Washington, D.C. The topic was the scale of the universe, specifically whether so-called spiral nebulae were small objects within the Milky Way or separate galaxies, island universes, far beyond our own galaxy. Shapley argued that the Milky Way was much larger than previously thought, and that spiral nebulae were relatively nearby objects within it. Curtis argued that spiral nebulae were separate galaxies, comparable in size to the Milky Way, and located at enormous distances. They were arguing, in essence, about the size of the entire known universe. If Shapley was right, the universe consisted of one large galaxy. If Curtis was right, the universe contained countless galaxies, each a Milky Way scale structure in its own right. The debate wasn't definitively resolved at the time. Both astronomers had evidence supporting their views, and both had weaknesses in their arguments. Shapley was closer to correct about the size of the Milky Way. It was indeed larger than the earlier estimates Curtis was using. But Curtis was right about the spiral nebulae being separate galaxies. In a sense, both were partially correct and partially wrong, which is often how scientific disputes work out. The resolution came a few years later, in 1924, when Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to observe Cepheid variable stars in the Andromeda Nebula. Cepheid variables have a known relationship between their brightness and pulsation period, which makes them excellent distance indicators, standard candles in astronomy. By measuring the period of Cepheids in Andromeda, Hubble could calculate its distance. The answer was clear. Andromeda was far too distant to be part of the Milky Way. It was a separate galaxy. With that measurement, the universe expanded overnight in human understanding. Suddenly, we knew there were other galaxies. And if there was one, there were probably many more. The Milky Way was not the universe. It was a component of something much larger. The night sky, which had seemed vast with its countless stars, now revealed itself as even vaster, full of entire galaxies, each containing billions of stars. The Great Debate is remembered not because it was settled in 1920, it wasn't, but because it represents a pivotal moment when humanity was on the cusp of a new understanding. The question being debated was so fundamental that the answer would reshape cosmology. And within just a few years, we had that answer, and the universe would never seem the same again. Edwin Hubble is often credited with discovering that the universe extends beyond the Milky Way. Though as with most scientific discoveries, the story is more complex than a single eureka moment. What Hubble did in 1924 was provide definitive evidence that the Andromeda Nebula, a fuzzy patch of light visible even to the naked eye under dark skies, was actually a separate galaxy located about 2.5 million light-years away. This was done by observing Cepheid variable stars, stars whose brightness fluctuates in a predictable pattern. The astronomer Henrietta Leavitt had earlier discovered that the period of a Cepheid's pulsation is directly related to its intrinsic brightness. Brighter Cepheids pulse more slowly. If you measure how long a Cepheid takes to pulse, you know how bright it actually is. Compare that to how bright it appears from Earth, and you can calculate its distance using the inverse square law. Brightness falls off with the square of distance. Hubble identified Cepheids in Andromeda and measured their periods. The calculations were unambiguous. Andromeda was far beyond the estimated boundaries of the Milky Way. It had to be a separate structure, a separate galaxy. And if Andromeda was a separate galaxy, then surely other spiral nebulae were too. This discovery expanded the known universe by an almost unimaginable factor. Before Hubble's measurement, many astronomers thought the Milky Way encompassed everything. All the stars, all the nebulae, all the visible universe. After his measurement, the universe suddenly contained multiple galaxies. And as telescopes improved, astronomers found more and more galaxies, until it became clear that galaxies numbered in the billions, perhaps trillions. It's hard to overstate the psychological and philosophical impact of this shift. The universe had seemed large with the Milky Way's 100 billion stars. Now it was incomprehensibly larger, not just one galaxy, but countless galaxies, each with billions of stars. Humanity's cosmic address grew from Earth, Solar System, Milky Way to Earth, Solar System, Milky Way, one galaxy among billions. The same basic hierarchy, but with an extra, staggering level added on top. And Hubble wasn't done. Later in the 1920s, he measured the distances to many more galaxies and noticed something peculiar. The farther away a galaxy was, the faster it appeared to be moving away from us. This was the first observational evidence that the universe itself is expanding, a discovery that would lead to the Big Bang theory and an entirely new understanding of cosmic history. But that's another story. For now, it's enough to recognize that Hubble's work in 1924 fundamentally changed our understanding of where we are. The Milky Way was no longer the universe. It was a single galaxy, one among an almost infinite population of galaxies scattered through an unimaginably vast cosmos. The night sky, which had seemed crowded with stars, was actually almost empty, with vast distances separating our galaxy from all the others. And that discovery, made less than a century ago, still shapes how we think. about our place in the cosmos today. For most of human history, we couldn't see the full structure of the Milky Way because we're inside it, looking out through layers of dust and gas. Visible light doesn't penetrate dust very well. It gets absorbed or scattered, the same way headlights scatter in fog. This means that when you look toward the galactic center, you can see only a few thousand light years before the view becomes completely obscured. The heart of the galaxy, just 26,000 light years away, is hidden behind thick clouds of cosmic dust. This limitation meant that for centuries, even as we developed better and better optical telescopes, we couldn't map the Milky Way's spiral structure. We knew it was a flattened disk of stars. That much was clear from the Milky Way's appearance. But were there spiral arms? How many? Where exactly were they? These questions remained unanswered because we simply couldn't see far enough through the dust. The breakthrough came in the 1950s with the development of radio astronomy. Radio waves have much longer wavelengths than visible light, which means they can slip through dust clouds that would completely block optical observations. It's like the difference between throwing pebbles at a chain-link fence, some get through the gaps, versus throwing beach balls, which all bounce off. Radio waves are the pebbles. They find their way through the spaces between dust grains. Using radio telescopes, astronomers could detect hydrogen gas throughout the galaxy. Hydrogen is the most abundant element in the universe, and it emits radio waves at a specific frequency, 21 centimeters. By mapping this hydrogen emission and measuring its Doppler shift to determine how fast it was moving, astronomers could start to piece together the galaxy's structure. They found that the hydrogen wasn't uniformly distributed. It was concentrated in long, curved lanes that traced out spiral arms. This was how we finally mapped the Milky Way's spiral structure, not by looking at it directly, but by listening to the radio whispers of hydrogen gas threading through it. It's a bit like exploring a dark cave system using sonar instead of a flashlight. You can't see the walls, but you can detect them through reflections and echoes, building a mental map from indirect evidence. Even today, with infrared telescopes that can also see through dust, much of the Milky Way remains hidden from direct observation. We've built detailed maps, but they're still incomplete, still being refined as new observations come in. We're still, in a very real sense, trying to understand the shape of the forest from deep within the trees, using every wavelength of light we can detect to build a picture of the whole. About 1/3 of humanity has never seen the Milky Way. Not because they haven't looked up, but because they live under skies so bright with artificial light that the galaxy's faint glow is completely drowned out. In major cities, New York, London, Tokyo, Mumbai, the night sky is often orange or gray, reflecting streetlights and building lights and the collective glow of millions of human sources. Against this artificial brightness, all but the brightest stars vanish, and the Milky Way disappears entirely. This is a relatively recent development in human history. 100 years ago, nearly everyone could see the Milky Way. It was simply part of the night sky, as common and expected as the moon. People planned their activities around it, navigated by it, told stories about it. The night sky was darker then, punctuated by stars and that pale river of light cutting across the heavens. Now for billions of people, the night sky is empty. Children grow up in cities never seeing more than a handful of stars, never experiencing the overwhelming sensation of looking up and seeing thousands of points of light scattered across darkness. They might see the moon and Venus and maybe a few bright stars if conditions are right. But the Milky Way, it's absent, erased by the glow of their own civilization. There's something profound about this loss, even if it's not immediately obvious. The Milky Way has been part of human experience for as long as humans have existed. Every culture had stories about it, used it for navigation, incorporated it into their mythology and worldview. It was a constant presence, connecting people to the cosmos in a direct, visual way. And now, within just a few generations, we've eliminated it from view for much of the population. What does it mean to grow up never seeing your place in the galaxy? Never experiencing that humbling sensation of looking up and realizing you're inside something vast? It's hard to say, but perhaps it matters. Perhaps there's value in occasionally confronting the scale of the universe, in seeing directly that you're part of something much larger than yourself. Light pollution takes that away, replacing cosmic perspective with the immediate glow of human activity. The good news, if there is any, is that the Milky Way is still there. It hasn't actually gone anywhere. If you drive a few hours away from the city, get away from the light domes that surround urban areas, find a dark location on a moonless night. You can still see it. It takes effort now, intentionality, a willingness to travel. But it's possible. The galaxy hasn't abandoned us. We've just made it harder to see, surrounded ourselves with so much light that we've hidden the stars. And maybe that's worth thinking about. Not in a judgmental way. Light has benefits, safety and visibility, and the ability to extend our days. But as a trade-off we've made, perhaps without fully realizing what we were trading away. We've gained illuminated cities and lost dark skies. Both have value. Both shape how we see ourselves and our place in the cosmos. The Aboriginal peoples of Australia have the oldest continuous culture on Earth, with traditions stretching back at least 65,000 years. And for all that time, they've been observing the night sky, developing sophisticated astronomical knowledge, and passing it down through generations. One of the most fascinating aspects of their astronomy is how they mapped the sky, not just by connecting bright stars into constellations, but by identifying and naming the dark spaces between the stars. These are called dark constellations, and they're created by dense clouds of dust in the Milky Way that block the light from stars behind them. To Western eyes trained to look for patterns in the stars themselves, these dark patches might seem like absences, empty spaces in the galactic band. But Aboriginal astronomers saw them as shapes, an emu, a crocodile, and many others, each with their own stories and seasonal significance. The most famous is probably the emu in the sky, which stretches across the Milky Way. Its body is formed by the Coalsack Nebula near the Southern Cross, and its neck and head extend along the dark lane towards Scorpius. The emu appears in different orientations throughout the year, and its position was used to predict when emu eggs would be ready to harvest. The sky emu and the terrestrial emus were connected, part of a cyclical relationship between the heavens and the earth. This represents a fundamentally different way of seeing the sky. Most astronomical traditions worldwide focused on the stars, connecting them into patterns, tracking their movements, using them for navigation. But Aboriginal astronomy incorporated the darkness itself, recognizing that the spaces between stars were also meaningful, also part of the cosmic landscape. They were seeing structure that other cultures missed, finding patterns in absence rather than presence. And they were right, of course, though not in the way they might have originally thought. Those dark patches aren't empty. They're dense clouds of dust and gas, stellar nurseries where new stars are being born, or remnants of old stars that have died and shed their material back into space. The Aboriginal astronomers who named these dark constellations were mapping real structures in the galaxy, even without telescopes or modern astrophysics. There's something beautiful about this, the idea that different cultures, looking at the same sky, can see completely different things depending on how they choose to look. One culture connects the bright dots. Another maps the darkness between them. Both are valid. Both reveal something true about the cosmos. And both remind us that there are many ways to know the universe, many perspectives from which to understand our place within it. The Aboriginal star catalogues are among the oldest astronomical traditions still practiced today. A continuous thread of observation and knowledge stretching back tens of thousands of years. They predate agriculture, writing, cities, almost everything we think of as civilization. And yet they contain sophisticated astronomical knowledge, carefully preserved and transmitted across countless generations. It's a reminder that humans have been stargazers for as long as we've been human, looking up and wondering, finding meaning in the patterns above, whether those patterns are made of light or shadow. In 2013, the European Space Agency launched a spacecraft called Gaia with a singular purpose: to measure the positions and motions of stars with unprecedented precision. Not a handful of stars, not thousands, but over 1 billion stars, about 1% of the Milky Way's total stellar population. The mission has been an extraordinary success, creating the most detailed three-dimensional map of our galaxy ever made. The precision Gaia achieves is almost hard to believe. For the brightest stars, Gaia can measure their positions to within about 20 micro-arcseconds. That's roughly equivalent to measuring the width of a human hair from 1,000 kilometers away, or spotting a coin on the moon from Earth. At this level of precision, Gaia can detect not just where stars are, but how they're moving through space, their velocity in 3 dimensions, tracing their paths as they orbit the galactic center. This has revealed things about the Milky Way we never knew. For instance, Gaia data showed that the galaxy's disk isn't perfectly flat, but has waves rippling through it, like a flag flapping in the wind. These waves were so subtle that they were invisible until Gaia measured the positions of millions of stars and found systematic patterns in their vertical motions. The ripples are probably the result of past encounters with smaller galaxies, collisions that sent shockwaves through the disk that are still resonating billions of years later. Gaia has also traced the remnants of ancient galactic mergers. When the Milky Way consumes a smaller galaxy, the stars from that galaxy don't just disappear. They remain in orbit, but now as part of the Milky Way. Over time, they spread out, but they retain a memory of their origin in their orbits and velocities. By analyzing Gaia's data, astronomers have identified streams of stars that once belonged to separate galaxies, including one called Gaia Enceladus, that merged with the Milky Way about 10 billion years ago. We're literally seeing the fossils of ancient cosmic collisions, preserved in the motions of stars. What's remarkable is that this precision comes from a spacecraft orbiting a point in space about 1.5 million kilometers from Earth, constantly spinning and scanning the sky, measuring stars over and over again to refine their positions. Gaia has observed each of its target stars an average of 70 times, building up a detailed picture of where they are and how they're moving. The result is a map of the Milky Way that shows not just a static snapshot, but a dynamic portrait of a galaxy in motion. This is modern astronomy at its finest, using technology to extend our senses far beyond their natural limits, collecting data on a scale that would be impossible for human observers, and using that data to reconstruct the history and structure of our galaxy. Gaia has given us eyes precise enough to see the Milky Way as it really is, not a fixed structure, but a living, evolving system shaped by billions of years of collisions, star formation, and gravitational interactions. And the mission isn't over. Gaia continues to observe, and each new data release reveals more details, more structure, more history written in the positions and motions of stars. We're living in an era where we can map our galaxy with extraordinary precision, where we can trace its history and predict its future, all because of a spacecraft the size of a small car orbiting quietly in space, measuring starlight with exquisite care. On July 4, 1054, CE, observers in China, Japan, and the Middle East recorded the appearance of a guest star in the constellation Taurus. This wasn't a normal star. It was far brighter than anything else in the sky except the sun and moon. In fact, it was bright enough to be visible during the daytime for 23 days, and it remained visible at night for nearly 2 years before gradually fading from view. What these medieval astronomers had witnessed was a supernova, the catastrophic death explosion of a massive star. The star had reached the end of its life, exhausted its nuclear fuel, and collapsed in on itself before rebounding in a violent explosion that briefly outshone the entire galaxy. For a few weeks, that single dying star was as bright as billions of stars combined, releasing in seconds more energy than the sun will produce in its entire 10 billion year lifetime. The explosion occurred about 6,500 light years away in the Milky Way, which means the light took 6,500 years to reach Earth. The star actually exploded around 5,500 BCE, when humans were just beginning to develop agriculture in the Fertile Crescent. But the light from that event traveled through space for millennia, finally arriving in 1054 CE, to be recorded by observers who had no idea what they were seeing, only that something extraordinary had appeared in the heavens. Today, we can still see the remnant of that explosion. It's called the Crab Nebula, and it's a roughly circular cloud of glowing gas about 11 light years across, still expanding outward from the site of the explosion at thousands of kilometers per second. At the center is a pulsar, a rapidly spinning neutron star, the collapsed core of the original star, now compressed to incredible density and spinning 30 times per second, beaming radiation into space like a cosmic lighthouse. The Crab Nebula is one of the most studied objects in astronomy, observed at every wavelength from radio waves to gamma rays. It's a laboratory for extreme physics, a place where matter and energy behave in ways that can't be replicated on Earth. And it's also a historical artifact, a cosmic event documented by human observers nearly 1,000 years ago, preserved in medieval records and still visible in our telescopes today. There's something profound about the connection between past and present here. The same light that reached observers in 1054, traveling for 6,500 years across the void, continues to reach us today from the expanding remnant. We're seeing the aftermath of an event that those medieval astronomers saw at its peak, connected across centuries by the light of a dead star. They didn't know what it was, couldn't understand the physics of it, but they recorded it carefully, and their records helped us identify the remnant and understand what happened. The supernova of 1054 is a reminder that the Milky Way is not static. Stars are born, live their lives, and die, sometimes spectacularly. The death of that one star enriched the surrounding space with heavy elements forged in its core and in the explosion itself. Those elements might someday be incorporated into new stars, new planets, perhaps even new life. The cycle continues, powered by events like this one, recorded by curious observers who looked up and noticed something new in the eternal sky. The center of the Milky Way wasn't identified until the 1940s, which might seem strange given that we've been studying the galaxy for centuries. But there's a good reason for the delay. The galactic center is hidden behind thick clouds of dust in the constellation Sagittarius, invisible to optical telescopes. If you look towards Sagittarius on a dark night, you'll see a particularly dense region of the Milky Way, but you're not seeing the center itself. That's completely obscured. For a long time, we didn't even know where to look. Early astronomers assumed we were near the center of the galaxy, or that the galaxy had no particular center at all. It wasn't until the early 20th century that Harlow Shapley, studying the distribution of globular clusters, realized we must be far from the center. The clusters formed a spherical halo, but the center of that halo was thousands of light years away in the direction of Sagittarius. Even once we knew roughly where to look, we couldn't see through the dust. The breakthrough came with radio astronomy and later infrared observations. These longer wavelengths can penetrate dust, revealing what lies beyond. Using radio telescopes, astronomers found a compact, intense radio source at the galactic center, something emitting vast amounts of energy from a very small region. They called it Sagittarius A, pronounced Sagittarius A star, and it would turn out to be one of the most important objects in the galaxy. Sagittarius A is now known to be a supermassive black hole weighing about 4 million times the mass of the Sun. It sits at the absolute center of the Milky Way, surrounded by a dense cluster of stars orbiting at incredible speeds. Some of these stars have been tracked for decades, allowing astronomers to map their orbits and calculate the mass of the black hole they're orbiting. The evidence is unambiguous. There's something with 4 million solar masses concentrated in a region smaller than Mercury's orbit, and the only thing that can be is a supermassive black hole. In 2022, astronomers released the first image of Sagittarius A, not the black hole itself, which is invisible, but its shadow, the dark region, surrounded by glowing gas, heated to millions of degrees as it spirals inward. Creating this image required coordinating radio telescopes across the entire Earth, turning our planet into a single massive telescope, capable of resolving details smaller than the black hole's event horizon. It was a technological triumph and a visual confirmation of what we'd already deduced. The heart of our galaxy contains a supermassive black hole, a cosmic engine that has shaped the Milky Way's evolution for billions of years. But for most of history, that heartbeat in complete darkness, unknown and unknowable, hidden behind veils of dust that only recently we've learned to see through. The galactic center was always there, of course, holding the galaxy together with its immense gravity, but it remained invisible until we developed the right tools to detect it. It's a reminder that what we can see directly is just a fraction of what exists. The universe doesn't reveal itself easily. It requires patience, ingenuity, and new ways of looking before its secrets emerge from darkness. The Milky Way has 4 major spiral arms winding out from the central bar-shaped structure: the Perseus arm, the Sagittarius arm, the Centaurus arm, and the Cygnus arm. These are named after the constellations where they appear most prominent from our perspective, though of course the arms themselves extend for tens of thousands of light years, far beyond any constellation's boundaries. Each arm is a region of higher density, where stars, gas, and dust are more concentrated than in the spaces between arms. They're not solid structures. Stars aren't stuck to the arms like they would be to the spokes of a wheel. Instead, the arms are density waves, pressure waves that move through the galactic disk like ripples on a pond. Stars and gas flow through these waves, slowing down as they enter the denser regions and speeding up as they exit, creating the spiral pattern. But we don't live in one of the major arms. We live in a smaller structure called the Orion Spur, or the Local Spur, or sometimes the Orion Cygnus arm. It's a minor arm, a kind of cosmic side street connecting the larger Sagittarius and Perseus arms. It's about 10,000 light-years long and perhaps 3,500 light-years wide. And it's home to the sun and all the nearby stars you can see with the naked eye. Living in a minor arm might seem unremarkable, but it's probably significant for our existence. The major arms are denser, which means more stars packed closer together, which means higher rates of supernovae and more intense radiation. In a major arm, the environment would be more turbulent, more dangerous for a planet trying to maintain stable conditions for billions of years while life evolves. Here in the Orion Spur, things are quieter, more stable, enough activity to be interesting, not so much that it's hazardous. The spiral structure of the Milky Way is still being refined. It's difficult to map the galaxy's structure from inside it. And different studies sometimes come to slightly different conclusions about the number and exact positions of the spiral arms. Some models suggest there are only 2 main arms, with the others being minor features. Others count more arms or find bridges and spurs connecting the major structures. The truth is probably somewhere in the middle, and the exact details matter less than the overall picture. The Milky Way is a spiral galaxy with multiple arms winding outward from the center, and we live in one of the smaller branches, orbiting peacefully in a relatively calm region of the galactic disk. These arms are sites of active star formation. The increased density in the arms causes gas clouds to collapse more readily, triggering the birth of new stars. The massive, hot blue stars that form in these regions are short-lived. They burn through their fuel quickly and explode as supernovae after just a few million years. This means the spiral arms are lit up by young, bright stars that trace out the arm's structure. The Sun, being middle-aged and less massive, is more of a background resident, part of the longer-lived stellar population that fills the disk between the dramatic, star-forming regions. It's a bit like living in a suburb instead of downtown. The major arms are where the action is, new stars being born, massive stars exploding, intense radiation and stellar winds shaping their surroundings. The Orion Spur is quieter, less dramatic, a cosmic residential neighborhood where middle-aged stars like the Sun can orbit in relative peace. It's not the most exciting address in the galaxy, but it's probably one of the safest, and that might be exactly what's needed for a planet to harbor life for billions of years. At the very center of the Milky Way sits Sagittarius A, a supermassive black hole weighing approximately 4 million times the mass of our Sun. Despite this enormous mass, it would fit comfortably inside Mercury's orbit. The region is small in astronomical terms, compressed to incredible density, a point of such intense gravity that not even light can escape once it crosses the event horizon. Black holes are strange objects, predictions of Einstein's general relativity so extreme that even Einstein himself was skeptical they could exist. A supermassive black hole is even stranger, millions or billions of times the mass of the Sun, compressed into a region smaller than a solar system. How such objects form is still debated. They appear to exist at the centers of most large galaxies, suggesting they play a fundamental role in galactic evolution, but the exact mechanisms by which they grow to such enormous sizes remain unclear. Sagittarius A is relatively quiet. For a supermassive black hole, some galactic centers blaze as quasars, actively consuming vast amounts of material and radiating energy that outshines the entire galaxy. Sagittarius A, by contrast, sips its fuel slowly, occasionally flaring when a stray gas cloud or asteroid wanders too close and gets torn apart by tidal forces. These flares have been observed in X-rays, sudden brightening events that last for hours or days before fading back to the baseline level. Around the black hole orbits a dense cluster of stars, packed much more tightly than stars are elsewhere in the galaxy. Some of these stars have been tracked for decades as they complete their orbits around the invisible mass at the center. One star, called S2 or S02, orbits Sagittarius A SAR in just 16 years, reaching speeds of up to 3% the speed of light at its closest approach. By measuring this star's orbit with exquisite precision, astronomers have confirmed that the mass at the center is indeed a black hole. Nothing else could be so massive and so compact. The event horizon of Sagittarius A, the boundary beyond which nothing can escape, is about 12 million kilometers in radius, roughly 17 times the Sun's radius. Inside this boundary, space-time is so warped that all paths lead inward. Time itself behaves strangely near the horizon, slowing down relative to distant observers, approaching a standstill at the boundary. An observer falling toward the black hole would experience their own time normally, but to someone watching from far away, they would appear to slow down asymptotically, never quite reaching the horizon, frozen at the edge forever. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A's shadow, the dark region where the black hole blocks light from the glowing gas surrounding it. The image shows a bright ring of emission with a dark center, exactly as general relativity predicts. Creating this image required coordinating radio telescopes across the entire Earth, combining their observations to achieve resolution high enough to see features the size of the black hole's event horizon from 26,000 light-years away. Sagittarius A is our galaxy's central anchor, the gravitational nexus around which everything else orbits. It's been there for billions of years, growing slowly as it consumes gas and occasionally captures passing stars. It will remain there for billions more, long after the sun dies and the Earth is gone, quietly holding the galaxy together. A cosmic spider at the center of a web 100,000 light-years across. Here's a fact that challenges intuition. Sagittarius A, the supermassive black hole at the center of the Milky Way, contains 4 million times the mass of our Sun, yet it would fit comfortably inside Mercury's orbit. Mercury orbits the Sun at an average distance of about 58 million kilometers. The event horizon of Sagittarius A, the boundary beyond which nothing can escape, has a radius of only about 12 million kilometers. You could fit the entire black hole inside Mercury's orbit with room to spare. This is what makes black holes so extreme. They're not just massive. Lots of things are massive. 1 million stars have 1 million times the Sun's mass, and they're spread out over many light years. But a black hole compresses all that mass into an incredibly small volume. The more massive a black hole, the larger its event horizon, but the relationship is linear. Double the mass, double the radius. The density, however, mass divided by volume, becomes almost meaningless because the mass is concentrated at a singularity, a point of infinite density at the very center. For comparison, the Sun has a radius of about 700,000 kilometers. To turn the Sun into a black hole, you'd have to compress it down to a radius of about 3 kilometers, about the size of a small town. The Earth would need to be compressed to about 9 millimeters, smaller than a marble. These are the Schwarzschild radii for these objects, the size of the event horizon if they were to become black holes. They don't become black holes naturally. Neither has enough mass to collapse that far, but the comparison shows just how extreme the compression needs to be. Sagittarius A, with 4 million solar masses, has an event horizon that's proportionally larger, but still remarkably small compared to its mass. It's one of the most dense concentrations of matter in the known universe, rivaled only by other supermassive black holes, or the briefly existing conditions during a supernova core collapse. What happens inside the event horizon is unknown. General relativity predicts a singularity at the center, a point where space-time curvature becomes infinite, where the laws of physics as we know them break down. But most physicists suspect this is a sign that general relativity is incomplete, that quantum effects become important at these scales and prevent the true singularity from forming. We don't have a quantum theory of gravity yet, so we can't say for sure what the core of a black hole actually contains. What we can say is that from the outside, Sagittarius A appears as a region of space where 4 million solar masses have vanished from view, leaving behind only their gravitational influence and a boundary that marks the point of no return. It's smaller than our inner solar system, yet it holds our galaxy together, its gravity organizing the orbits of hundreds of billions of stars. Density and compactness raised to an extreme that still, even after decades of studying black holes, feels almost impossible to accept. The Milky Way exists inside a halo of dark matter that extends far beyond the visible disk, perhaps 10 times wider than the galaxy we can see. This halo is roughly spherical, or at least more spherical than the flattened disk of stars and gas. It contains most of the galaxy's mass, yet it's completely invisible. We know it's there only through its gravitational effects on the visible matter we can observe. Dark matter doesn't emit light. It doesn't absorb light. It doesn't reflect light. It doesn't interact electromagnetically at all, as far as we can tell. It interacts only through gravity, pulling on everything around it, but remaining otherwise invisible and intangible. If dark matter particles are passing through you right now, and they probably are, billions of them every second, you wouldn't feel anything. They'd pass through your body, through the earth, through the sun, barely interacting at all. So how do we know it exists? The most direct evidence comes from rotation curves, graphs showing how fast objects orbit the galaxy at different distances from the center. If you calculate how fast stars should orbit based only on the visible mass, stars, gas, dust, you find that outer stars should move more slowly than they actually do. They're moving too fast, which means there must be additional mass we can't see providing extra gravitational pull. The distribution of this dark matter has been mapped by observing its gravitational effects. It forms a diffuse halo around the galaxy, with density highest near the center and gradually decreasing toward the edges. The visible Milky Way, the disk of stars and gas, is embedded in this halo like a coin floating in a sphere of invisible gelatin. The dark matter outweighs the visible matter by a factor of about 10 to 1, perhaps more. What is dark matter made of? We don't know. The leading hypothesis is that it consists of exotic particles that were created in the early universe and have been around ever since. These particles might be weakly interacting massive particles, WIMPs, or axions, or something else we haven't thought of yet. Numerous experiments are underway trying to detect dark matter particles directly, but so far, none have succeeded. Whatever dark matter is, it's remarkably good at hiding. Alternative theories suggest that dark matter might not be matter at all. Perhaps it's a sign that our theory of gravity needs modification on galactic scales. But most physicists favor the particle explanation because it explains not just galactic rotation curves, but also many other observations. The large-scale structure of the universe, gravitational lensing patterns, the cosmic microwave background fluctuations. All of these phenomena point to the existence of additional mass that we can't see. So we live inside an invisible sphere, a gravitational cocoon we can only detect through its influence on the things we can see. It's like living inside a building we can't perceive directly. We know it's there because doors open and close, because there are walls we bump into, because things fall down instead of floating away. But the building itself remains invisible, a structure we infer from its effects rather than observing directly. The dark matter halo is arguably the most important component of the Milky Way. Without it, the galaxy wouldn't hold together. The stars would fly off into intergalactic space. It provides the gravitational foundation on which the visible galaxy is built, an invisible scaffold supporting everything we can see. And yet we know almost nothing about it. Not what it's made of, not how it formed, not whether it has substructure or is smoothly distributed. It's one of the universe's deepest mysteries, and we're living inside it. Scattered throughout the Milky Way are massive clouds of gas and dust called nebulae, stellar nurseries where new stars are born. These clouds can be light years across, absolutely vast by human standards, yet so diffuse that by Earth standards they'd count as a vacuum. The density might be just a few hundred molecules per cubic centimeter, compared to the roughly 1019 molecules per cubic centimeter in the air you're breathing right now. But across such enormous volumes, even extremely diffuse gas adds up to substantial mass. A large molecular cloud might contain hundreds of thousands of times the mass of the Sun, all of it slowly drifting through space, held together by its own weak gravity. And occasionally, something triggers collapse. Maybe a nearby supernova sends a shockwave through the cloud. Maybe the cloud collides with another cloud. Maybe it just accumulates enough mass that its own gravity overcomes the internal pressure resisting collapse. When a region of the cloud starts to collapse, it heats up. Gravitational potential energy converts to thermal energy as the gas falls inward. The collapsing region fragments into smaller clumps, each one continuing to collapse independently. Over hundreds of thousands of years, these clumps become denser and hotter, until eventually the core temperature reaches about 10 million degrees, hot enough for nuclear fusion to begin. Hydrogen atoms start fusing into helium, releasing energy that halts the collapse. A star is born. The most famous stellar nursery visible from Earth is the Orion Nebula, located about 1,350 light-years away in the constellation Orion. It's visible to the naked eye as a fuzzy patch in Orion's sword, and through a telescope, it reveals itself as a glowing cloud illuminated by the intense radiation from newly formed stars within it. The central region contains 4 massive stars called the trapezium, whose ultraviolet light causes the surrounding gas to glow, creating the beautiful nebula we see. But the Orion Nebula is just one example. The Milky Way contains hundreds of such regions, each one a factory producing new stars from the raw materials of gas and dust. Some are enormous, like the Carina Nebula or the Tarantula Nebula in the Large Magellanic Cloud. Others are smaller, more modest affairs, birthing just a few stars at a time. These nebulae are also enriched with heavier elements from previous generations of stars. The first stars in the universe were made of almost pure hydrogen and helium, the primordial elements created in the Big Bang. But those stars fused lighter elements into heavier ones: carbon, oxygen, nitrogen, silicon, iron. And when they died, they scattered these elements back into space. Over billions of years, the interstellar medium has become progressively enriched with heavier elements, so that stars forming today are composed of material that's been through multiple cycles of stellar birth, life, death, and rebirth. This means every atom in your body heavier than hydrogen was forged inside a star, in the nuclear furnace of a stellar core, and then scattered back into space when that star died. You are literally made of stardust, assembled from atoms that once belonged to stars that lived and died before the sun even formed. The stellar nurseries are where new stars, and eventually new planets, and perhaps new life, emerge from the recycled ashes of previous generations. A cosmic cycle of birth and death and rebirth that's been continuing for billions of years. The Milky Way isn't just a simple spiral galaxy. It's what's called a barred spiral galaxy, meaning it has a distinct bar-shaped structure of stars running through its center. This bar is made of stars and gas, roughly 27,000 light-years long, stretching out from either side of the central bulge like an elongated rugby ball, or peanut shape cutting through the galaxy's core. For a long time, we didn't know the Milky Way had a bar. it's difficult to detect from our position inside the galaxy, and the central regions are heavily obscured by dust. But infrared observations, which can penetrate that dust, revealed the bar's existence in the 1990s. Since then, studies have refined our understanding of its size, shape, and orientation. The bar rotates as a coherent structure, though not quite like a solid object. Stars near the ends move differently than stars near the center, creating a complex, dynamical pattern. Bars appear to be common in spiral galaxies. Roughly 2/3 of all spiral galaxies show some kind of bar structure. They form through gravitational instabilities in the disk, arising naturally from the interactions between stars and the gravitational field they collectively create. Once formed, bars are relatively stable structures that can persist for billions of years, though they can also dissolve if conditions change. The bar serves an important function in the galaxy's ecology. It acts like a conveyor belt, funneling gas from the outer regions toward the center. As gas moves along the bar, it loses angular momentum and spirals inward, eventually feeding star formation in the central regions and possibly feeding the supermassive black hole at the very center. This process helps regulate how gas is distributed throughout the galaxy and influences where and when new stars form. The spiral arms of the Milky Way extend from the ends of the bar, not from the central bulge directly. This gives the galaxy a distinctive structure when viewed from above. A central bar with spiral arms trailing off from its ends, like water spiraling away from a spinning lawn sprinkler. The sun orbits beyond the bar, out in the disk where the spiral arms dominate, but the bar's gravitational influence extends throughout the galaxy, affecting the orbits of stars even thousands of light years away. Interestingly, the bar may have formed relatively recently in cosmic terms, perhaps just a few billion years ago. Computer simulations suggest that galactic bars can form, dissolve, and reform over the lifetime of a galaxy, depending on factors like the amount of gas in the disk and the frequency of mergers with smaller galaxies. The Milky Way's bar might not be a permanent feature, but rather a phase in the galaxy's ongoing evolution, a transient structure that will eventually dissipate and perhaps reform again millions of years later. Living in a barred spiral galaxy versus a regular spiral doesn't change much for us. We're far enough from the bar that its direct influence is minimal, but it does affect the overall dynamics of the galaxy, the flow of gas and the formation of stars, and ultimately the environment in which we find ourselves. The bar is part of the Milky Way's character, a structural feature that makes our galaxy what it is, even if we can't see it directly from our suburban location halfway out in the disk. Between the stars lies the interstellar medium, a tenuous mix of gas and dust that fills the space in the galactic disk. It's almost empty by Earth standards, typically containing just one atom per cubic centimeter, compared to the roughly 1019 molecules in the same volume of air you're breathing. Yet across the vast distances of interstellar space, this near vacuum adds up to substantial mass, actually more mass than all the stars combined. The gas is mostly hydrogen and helium, the primordial elements left over from the Big Bang. But it also contains trace amounts of heavier elements: carbon, oxygen, nitrogen, silicon, iron, and dozens of others. These heavier elements were forged in stellar cores and scattered into space when stars died, gradually enriching the interstellar medium over billions of years. The very atoms that now drift between the stars were once inside stars, fused and processed, and then returned to the cosmic recycling stream. The interstellar medium isn't uniform. It has structure, temperature variations, density fluctuations. Some regions are cold and dense, giant molecular clouds where temperatures drop to just 10 or 20 degrees above absolute zero, and densities climb to thousands of particles per cubic centimeter. These are the stellar nurseries, where stars are born. Other regions are hot and diffuse, heated to millions of degrees by supernova shock waves or stellar winds, so thin that you might find only one particle in 100 cubic centimeters. Then there's the dust. Tiny solid particles, typically less than a micron across, made of carbon, silicon, and other elements. These dust grains scatter and absorb starlight, creating the dark lanes and patches visible in images of the Milky Way. They're also essential for planet formation, serving as the seeds around which larger objects can grow. The Earth began as dust grains in the solar nebula, gradually accumulating into pebbles, then boulders, then planetesimals, and eventually a full-sized planet. The interstellar medium is not static. It's constantly in motion, stirred by stellar winds, supernova explosions, the rotation of the galaxy, and magnetic fields threading through the disk. Gas flows from one region to another, cools and condenses to form stars, then gets heated and expelled back into space when those stars die. It's a dynamic system, a vast ecosystem of matter cycling through different states, diffuse to dense, cold to hot, gas to stars, and back to gas again. Traveling through the interstellar medium are cosmic rays, high-energy particles, mostly protons, accelerated to nearly the speed of light by supernova shock waves and other violent events. These particles zip through space, occasionally striking atoms in the interstellar medium or even reaching Earth's atmosphere, where they collide with air molecules and create showers of secondary particles. Cosmic rays are constantly bombarding Earth, though our atmosphere and magnetic field protect us from most of their effects. The interstellar medium also contains complex organic molecules, chains of carbon atoms bonded with hydrogen, oxygen, nitrogen, and other elements. Over 200 different molecules have been detected in interstellar space, including some surprisingly complex ones like amino acids and sugars, the building blocks of life. These molecules form on the surfaces of dust grains or in the gas phase, assembling themselves through chemical reactions driven by ultraviolet starlight or cosmic rays, when new stars form and planets coalesce around them. These organic molecules get incorporated into the planets, potentially seeding them with the raw materials for life. So the space between stars, which seems empty, is actually filled with a dilute but chemically rich medium, a vast reservoir of raw material waiting to be transformed into the next generation of stars, planets, and perhaps living things. We tend to focus on the stars, the bright points of light, but the darkness between them is just as important, just as full of potential, quietly waiting for gravity and chemistry to work their slow magic. The Milky Way's disk isn't perfectly flat, it's warped, like a vinyl record left too long in the sun. If you could view the galaxy edge-on from far away, you'd see the disk bending upward on one side and downward on the other, creating an S-shaped curve that extends throughout the outer regions of the galaxy. This warping is subtle near the center, but becomes more pronounced toward the edges, where the disk can deviate from the plane by thousands of light years. For decades, astronomers debated what causes this warp. Many galaxies show similar features, so it's probably a common phenomenon, but the exact mechanism wasn't clear. The leading explanation now is that the warp is caused by gravitational interactions with the Magellanic Clouds, two smaller galaxies that orbit the Milky Way. The Magellanic Clouds, particularly the Large Magellanic Cloud, are massive enough to exert significant gravitational torque on the Milky Way's disk, pulling it out of alignment and creating the warp we observe. Computer simulations support this idea. When you model the Milky Way with the Magellanic Clouds orbiting around it, the disk naturally develops a warp that matches what we see. The warp isn't static, it precesses, meaning the orientation of the S-curve slowly rotates over time, though on timescales of hundreds of millions of years. From our perspective, the warp is effectively frozen, but over cosmic time it's a dynamic feature, responding to the changing gravitational environment as the Magellanic Clouds orbit and the galaxy evolves. The warp also tells us something important. The Milky Way is not an isolated system. It's embedded in a gravitational environment shaped by nearby galaxies, dark matter structures, and the overall flow of matter on cosmological scales. Galaxies influence each other across vast distances, their gravity reaching out to tug and pull on their neighbors, creating tides and torques that shape galactic structure. This warping was detected gradually as astronomers mapped the three-dimensional distribution of stars and gas in the outer disk. It's most easily seen in hydrogen gas, which extends farther out than stars and clearly traces the warped structure. The Gaia spacecraft's precise measurements of stellar positions have also revealed the warp in unprecedented detail, showing not just the large-scale bend, but also smaller ripples and undulations superimposed on top of it. There's something almost organic about this. The Milky Way isn't a rigid structure, but a flexible one, capable of bending and flexing in response to external forces. It's more like a sheet of fabric or a membrane than a solid disk, responsive to gravitational pressures in ways that reveal its nature as a dynamic, evolving system rather than a fixed architecture. And we're inside this warped disk, orbiting along with it, our path through the galaxy slightly curved by the overall structure. The warp doesn't affect us much directly. The Sun's orbit is determined mostly by the galaxy's overall mass distribution, but it's part of the environment we inhabit, part of the shape of home. Orbiting the Milky Way like a swarm of bees around a hive are over 150 globular clusters, dense spherical collections of stars that formed early in the galaxy's history. Each cluster contains hundreds of thousands of stars, sometimes over 1 million, packed into a region just a few dozen light years across. The stars in a globular cluster are so densely concentrated that near the center, the distance between stars might be just a fraction of a light year, still vast by solar system standards, but remarkably close compared to the typical spacing of stars in the galactic disk. These clusters are ancient. Most globular clusters are between 10 and 13 billion years old, formed when the universe was young and the Milky Way was just beginning to take shape. They contain some of the oldest stars in the galaxy, survivors from an era when the universe was very different, hotter, denser, lacking in heavy elements. The stars in globular clusters are almost entirely composed of hydrogen and helium, with only trace amounts of heavier elements, reflecting their formation from the relatively pristine gas available in the early universe. Because globular clusters are so old, they contain no massive, short-lived stars. All the blue giants and supergiants that once existed in these clusters have long since died, leaving behind only the smaller, longer-lived stars, red dwarfs, sun-like stars, and red giants nearing the end of their lives. This gives globular clusters a distinctive appearance, a dense ball of yellowish or reddish stars, ancient and stable, slowly evolving on timescales of billions of years. The clusters orbit the Milky Way in elongated, eccentric paths that take them plunging through the galactic disk and back out into the halo. They don't orbit in the disk's plane. Instead, they follow orbits that are randomly oriented, creating a roughly spherical distribution around the galaxy. This spherical halo of globular clusters traces out the shape of the galaxy's gravitational well, the region dominated by the Milky Way's mass. Some globular clusters pass through the galactic disk periodically, creating brief, dramatic encounters as they traverse the denser environment. These passages can strip stars from the clusters through tidal forces, leaving streams of stars trailing behind the cluster in its orbit. Over billions of years, some clusters have been completely dissolved by these interactions, their stars scattered throughout the halo. Former members of a once coherent group, now lost in the general stellar population. Studying globular clusters tells us about the early history of the Milky Way. The chemical composition of their stars reveals what the interstellar medium was like billions of years ago. Their orbits carry information about past mergers and gravitational interactions. Some clusters might not have formed in the Milky Way at all, but were captured from smaller galaxies that merged with ours, immigrants carrying their own history into our galactic family. There's something poignant about these clusters, islands of ancient stars, survivors from the galaxy's youth, slowly orbiting through space on paths they've followed for billions of years. They've witnessed almost the entire history of the Milky Way, from its early chaotic assembly to its current mature structure, and they'll continue orbiting for billions more, until eventually the galaxy's evolution, or its eventual merger, with Andromeda changes their orbits or dissolves them entirely, releasing their stars into the larger cosmic population. Threaded through the Milky Way's halo are stellar streams, long, thin ribbons of stars stretching for thousands or even tens of thousands of light years. These streams are the shredded remains of smaller galaxies and star clusters that ventured too close to the Milky Way and were torn apart by tidal forces. As these smaller objects orbit the galaxy, the difference in gravitational pull between their near and far sides stretches them out, like taffy being pulled, until eventually they're completely disrupted and spread into a stream. The stars in these streams all move together, following similar orbits because they share a common origin. This makes them detectable, even though they're mixed in with all the other halo stars. By measuring the positions and velocities of millions of stars, something the Gaia spacecraft has made possible, astronomers can identify groups of stars that are moving coherently, revealing streams that would otherwise be invisible. One of the most famous stellar streams is the Sagittarius stream, created by the ongoing disruption of the Sagittarius dwarf elliptical galaxy. This small galaxy is currently in the process of being consumed by the Milky Way, and as it orbits, it's leaving behind a trail of stars that wraps around our galaxy multiple times. It's like watching a slow-motion collision, a smaller galaxy being gradually pulled apart and absorbed by a larger one, the process unfolding over hundreds of millions of years. Other streams come from disrupted globular clusters. These clusters, if they orbit too close to the galactic center or pass through the dense disk too many times, can be torn apart by tidal forces. The stars don't disappear. They remain in orbit around the galaxy, but they're no longer gravitationally bound to each other. They spread out along the cluster's former orbit, creating a stream that gradually disperses over cosmic time. These streams are like archaeological artifacts, preserving information about the Milky Way's past. Each stream represents a merger or disruption event, a moment when the galaxy consumed something smaller. By mapping the streams and measuring their properties, astronomers can reconstruct the history of these events, when they happened, what the original objects were like, how they contributed to the Milky Way's growth. The Milky Way is, in a sense, wearing the remains of its victims. The streams drape around the galaxy like ghostly ribbons, silent witnesses to billions of years of galactic cannibalism. They're beautiful in images, thin, delicate structures tracing graceful curves through the halo. But they're also reminders that galaxy formation is a violent process, driven by mergers and acquisitions, larger structures growing by consuming smaller ones. And this process is ongoing. The Milky Way is still consuming satellite galaxies. The Sagittarius dwarf won't survive much longer. In another billion years or so, it will be completely dissolved, its stars fully integrated into the Milky Way's halo. The Magellanic Clouds might meet a similar fate eventually, though they're larger and might take longer to consume. The galaxy is still growing, still evolving, still gathering matter from its surroundings and incorporating it into itself. We live inside a cosmic predator, a galaxy that has grown through consumption, and the stellar streams are the evidence of this process, the trails left behind by mergers past and present. They're beautiful and melancholy at the same time. Beautiful as structures, melancholy as tombstones, marking the end of smaller galaxies that no longer exist as independent entities. About 90% of the mass in the Milky Way is dark matter, mysterious, invisible material that doesn't interact with light or any other electromagnetic radiation. This means that everything you can see when you look at the galaxy, all the stars, all the gas and dust, all the visible structure, represents only about 10% of what's actually there. The other 90% is completely invisible, detectable only through its gravitational effects. This is a profound and somewhat unsettling fact. The universe we can see, the matter we're made of, the stuff that emits and absorbs light, all of it is a minority component. Most of the universe is made of something else, something we don't understand, something that refuses to reveal itself except through gravity. It's like discovering that your house is 90% filled with invisible furniture that you can only detect by bumping into it. The evidence for dark matter comes from multiple sources. Galactic rotation curves show that stars orbit faster than they should if only visible matter were present. Gravitational lensing, the bending of light by massive objects, reveals concentrations of mass where nothing visible exists. The cosmic microwave background, the afterglow of the Big Bang, contains patterns that require dark matter to explain. Computer simulations of cosmic structure formation only match reality if they include dark matter. All of these independent lines of evidence point to the same conclusion. There's a lot more matter out there than we can see. What is dark matter? We genuinely don't know. It's one of the biggest unsolved problems in physics. The leading hypothesis is that dark matter consists of exotic particles, perhaps WIMPs, weakly interacting massive particles, or axions or sterile neutrinos. These particles would have been created in the early universe and would still be around today, passing through ordinary matter with barely any interaction. Detecting them is incredibly difficult, and despite decades of experiments, we haven't definitively identified a dark matter particle yet. Some physicists have proposed alternatives to dark matter, suggesting instead that our theory of gravity needs modification on galactic scales. These modified gravity theories can explain galactic rotation curves without invoking invisible matter, but they struggle to explain other observations like gravitational lensing and the cosmic microwave background. Most physicists believe dark matter is real, but the debate continues. What we do know is that dark matter behaves like matter in the sense that it clumps together under gravity, forming a scaffolding on which visible matter accumulates. The Milky Way's dark matter halo provides the gravitational potential well in which the disk of stars and gas resides. Without dark matter, the galaxy wouldn't exist in its current form. The stars would fly off into space, and the galaxy would disperse into the intergalactic void. So we live inside an invisible ocean, a sea of dark matter particles that surrounds us, pervades us, and holds everything together. They're passing through you right now, billions of them every second, and you feel nothing. They don't interact with the atoms in your body, don't bounce off, don't leave any trace of their passage. They're ghosts, present but undetectable, the hidden majority of the universe making itself known only through the gravity it exerts on the visible minority we can actually observe. It's a humbling realization that most of what's out there remains mysterious, that we've mapped and cataloged the visible universe, but the majority of reality is still beyond our understanding. Dark matter is a reminder that the cosmos has depths we haven't plumbed, that for all our telescopes and theories, we're still largely in the dark about what the universe is really made of. The central bulge of the Milky Way, the concentration of stars around the galactic center, isn't a simple sphere. When viewed from certain angles, it's shaped more like a peanut or a box with a distinctive elongated structure. This unusual shape was discovered through infrared observations that could penetrate the dust obscuring the galactic center, revealing the three-dimensional distribution of stars in the bulge. The peanut shape is thought to be a consequence of the galactic bar. When a bar forms in a disk galaxy, it can create vertical instabilities, regions where stars get kicked out of the plane of the disk. These stars don't escape the galaxy. Instead, they oscillate above and below the disk in a pattern that creates the peanut or X-shaped structure visible from certain viewing angles. It's a dynamical sculpture, stars organized by gravity into an unexpected geometry. This shape tells us that the Milky Way's center is more complex than a simple collection of old stars orbiting the supermassive black hole. There's structure here, patterns created by billions of years of gravitational interactions, the bar influencing how stars move and creating vertical resonances that organize them into this unusual configuration. The bulge is also older and more metal-poor than the disk on average. It formed early in the galaxy's history, when the Milky Way was still coalescing from smaller fragments. The stars there have seen nearly the entire history of the galaxy, orbiting the center for billions of years in this densely packed environment. Some might have been captured from smaller galaxies that merged with the Milky Way long ago, immigrants from structures that no longer exist. The peanut shape is somewhat transient. It depends on the bar, and if the bar eventually dissolves or reforms, the bulge's shape might change. The Milky Way's structure is not fixed for all time, but evolves, responding to changes in the distribution of mass and the ongoing dynamics of stellar orbits. What we see now is a snapshot of the galaxy at this particular moment in its long history, a shape that might look different a few billion years from now. Within the Milky Way, astronomers estimate there are about 10 billion Earth-like planets orbiting in the habitable zones of their stars, regions where temperatures are right for liquid water to exist on a planet's surface. This estimate comes from data gathered by the Kepler Space Telescope and other planet-hunting missions, which have revealed that planets are extremely common and that rocky planets orbiting at the right distance from their stars are not rare exceptions, but frequent outcomes of planet formation. 10 billion. That's a staggering number of potential cradles for life, worlds where conditions might be similar enough to Earth that life could emerge, evolve, and perhaps develop into something complex, maybe even intelligent. Each one is a possibility, a place where the chemistry of life might unfold, where oceans might teem with strange organisms, where evolution might produce its own unique solutions to the challenges of existence. Of course, being in the habitable zone doesn't guarantee life. A planet also needs the right atmosphere, the right chemistry, geological activity to recycle nutrients, protection from excessive radiation, and probably dozens of other factors we haven't fully identified yet. Many of these 10 billion planets might be lifeless deserts, or frozen wastelands, or sweltering greenhouses, despite being in the nominal habitable zone. But even if only a tiny fraction harbor life, say 1 in 1,000, that's still 10 million living worlds in our galaxy alone. We haven't found life on any of them yet. We've barely begun to look, and detecting life on a planet orbiting another star is extraordinarily difficult with current technology. We can detect planets, measure their sizes and orbits, and in some cases analyze their atmospheres for signs of gases that might indicate biological activity. But we're still in the early stages of this search, and it might take decades or longer before we find definitive evidence of life beyond Earth. The existence of so many potentially habitable planets raises profound questions. Are we alone in the galaxy? If not, why haven't we detected any signals from other civilizations? This is the Fermi paradox. If the galaxy is full of habitable planets and life is reasonably common, we should see some evidence of it by now. The silence suggests either that technological civilizations are extraordinarily rare, or they don't last long, or they're quiet and don't broadcast their presence, or we're looking in the wrong ways. Whatever the answer, the galaxy offers an ocean of possibilities. 10 billion worlds where the dice have been rolled, where chemistry has had billions of years to work, where evolution might have produced outcomes we can't imagine. Some might be Edens, some might be hells, some might be utterly alien environments we'd never recognize as potentially habitable. And we're orbiting one of them, one planet among billions, asking the ancient question, are we alone? The answer is out there, written in the atmospheres of distant worlds, waiting for us to develop the technology to read it. For now, we can only estimate, calculate probabilities, and wonder. But the sheer number of possibilities, 10 billion planets, each one a chance for life to emerge, suggests that the Milky Way might be far more alive than we ever imagined. A galaxy not just of stars and gas and dark matter, but of living worlds, scattered like seeds across the vast garden of space. The Milky Way doesn't travel through space alone. It's accompanied by at least 50 smaller satellite galaxies, dwarf galaxies that orbit our galaxy like moons orbiting a planet. These satellites range in size from a few billion stars down to just a few thousand, tiny compared to the Milky Way's hundreds of billions, but still gravitationally bound systems in their own right. The most famous satellite galaxies are the Large and Small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light that look like detached pieces of the Milky Way. These are irregular dwarf galaxies containing billions of stars and still actively forming new ones. They're close enough and large enough to be visible to the naked eye, and they've been known to indigenous peoples of the southern hemisphere for tens of thousands of years. Most of the other satellites are much smaller and fainter, dwarf spheroidal galaxies or ultra-faint dwarfs, some containing so few stars that they're barely distinguishable from globular clusters. These tiny galaxies are dominated by dark matter. In some cases, dark matter outweighs visible matter by a factor of 100 or more. They're held together primarily by invisible mass, their few stars scattered through a dark matter halo much larger than the visible galaxy. Discovering these faint satellites requires deep surveys of the sky, looking for slight overdensities of stars that move together, indicating they're part of a gravitationally bound system. The Sloan Digital Sky Survey and other projects have discovered dozens of previously unknown dwarf galaxies orbiting the Milky Way. And there are probably more waiting to be found, perhaps hundreds of ultra-faint dwarfs hiding in the halo, too dim to have been detected yet. These satellite galaxies are important for understanding galaxy formation. According to cosmological simulations, large galaxies like the Milky Way should be surrounded by hundreds or thousands of smaller dark matter halos left over from the hierarchical assembly process that builds galaxies. Many of these halos apparently don't contain visible galaxies. They're just dark matter with no stars. The satellites we can see might be the tip of the iceberg, the brightest and largest examples of a much larger population of dark matter substructures. The satellites are also being gradually consumed by the Milky Way. Tidal forces strip stars from them as they orbit, feeding streams of stars into the galactic halo. Eventually, many of these dwarfs will be completely dissolved, their stars added to the Milky Way's population, their dark matter halos absorbed into the larger dark matter halo. This is how large galaxies grow, by cannibalizing smaller ones, a slow process of galactic amalgamation that's been ongoing for billions of years. The satellite galaxies are our cosmic neighbors, companions on a long journey through space. They're bound to us by gravity, orbiting the Milky Way just as we orbit the galactic center. All of us part of a larger structure held together by invisible forces. They're smaller, fainter, less impressive perhaps than our galaxy, but they're family nonetheless, fellow travelers in the local corner of the universe. About 1% of the Milky Way's mass is dust, tiny solid particles, typically less than a micron across, made of carbon, silicon, oxygen, and other elements. This might not sound like much, but across a galaxy containing trillions of solar masses, 1% is a substantial amount of material. This dust pervades the galactic disk, scattered between the stars, absorbing and scattering starlight, creating the dark lanes and patches visible in images of the Milky Way. Dust grains form in several ways. Some condense in the atmospheres of cool red giant stars, where temperatures drop low enough for molecules to stick together and build up solid particles. When these stars shed their outer layers, they release these dust grains into space. Other dust forms in the expanding debris of supernovae, where heavy elements created in the explosion cool and condense into solid form. Over billions of years, these processes have gradually enriched the interstellar medium with dust, coating the galaxy in cosmic soot. These grains are not just debris, they're essential players in the chemistry of space. On the surfaces of dust grains, molecules can form that wouldn't easily form in the gas phase. The grain provides a surface where atoms can meet and stick, giving them time to react and form molecular bonds. Complex organic molecules, including some of the building blocks of life, form this way, assembled on the frozen surfaces of dust grains, drifting through molecular clouds. Dust grains also serve as the seeds for planet formation. In the disk of gas and dust surrounding a young star, grains collide and stick together, gradually growing into larger particles, pebbles, boulders, planetesimals, and eventually planets. The Earth began as dust, as did every rocky planet and moon in the solar system. The dust in the early solar nebula, itself inherited from the interstellar medium, contained all the elements needed to build worlds: silicon for rocks, iron for cores, carbon and water and organic molecules for atmospheres and oceans and life. But dust is also a nuisance for astronomers because it obscures our view of the galaxy. Light from stars behind dust clouds gets absorbed or scattered, making those regions appear dark in optical images. The galactic center, heavily obscured by intervening dust, is almost invisible in visible light. To see through the dust, astronomers use longer wavelengths, infrared and radio, which pass through dust more easily, revealing structures hidden from optical telescopes. The dust isn't uniformly distributed. It's concentrated in the galactic disk, particularly in spiral arms where gas and dust accumulate. It's thicker in some directions and thinner in others, creating the patchy, mottled appearance of the Milky Way, as seen from Earth. Where dust is thick, the Milky Way appears dark and obscured. Where it's thin or absent, we can see deeper into the galaxy, glimpsing more distant stars. So this 1% of cosmic dust shapes our experience of the galaxy in profound ways. It obscures some regions while revealing others. It facilitates the chemistry that produces complex molecules. It provides the raw material for planets. It's the soot and ash of dead stars, recycled into new structures, a reminder that nothing in the galaxy is permanent. everything cycles through different forms, from stars to dust to stars again. An endless process of transformation driven by gravity, nuclear fusion, and the slow chemistry of space. The Milky Way formed from a collapsing cloud of hydrogen and helium left over from the Big Bang, primordial gas that had been drifting through space for perhaps 200 million years after the universe began. This gas was almost entirely hydrogen and helium, the only elements created in significant quantities during the first few minutes of the universe's existence. There was no carbon, no oxygen, no iron, no silicon. Just the two lightest elements, simple atoms floating in the darkness, slowly being pulled together by gravity. As the gas cloud collapsed, it began to fragment. Different regions fell inward at different rates, creating clumps and overdensities. Some of these clumps became the first stars, massive and short-lived, burning through their fuel quickly and exploding as supernovae. These explosions scattered the first heavy elements into the surrounding gas: carbon and oxygen from the star's cores, iron and nickel from the supernova itself. Gradually, the interstellar medium became enriched with elements heavier than helium, though it would take billions of years for this enrichment to reach current levels. The early Milky Way didn't look like it does today. It was smaller, more chaotic, less organized. There was no clear disk, no spiral structure, just a turbulent collection of gas clouds, young stars, and the remnants of the first supernovae. The galaxy grew by accreting more gas from its surroundings and by merging with smaller protogalaxies, fragments of the cosmic web that were falling together under gravity's relentless pull. Over time, the gas settled into a rotating disk. Conservation of angular momentum, the tendency for rotating systems to spin faster as they contract, caused the collapsing cloud to flatten, just as a pizza dough flattens when spun in the air. Material that wasn't rotating with the general flow either fell to the center or was ejected. What remained organized itself into the disk we see today, a flat structure where most of the star formation now occurs. This process took billions of years. The Milky Way wasn't built in a moment, but assembled piece by piece, merger by merger, star by star. The oldest stars in the halo formed early, when the galaxy was still a chaotic proto-structure. The disk stars formed later, once the gas had settled into a coherent rotating system. The Sun, born 4.5 billion years ago, is a relative latecomer, formed when the galaxy was already more than 9 billion years old and well into its mature phase. Everything you see in the galaxy today, every star, every planet, every nebula, condensed from that initial cloud of primordial gas, organized by gravity into increasingly complex structures. The atoms that make up your body were once part of that cloud, drifting freely through space. Gravity brought them together, first into the Milky Way, then into the solar nebula, then into the Earth, and eventually into the molecules that compose living things. You are, in a very literal sense, the Milky Way contemplating itself, primordial gas organized by 13.6 billion years of cosmic evolution into something capable of wondering about its own origins. The oldest stars in the Milky Way are nearly as old as the universe itself, born around 13 billion years ago, when the galaxy was just beginning to form. These ancient stars are found primarily in the halo and in globular clusters, relics from an earlier epoch when the cosmos was very different from what it is today. These stars are metal poor, meaning they contain very few elements heavier than helium. Astronomers use metal to refer to any element heavier than helium, a quirk of terminology that can be confusing but makes sense in context. Hydrogen and helium were created in the Big Bang, while everything else was made in stars. A metal-poor star is one formed from gas that hadn't been enriched much by previous generations of stars, gas that was still relatively pristine. The most metal-poor stars we've found contain only about 1/10,000th the heavy element content of the Sun. This tells us they formed very early, from gas that had been enriched by only a few supernovae. They're living fossils, their chemical composition preserving information about the early universe that's been erased elsewhere. By studying these stars, measuring their abundances of different elements, their ages, their motions, astronomers can reconstruct what the early Milky Way was like. These old stars are small and dim, mostly. Massive stars burn through their fuel quickly and die young, so any massive stars that formed 13 billion years ago are long gone, exploded as supernovae billions of years before the Sun even formed. What remains are the low-mass stars, the ones that burn their fuel slowly and can survive for 10, 20, even 100 billion years. They're still here, quietly orbiting, witnesses to nearly the entire history of the galaxy. Some of these stars have complex orbital paths that take them far from the galactic plane, out into the halo and back again. These orbits suggest they formed before the disk fully settled, when the proto-galaxy was still a chaotic cloud without clear structure. As the disk formed and most of the gas settled into a rotating plane, these stars retained their random, high-velocity orbits, fossils of the galaxy's violent youth preserved in their motion. Finding these ancient stars requires dedicated searches. They're faint, scattered throughout the halo, easily lost among the billions of younger, more typical stars. But projects like the Hamburg ESO survey and the Pristine survey have identified thousands of metal-poor candidates, and spectroscopic follow-up can determine their detailed compositions and ages. Each discovery adds a piece to the puzzle of how the Milky Way formed and evolved. These stars have witnessed almost everything. They were here when the first spiral arms formed. They saw the Milky Way collide with and consume dozens of smaller galaxies. They watched as the interstellar medium gradually became enriched with heavy elements, as each generation of stars added its contribution to the cosmic recycling stream. They orbited through the halo while the Sun formed, while the Earth cooled, while life emerged and evolved. And they're still here, still shining, carrying in their atmospheres the chemical fingerprints of the early universe, patiently waiting for us to study them and learn their secrets. The Milky Way didn't form in isolation. It grew by merging with and consuming smaller galaxies over billions of years. This is the standard model of galaxy formation. Large galaxies build up hierarchically, starting as small fragments in the early universe and gradually merging to form larger and larger structures. The Milky Way is the product of countless such mergers, an amalgamation of what were once independent galaxies, now blended into a single system. Evidence for this merger history is written throughout the galaxy. Stellar streams in the halo trace the disrupted remains of smaller galaxies, their stars stretched into long ribbons by tidal forces. Chemical signatures in halo stars reveal their diverse origins. Some formed in the proto-Milky Way, others in smaller galaxies that were later absorbed. The kinematics of stars, their velocities and orbital patterns, show groups moving together in ways that suggest they share a common origin in a merged satellite. Not all mergers are equal. Small mergers, where the Milky Way absorbs a dwarf galaxy containing a few billion stars or less, happen relatively frequently and don't dramatically alter the galaxy's structure. The smaller galaxy gets shredded, its stars added to the halo, its dark matter absorbed into the Milky Way's larger dark matter halo. The process is slow and relatively gentle, a gradual consumption rather than a violent collision, but occasionally larger mergers occur. About 10 billion years ago, the Milky Way collided with a galaxy called Gaia Enceladus, which contained roughly 600 million stars, a significant fraction of the Milky Way's mass at the time. This collision was violent enough to heat the galactic disk, puffing it up and disrupting its structure. Stars from Gaia Enceladus now make up a significant portion of the inner halo, identifiable by their chemical composition and orbital properties. This was a transformative event in the Milky Way's history, one of the most significant mergers in the past several billion years. And the merger process continues. The Sagittarius dwarf elliptical galaxy is currently being torn apart as it orbits through the Milky Way. Each time it passes through the disk, tidal forces strip away more of its stars, feeding them into streams that wrap around the galaxy. In another billion years or so, Sagittarius will cease to exist as a separate entity, fully absorbed into the Milky Way. The Magellanic Clouds may face a similar fate. These two satellite galaxies are the largest companions of the Milky Way, and while they're currently in orbit around our galaxy, their ultimate fate is uncertain. Some models suggest they'll eventually merge with the Milky Way, though this might take several billion years. If and when it happens, it will be another significant merger, adding billions of stars to the galactic population and triggering new bursts of star formation as gas from the clouds gets compressed and collapses. This process of growth through mergers is common to all large galaxies. The universe's structure formed hierarchically, with small objects merging to form larger ones in a cosmic tree of assembly. The Milky Way is a branch on that tree, formed from the union of countless smaller branches, each with its own history, now blended into the galaxy we inhabit. We're living inside the product of billions of years of galactic cannibalism, a composite structure built from the remains of galaxies that no longer exist as independent entities. About 10 billion years ago, when the universe was less than a quarter of its current age, the Milky Way experienced one of its most significant collisions. A galaxy now called Gaia Enceladus, containing roughly 600 million stars, crashed into our galaxy in a merger so violent it fundamentally changed the Milky Way's structure and evolution. This ancient collision wasn't directly observed, of course. It happened billions of years before the Sun even formed. But its effects are still visible today, written in the chemistry and motions of stars in the galactic halo. The discovery came from analyzing data from the Gaia spacecraft, which measured the positions and velocities of over 1 billion stars with unprecedented precision. When astronomers looked at how these stars were moving, they found a population in the halo with unusual kinematics. Stars moving in similar directions, as if they shared a common origin. Further analysis revealed that these stars also had distinctive chemical compositions, different from typical Milky Way halo stars. They were more metal-rich than you'd expect for their age, suggesting they formed in a separate galaxy with its own enrichment history. By tracing back their orbits and studying their properties, astronomers reconstructed what must have happened. A separate galaxy, roughly 1/4 the mass of the Milky Way at the time, fell inward and merged with our galaxy. The collision wasn't a gentle absorption, but a dramatic crash. When Gaia Enceladus plunged through the Milky Way's disk, it pumped enormous amounts of energy into the system, heating the disk and causing it to puff up. Stars that had been in orderly circular orbits were scattered into more chaotic, eccentric paths. The disk, which had been thin and well organized, became thicker and more turbulent. It took billions of years for the system to settle back down into the structured disk we see today. The stars from Gaia Enceladus now make up a significant fraction of the inner halo, perhaps 1/3 of all the stars in that region. They're thoroughly mixed with the Milky Way's population now. You can't look up and point to a specific star and say, that one came from Gaia Enceladus. But statistically, as a population, they're identifiable by their shared motion and chemistry. Ghosts of a galaxy that no longer exists, absorbed into the larger structure of the Milky Way. This collision was probably the last major merger the Milky Way experienced. There have been smaller mergers since then, dwarf galaxies absorbed and disrupted, but nothing on the scale of Gaia Enceladus. That collision represents a kind of boundary in the galaxy's history. Before it, the Milky Way was still being assembled from major building blocks. After it, the growth has been primarily through smaller accretion events, a slower and more gradual accumulation of mass. Studying this ancient collision helps us understand how galaxies form and evolve. The Milky Way didn't spring into existence fully formed. It was built up piece by piece through mergers that each left their mark on the galaxy's structure and stellar populations. Gaia Enceladus is the clearest example we found of this process, a fossil record of a collision preserved in the stars, waiting billions of years for us to discover it and read the story it tells about our galaxy's violent past. New stars are still being born in the Milky Way, emerging from collapsing gas clouds at a rate of about 1 to 2 solar masses per year. This might not sound like much, just 1 or 2 sun-like stars annually, but over millions of years, it adds up to significant numbers. The galaxy is continuously refreshing itself with new light, replacing stars that die with new ones, just beginning their lives. Star formation occurs primarily in the spiral arms, where gas and dust are compressed by density waves into denser clouds that can collapse under their own gravity. These regions light up in images as glowing nebulae: the Orion Nebula, the Eagle Nebula, the Carina Nebula, showcasing sites where stars are actively forming right now, in real time, the process unfolding over thousands to millions of years. The process begins when a region of a molecular cloud becomes dense enough that gravity overcomes the internal pressure resisting collapse. This can be triggered by various mechanisms: a passing density wave compressing the gas, a nearby supernova sending a shock wave through the cloud, or simply the gradual accumulation of mass until the cloud becomes unstable. Once collapse begins, the region fragments into smaller clumps, each one becoming a protostar. As the protostar contracts, it heats up, and eventually its core temperature reaches about 10 million degrees Kelvin, hot enough for nuclear fusion to ignite. Hydrogen atoms begin fusing into helium, releasing energy that halts the collapse and establishes hydrostatic equilibrium. The protostar becomes a main sequence star, beginning a stable phase that will last for millions to billions of years, depending on its mass. Not all collapsing gas forms stars. Much of it gets blown away by stellar winds and radiation from newly formed massive stars, or dispersed by supernova explosions. Star formation is an inefficient process. Only a small fraction of the available gas actually ends up in stars. The rest gets recycled back into the interstellar medium, waiting for another chance to collapse and try again. The rate of star formation in the Milky Way has varied over cosmic time. It was higher in the past, when the galaxy had more gas available and was experiencing more turbulent conditions from mergers. The current rate of 1 to 2 solar masses per year is relatively modest, a sign that the Milky Way is a mature galaxy settling into middle age. There's still gas available for star formation, and the process will continue for billions of years. But the frantic pace of the early galaxy has slowed to a steadier, more measured rhythm. Each new star is a fresh start, a new nuclear furnace igniting in the darkness. Another point of light added to the galaxy's vast population. Some of these stars will be like the Sun, stable, long-lived, perhaps orbited by planets where life might emerge. Others will be massive blue giants, burning bright and dying young in spectacular supernovae. Still others will be dim red dwarfs, so faint they're invisible to the naked eye, but so long-lived they'll still be shining trillions of years from now, long after the sun has died. The galaxy is alive with creation, a cosmic nursery where the raw materials of gas and dust are continuously being transformed into new stars, new solar systems, new possibilities, and this process shows no sign of stopping anytime soon. The Milky Way still has fuel for billions more years of star formation, ensuring that the galaxy's light will continue to shine far into the future. The chemical composition of stars reveals their age, a cosmic clock written in the elements they contain. Older stars have fewer heavy elements because those elements hadn't been created yet when the stars formed. Each generation of stars enriches the galaxy with heavier elements, gradually changing the composition of the interstellar medium and altering the chemistry of stars formed later. This process is called chemical evolution, and it's driven by stellar nucleosynthesis, the fusion reactions in stellar cores that create heavier elements from lighter ones. Hydrogen fuses into helium, helium into carbon and oxygen, and in the cores of massive stars, fusion continues up the periodic table, creating elements as heavy as iron. Elements heavier than iron are created in supernova explosions, where the intense energy and neutron flux allow rapid nuclear reactions that build up the heaviest elements. When a star dies, it returns much of its material to the interstellar medium. Low-mass stars like the Sun shed their outer layers gently as planetary nebulae, enriching the surrounding space with helium, carbon, and nitrogen. Massive stars explode as supernovae, violently ejecting their fusion products, oxygen, neon, silicon, iron, and heavier elements, into the galaxy. This material mixes with the existing gas, raising its metallicity, the fraction of elements heavier than helium. The next generation of stars forms from this enriched gas, so they contain more heavy elements than their predecessors. Over billions of years, the average metallicity of the galaxy has steadily increased. The first stars were almost pure hydrogen and helium. Stars forming today, like the Sun, contain about 2% heavy elements by mass, a small fraction, but vastly more than the early universe provided. This chemical fingerprint allows astronomers to age-date stars. By measuring the abundances of different elements in a star's atmosphere, they can estimate when it formed. Low metallicity stars are old, formed from relatively pristine gas. High metallicity stars are younger, formed from gas that's been through multiple cycles of stellar processing. It's not a perfect clock. Other factors affect stellar composition, but it's a useful guide to understanding galactic history. The Sun's metallicity tells us it's a third-generation star, at least. The gas that formed the solar nebula had been through multiple cycles of star formation and death before it collapsed to form our solar system. The iron in Earth's core, the oxygen you breathe, the calcium in your bones, all of it was forged in stars that lived and died before the sun existed. Their ashes recycled into new structures, eventually finding their way into planets and life. This cosmic alchemy, stars transforming light elements into heavy ones, generation by generation, is how the universe built up the periodic table. Everything heavier than lithium was made in stars or in stellar explosions, scattered into space and incorporated into later generations. You are, quite literally, made of stardust and supernova ash, assembled from atoms that were forged in stellar cores billions of years ago and recycled through the galactic ecosystem until they ended up here, arranged into patterns capable of contemplating their own origin. The Milky Way is in its middle age, roughly 13.6 billion years old, in a universe that's 13.8 billion years old. It's been around for nearly the entire history of the cosmos, but it's not done yet. It has perhaps another 5 billion years of active star formation ahead, maybe more, before it begins to fade into old age. This middle age is characterized by a kind of stability the galaxy didn't have in its youth. The major mergers that shaped its early evolution are mostly complete. The disk has settled into a coherent, rotating structure. Star formation continues, but at a modest pace, not the frantic rate of the early galaxy when gas was abundant and conditions were more turbulent. The Milky Way has reached a mature configuration, still evolving but more gradually, more predictably. But this stability is temporary, at least on cosmic timescales. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy, our nearest large galactic neighbor. This collision will be a transformative event, mixing the stars from both galaxies, triggering intense bursts of star formation as gas clouds collide and compress, and eventually merging the two galaxies into a single, larger elliptical galaxy. Until then, though, the Milky Way will continue its current pattern of evolution. Stars will form in the spiral arms, live their lives, and die, some gently and some explosively. The interstellar medium will continue to be enriched with heavy elements. Smaller satellite galaxies will be absorbed and disrupted. The supermassive black hole at the center will continue consuming gas, and occasionally flaring as material falls into it. These processes are all ongoing, part of the galaxy's normal metabolism. The Sun at 4.5 billion years old is roughly a third the age of the galaxy, middle-aged itself, in a middle-aged galaxy. It formed when the Milky Way was already well into its mature phase, long after the chaotic early epoch of assembly and major mergers. The solar system's entire history, from formation to now, including the emergence and evolution of life on Earth, has occurred during the galaxy's stable middle age, a period of relative calm compared to what came before and what will come after. This is a good time to be alive in the galaxy, perhaps. Not so early that heavy elements were scarce and planets might not form easily. Not so late that star formation has ceased and the galaxy is fading. We exist in a sweet spot, temporally, a period when the galaxy is mature enough to have interesting structure and chemistry, but young enough to still be vibrant and active. It's the cosmic equivalent of a pleasant autumn afternoon, after the heat of summer, but before the deep cold of winter, a moment of equilibrium before change comes again. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy. This isn't speculation or a remote possibility. It's a certainty, written in the current motions of the two galaxies as they fall toward each other under mutual gravitational attraction. Andromeda is currently about 2.5 million light-years away and approaching at roughly 110 kilometers per second. At this rate, the collision is inevitable, though the exact timing and details depend on factors like the galaxy's dark matter distributions and their current velocities. This collision will be spectacular, at least from an outside perspective. The two galaxies will approach, their gravitational fields beginning to distort each other's structures even before they make direct contact. Tidal forces will pull out long streamers of stars, creating bridges and tails connecting the two systems. As they interpenetrate, the spiral arms will become disrupted, the ordered structure dissolving into chaos. But despite the drama on galactic scales, individual stars will almost never collide. Space is mostly empty, and the distances between stars are so vast that even when two galaxies merge, the stars pass through each other like ghosts. A typical star has a diameter of about 1 million kilometers, but the distance to its nearest neighbor is measured in light years, trillions of kilometers. The odds of any two stars actually hitting each other during the merger are astronomically small. What will collide are the gas clouds. When clouds of interstellar gas from the two galaxies meet, they do interact. They compress each other, shock, heat up, and in many cases collapse to form new stars. The collision will trigger an intense starburst, a period of rapid star formation as gas is compressed throughout the merging system. The night sky of any surviving planets will become spectacular, filled with newly forming stars and the glowing nebulae that mark their birth sites. The merger will take several billion years to complete. The two galaxies will pass through each other, then fall back together, pass through again, gradually losing energy to dynamical friction until they finally settle into a single, merged system. The result will be an elliptical galaxy, a roughly spherical collection of stars without the clear disk and spiral structure both galaxies currently possess. Astronomers have already given this future galaxy a name, Milky, a portmanteau of Milky Way and Andromeda. By the time this happens, the Sun will be nearing the end of its life. In about 5 billion years, the Sun will evolve into a red giant, swelling up to perhaps engulf the inner planets, including possibly Earth. The collision with Andromeda and the Sun's death are on similar timescales, both transformative events in the far future of this region of space. Life on Earth, if it still exists, will have long since needed to adapt to changing conditions or migrate elsewhere. But the collision itself won't be dangerous to any surviving planets. The solar system will simply find itself in a different galaxy, orbiting through a larger elliptical structure instead of a spiral disk. The night sky will look different. No more Milky Way band, replaced by a more uniform distribution of stars. The sun might be flung into a different part of the merged galaxy, or it might remain in a similar orbit. The details are unpredictable, dependent on too many chaotic factors to forecast precisely. When the Milky Way and Andromeda finally merge, completing their billions of years-long collision, the result will be an elliptical galaxy that astronomers have already nicknamed Milky. This future galaxy will be very different from the spiral structures we currently inhabit. Larger, more massive, and with a fundamentally different shape and stellar population. Elliptical galaxies are roughly spherical or football-shaped collections of stars without the clear disk and spiral arms that characterize galaxies like the Milky Way and Andromeda. The stars in elliptical galaxies move in random orbits rather than the orderly, circular paths typical of disk galaxies. Some stars orbit one way, some another. Some plunge through the center and back out, creating a chaotic but stable configuration held together by the galaxy's overall gravitational field. The formation of Milky will erase the spiral structure of both progenitor galaxies. The orderly rotation of the disks will be disrupted by gravitational interactions during the merger, converting the organized motion into random, stellar velocities. The spiral arms, which were density waves moving through the disk, will dissolve as the disk itself is disrupted and mixed. What emerges will be a new structure, assembled from the pieces of both galaxies, but resembling neither. Most of the gas in both galaxies will be consumed in the starburst triggered by the collision. Gas clouds will collide, compress, and form stars at a rapid rate, using up the raw material that would otherwise have fueled star formation over billions of years. After this burst of activity, Milky will have little gas left, and star formation will largely cease. The galaxy will become red and dead, dominated by old red stars, with few young blue ones to provide fresh light. This is the typical fate of large galaxies in the universe. Many of the elliptical galaxies we see today probably formed through mergers, and they're mostly old stellar populations with little ongoing star formation. The Milky Way and Andromeda are currently vibrant, star-forming spirals, but their destiny is to become a quiescent elliptical, quietly aging as its stars slowly burn through their fuel with no new generation to replace them. The supermassive black holes at the centers of both galaxies, Sagittarius A in the Milky Way and the similar mass black hole in Andromeda, will eventually merge as well, creating a single, more massive black hole at the center of Milky. This merger will release gravitational waves, ripples in space-time, that will propagate outward at the speed of light, though by the time this happens, there likely won't be any technological civilizations nearby to detect them. Milky will be the dominant galaxy in the local group, having absorbed both of its largest members. The smaller satellite galaxies, the Magellanic Clouds, the Triangulum Galaxy, and various dwarf galaxies may also be absorbed during or after the merger, adding their stars to the mix. The final mass of Milky will be roughly the sum of its components, perhaps 1 trillion solar masses or more, making it one of the larger galaxies in the local universe. And all of this, the collision, the merger, the transformation into an elliptical, will unfold over billions of years, timescales so vast that they dwarf all of human history. It's the far future of our galactic home, written in gravitational inevitability, a destiny we can predict but will never witness. Sagittarius A, the supermassive black hole at the center of the Milky Way, is remarkably quiet for an object of its size. It's consuming material slowly, gently, accreting gas at a modest rate, and radiating relatively little energy. This quiescence is actually unusual. Many supermassive black holes at the centers of other galaxies blaze brightly as quasars, actively devouring gas and stars and radiating energy that outshines their entire host galaxy. But Sagittarius A is nearly dormant, sipping its fuel rather than gorging. This wasn't always the case. Evidence suggests that Sagittarius A was once much more active, perhaps as recently as a few million years ago. The Fermi bubbles, enormous lobes of high-energy gas extending thousands of light years above and below the galactic plane, might have been created by a period of intense activity when the black hole consumed a large amount of material and blasted out jets of energy in the process. If so, the black hole has since quieted down, and what we see now is a rest state, a lull between feeding episodes. The black hole does still consume material occasionally. There's a thin disk of hot gas orbiting it, accreting slowly onto the event horizon. Every so often, something larger, a gas cloud, an asteroid, maybe even a star that wandered too close, gets torn apart by tidal forces and fed into the black hole. When this happens, Sagittarius A flares, brightening temporarily in X-rays as the infalling material heats up and radiates before disappearing forever beyond the event horizon. These flares have been observed multiple times. They're brief, lasting hours to days, and they increase the black hole's luminosity by factors of tens or hundreds. But even during a flare, Sagittarius A is faint compared to active galactic nuclei in other galaxies. It's a gentle giant, massive but not particularly violent, holding court at the galactic center without demanding much attention. Why is it so quiet? Probably because there's not much material nearby to consume. The region around the black hole has been largely cleared out. Any gas or stars that were in unstable orbits have already been accreted or ejected. What remains is a stable population of stars in more distant orbits, safe from the black hole's immediate grasp, and a very low density of gas that trickles in slowly rather than flooding inward. This quiescence is probably typical for supermassive black holes in mature galaxies. When galaxies were younger and had more gas, or when they experienced mergers that funneled gas toward their centers, the central black holes were more active. But in a stable, middle-aged galaxy like the Milky Way, the black hole has largely exhausted its nearby fuel and settles into a low-activity state, occasionally stirring when something falls too close, but otherwise sitting quietly at the center. A sleeping giant holding the galaxy together with its gravity, but otherwise mostly dormant. The metallicity of stars, their content of elements heavier than helium, gradually increases over cosmic time, creating a kind of chemical timeline that traces the history of the galaxy. This progression happens because each generation of stars enriches the interstellar medium with the heavy elements it creates through nuclear fusion, leaving the gas slightly more metal-rich for the next generation to form from. The very first stars in the universe, called Population 3 stars, were made of almost pure hydrogen and helium, the only elements created in significant quantities during the Big Bang. These stars have never been directly observed because they all died billions of years ago, but we know they must have existed. They would have been massive, short-lived, and when they exploded as supernovae, they scattered the first heavy elements into the cosmos: carbon, oxygen, silicon, iron, elements that had never existed before. The next generation, population 2 stars, formed from gas that had been enriched by these first supernovae. They contained small amounts of heavy elements, perhaps 1,000th or 1/10,000th the metallicity of the Sun. Many of these stars still exist today, particularly in globular clusters and the galactic halo, ancient survivors from the early universe. Their low metallicity is a signature of their age, a chemical fossil record of a time when the galaxy was young and heavy elements were scarce. Population Y stars, like the Sun, formed more recently from gas that had been through multiple cycles of stellar processing. They have relatively high metallicity. About 2% of the Sun's mass consists of elements heavier than helium. This enrichment came from countless previous generations of stars, each one contributing its fusion products to the galactic recycling stream, gradually building up the periodic table one supernova at a time. This chemical evolution affects planet formation. The first stars couldn't have rocky planets like Earth because there weren't enough heavy elements to build them from. Rocky planets require silicon, iron, oxygen, magnesium, elements that simply didn't exist in significant quantities in the early universe. Only after several generations of stars had lived and died, enriching the galaxy with heavy elements, could rocky planets form. The Sun's relatively high metallicity is one reason the solar system has so many rocky objects: 4 rocky planets, numerous asteroids, rocky moons. The solar nebula from which these objects formed contained enough heavy elements to build substantial solid bodies. In a metal-poor environment, planets might be mostly gas and ice, lacking the rocky cores and surfaces that seem essential for Earth-like life. This means that life, at least life as we know it, requires a certain level of cosmic maturity. The universe needed to age, stars needed to live and die, heavy elements needed to be created and scattered before planets like Earth could form and life could emerge. We're living in a chemically evolved galaxy, enriched by billions of years of stellar alchemy, and that enrichment might be a prerequisite for our existence. The metallicity of stars also varies by location in the galaxy. The central regions tend to be more metal-rich because star formation has been more intense there, cycling gas through stars more rapidly. The outer regions are more metal-poor, having experienced less star formation and enrichment. There's a metallicity gradient across the galactic disk, with the inner regions showing higher abundances of heavy elements than the outer regions. By measuring stellar metallicities throughout the galaxy, astronomers can map out the history of star formation and gas flows. Where did gas accumulate? Where did stars form most actively? How has material moved around the galaxy over billions of years? The chemical fingerprints in stellar atmospheres preserve this history, offering clues to processes that happened long before the Sun formed, recorded in the elements, themselves like entries in a cosmic ledger. The Milky Way's disk formed as the initial gas cloud flattened due to rotation, a process driven by conservation of angular momentum, one of the fundamental principles of physics that governs how rotating systems behave. When a cloud of gas is rotating and begins to collapse under its own gravity, it doesn't collapse uniformly in all directions. Instead, it flattens along the axis of rotation, like pizza dough spun in the air. This happens because angular momentum must be conserved. As the cloud contracts, it would naturally spin faster. The same principle that makes ice skaters spin faster when they pull in their arms. But material can't easily move perpendicular to the rotation axis because that would require changing its angular momentum. Material can fall inward along the rotation axis relatively easily, but sideways motion is constrained. The result is that the cloud flattens into a disk, thin in the direction perpendicular to rotation, extended in the plane of rotation. This process took billions of years. The proto-Milky Way started as a roughly spherical cloud, but as it collapsed and merged with other fragments, the net rotation became more organized. Material that wasn't rotating with the general flow either fell to the center, where it became part of the bulge, or was ejected from the system entirely. What remained settled into a rotating disk, where most of the gas accumulated, and where most subsequent star formation occurred. The disk didn't form instantaneously. The oldest disk stars are about 10 billion years old, suggesting the disk began forming roughly 3 to 4 billion years after the Big Bang. The youngest disk stars are forming today, still emerging from collapsing gas clouds in the spiral arms. The disk has been a continuous feature of the galaxy for most of its history, the dominant structure where stars live and gas cycles through its phases. Not everything ended up in the disk. The halo stars, those in the spherical distribution surrounding the disk, either formed before the disk or formed in satellite galaxies that were later accreted. These stars retain their more random, non-circular orbits, remnants of the chaotic early epoch, before the disk's rotation dominated the galaxy's dynamics. They're like fossils of an earlier era, preserved in their motion even as the galaxy evolved around them. The disk's thinness is remarkable. It's about 100,000 light-years across, but only about 1,000 light-years thick, a ratio of 100.1. This extreme flattening is the natural result of dissipative collapse. Gas clouds can collide and lose energy, settling into the most stable configuration, which is a rotating disk. Stars can't collide and dissipate energy in the same way, so they retain whatever distribution they had when they formed. But new stars form from gas, and gas settles into the disk. This disk structure is why the Milky Way appears as a band across the sky. When we look along the plane of the disk, we see through the densest concentration of stars, thousands of light years of stellar population compressed into our line of sight. When we look perpendicular to the disk, we see through much less material, just the local stellar neighborhood before the view opens up to extragalactic space. The Milky Way's appearance is a direct consequence of our embedded position within this flattened structure. Supernovae explosions distribute heavy elements throughout the galaxy, seeding future generations of stars and planets with the raw materials for complexity. These violent stellar deaths are the primary mechanism by which elements heavier than helium get scattered into the interstellar medium, making them available for incorporation into new stars, new planets, and eventually new life. When a massive star reaches the end of its life, it has an onion-like structure, layers of different elements created through successive stages of fusion. The outermost layers are still hydrogen. Beneath that is helium, then carbon and oxygen, then neon and magnesium, then silicon, and finally an iron core at the center. Iron is the endpoint of fusion. You can't extract energy by fusing iron into heavier elements. When the iron core grows large enough, it becomes unstable and collapses. The collapse is catastrophic. In less than a second, the core implodes from the size of the Earth to the size of a city, compressing to nuclear density and rebounding in a shock wave that tears through the star's outer layers. This shock heats the layers to billions of degrees, triggering explosive fusion that creates all the elements heavier than iron: nickel, copper, zinc, gold, uranium. The explosion then blasts all of this material, the fusion products from the star's life, plus the newly created heavy elements, into space at thousands of kilometers per second. This ejected material expands outward, forming a supernova remnant, a glowing shell of hot gas enriched with heavy elements. Over thousands of years, the remnant expands and cools, eventually mixing with the surrounding interstellar medium. The heavy elements become part of the general galactic gas, available to be incorporated into the next generation of stars and planets. Every atom heavier than hydrogen in your body came from this process. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all were forged in stellar cores and scattered by supernova explosions. You are literally made of stardust and supernova ash, assembled from atoms that were created in stars that died billions of years ago, long before the sun and earth existed. The distribution of heavy elements isn't uniform throughout the galaxy. Regions with more intense star formation have experienced more supernovae and are more enriched. The central regions of the galaxy, where star formation has been most active, have higher metallicity than the outer regions. There's also variation within the disk. Some regions are more enriched than others, depending on local star formation history. Supernovae also affect star formation itself. The shock waves they produce can trigger the collapse of nearby gas clouds, initiating new episodes of star formation. But they can also disrupt star formation by heating and dispersing gas, preventing it from collapsing. Supernovae are both creators and destroyers. They end stars but also create the conditions for new stars. They destroy, but also distribute the raw materials for future complexity. The frequency of supernovae in the Milky Way is roughly 1 every 50 years, though they're difficult to observe because most occur in regions obscured by dust. The last nearby supernova visible to the naked eye was in 1604, Kepler's supernova, and before that, Tycho's supernova in 1572. We're overdue for one, statistically speaking, though overdue on these timescales doesn't mean much. The next galactic supernova could happen tomorrow, or it could be hundreds of years from now. When it does occur, it will be spectacular, potentially bright enough to be visible during the day, a cosmic reminder of the violent processes that created the elements we're made of. The Milky Way has gone through distinct epochs in its star formation history, with periods of intense activity followed by quieter times. Like a breathing organism with rhythms of birth and rest that span billions of years. These variations are driven by the availability of gas, the frequency of mergers, and the internal dynamics of the galaxy as it evolved from its chaotic youth to its current mature state. The earliest epoch, from about 13 to 10 billion years ago, was a time of rapid star formation. The proto-Milky Way was gas-rich, experiencing frequent mergers with smaller galaxies, and conditions were turbulent. Stars formed quickly from this abundant gas, creating the oldest stellar populations we see today in the halo and globular clusters. This was the galaxy's infancy, characterized by growth and activity. Around 10 billion years ago, the Gaia-Enceladus collision occurred, a major merger that heated the disk and temporarily disrupted star formation. After this event, the galaxy entered a period of lower activity as it settled back into equilibrium. The disk reformed, rotation became more organized, and star formation continued, but at a more moderate pace. There was another burst of star formation, roughly 2 to 3 billion years ago, possibly triggered by an interaction with a satellite galaxy or simply by the natural accumulation of gas in the disk. This created a population of relatively young stars that are now in their middle age, contributing to the galaxy's current stellar population. Currently, the Milky Way is in a relatively quiet phase, with star formation occurring at a steady but modest rate of 1 to 2 solar masses per year. This is typical for a mature spiral galaxy, not dormant, but not in a starburst phase either. The available gas is being converted to stars slowly, and there are no major mergers currently disrupting the system. These variations in star formation rate are recorded in the age distribution of stars by measuring stellar ages through techniques like asteroseismology, which analyzes stellar oscillations, or by dating star clusters. Astronomers can reconstruct when different populations formed. The result is a kind of timeline, showing when the galaxy was most active and when it was quieter, a history of cosmic activity written in the stars themselves. The future will bring another dramatic change. When the Milky Way collides with Andromeda in about 4 billion years, there will be an intense starburst as gas clouds from both galaxies collide and compress. This will be one of the most active periods in the galaxy's history, possibly the last major episode of star formation before the merged system settles into quiescence as an elliptical galaxy with little remaining gas. These epochs demonstrate that the galaxy is not a static structure, but a dynamic system, evolving over cosmic time, responding to internal processes and external influences. The stars we see today formed during different epochs, under different conditions, and they carry in their properties, their ages, their compositions, their orbits, the signatures of the galaxy's long history. The Milky Way has consumed 5 to 15 smaller galaxies throughout its history, each one leaving traces in the galaxy's current structure. A cosmic palimpsest where each absorbed galaxy is a ghostly text written over the last, stories layered through time. This process of galactic cannibalism is how large galaxies grow, building themselves up by consuming smaller neighbors that wander too close or orbit too long in the gravitational grip of the larger structure. The evidence for these ancient meals is written in several places. Stellar streams in the halo mark the disrupted remains of dwarf galaxies, their stars spread into long ribbons by tidal forces. Chemical signatures distinguish populations that formed in separate galaxies, stars with unusual elemental abundances, or patterns that don't match the Milky Way's general population. Orbital patterns reveal groups of stars moving together in ways that suggest a shared origin in a now destroyed satellite. Each absorbed galaxy brought its own population of stars, its own dark matter halo, its own history. When consumed, the stars were added to the Milky Way's halo. The dark matter was absorbed into the larger dark matter distribution. and any gas was either stripped away by ram pressure as the galaxy plunged through the Milky Way's disk, or added to the interstellar medium to fuel future star formation. The process is ongoing. The Sagittarius dwarf elliptical galaxy is currently being torn apart as it orbits through the Milky Way, leaving streams of stars that wrap around the galaxy multiple times. The Canis Major dwarf, if it's a separate galaxy and not just an overdensity of disk stars, is also being disrupted. The Magellanic Clouds may eventually suffer the same fate, though their larger mass means they'll take longer to consume. Not all of these mergers were equal. Some brought just a few million stars, barely noticeable additions to the Milky Way's hundreds of billions. Others, like Gaia Enceladus, were more substantial, bringing hundreds of millions of stars and significantly affecting the galaxy's structure and evolution. The largest merger in the last few billion years heated the disk, puffed up the halo, and left a clear signature that we can still detect today. This cannibalistic growth is predicted by cosmological simulations of galaxy formation. In the standard model of structure formation, small dark matter halos form first, then merge to form larger ones in a hierarchical process. Galaxies follow this pattern, with large galaxies like the Milky Way assembled from numerous smaller pieces over billions of years. The universe builds structure from the bottom up, small things merging to form larger things in a cosmic tree of assembly. The victims of this process are not lost exactly. Their stars still exist, still orbit, but now as part of the Milky Way rather than independent galaxies. They're immigrants, absorbed into a larger structure, their identity as separate entities erased, but their contribution to the whole preserved. The Milky Way is a composite, built from pieces, a collection of merged fragments that have lost their individual identities, but collectively form the galaxy we call home. The Milky Way produces Fermi bubbles, enormous structures of high-energy gas extending about 25,000 light-years above and below the galactic center, visible in gamma rays like cosmic breath exhaled from the galaxy's core. These bubbles were discovered in 2010 by analyzing data from the Fermi Gamma Ray Space Telescope, and they represent one of the most dramatic, large-scale structures associated with our galaxy. The bubbles are roughly symmetrical, extending equally above and below the galactic plane, creating a dumbbell or hourglass shape centered on the galactic core. They're filled with high-energy particles and hot gas glowing in gamma rays, the most energetic form of electromagnetic radiation. From Earth, they subtend a huge portion of the sky, about 50 degrees from end to end, though they're invisible to optical telescopes and only revealed in gamma-ray observations. What created these bubbles? The leading theory is that they were produced by a period of intense activity from Sagittarius A, the supermassive black hole at the galactic center, perhaps a few million years ago. During this active period, the black hole might have consumed a large amount of material, producing powerful jets of energy that blasted outward perpendicular to the galactic disk. These jets carved out the bubbles, pushing aside the surrounding gas and creating the structures we see today. Alternatively, or perhaps additionally, the bubbles might have been created by a burst of intense star formation in the galactic center, producing numerous supernovae in a short period. These explosions could have driven a wind of hot gas outward from the disk, creating the bubbles through collective stellar feedback rather than black hole activity. The truth might involve both processes: star formation driving gas toward the center, which then fed the black hole, which then produced jets, a combined process creating the observed structures. The bubbles are expanding, though slowly by human standards, perhaps 300 kilometers per second, which sounds fast but is gradual on galactic scales. Over millions of years, they've grown to their current enormous size, and they'll continue expanding for millions more, gradually slowing as they plow into the surrounding halo gas. Similar structures have been observed in other galaxies, suggesting this is a common phenomenon. Galactic centers occasionally become active, producing outflows and bubbles that reshape the surrounding environment. In our case, the Fermi bubbles indicate that Sagittarius A wasn't always as quiet as it is today, that the galactic center has experienced more violent episodes in the relatively recent past. The discovery of the Fermi bubbles also revealed the A Rosita bubbles, similar structures visible in X-rays that roughly align with the gamma-ray bubbles. Together, these structures show that the region around the galactic center is more complex and active than visible light alone would suggest, with energetic processes operating on truly massive scales, invisible to optical telescopes but clear in high-energy observations. These bubbles are a reminder that the galaxy is not inert but active, that its central regions occasionally experience violent events that affect the entire structure. The Fermi bubbles are like cosmic burps, evidence of digestive processes in the galactic core, material being processed and expelled in events that leave traces visible millions of years later. The Milky Way has its own magnetic field, organized and surprisingly strong, threading through the disk like invisible fibers that guide charged particles and influence the structure of the interstellar medium. This field isn't uniform. It follows the spiral arms, wrapped around the galaxy by differential rotation, creating a large-scale pattern that pervades the disk. Magnetic fields in space are generated and maintained through a process called a dynamo, similar to how the Earth's magnetic field is created by the motion of molten iron in its core. In the galaxy's case, the dynamo is driven by the rotation of the disk and by turbulent motions in the interstellar medium, gas flows, supernova shocks, stellar winds. These motions stretch and twist the field lines, amplifying the magnetic field over time. The field strength is about 5 microgauss on average, roughly 1,000,000 times weaker than the Earth's magnetic field at its surface, but extended over such vast distances that the total energy stored in the galactic magnetic field is enormous. This field affects how gas moves and how stars form. It provides pressure that resists gravitational collapse, making it slightly harder for gas clouds to collapse into stars. It also guides the motion of cosmic rays, high-energy charged particles that spiral along the field lines as they traverse the galaxy. The magnetic field is most easily detected through its effects on radio waves. When radio waves pass through a magnetized plasma, like the ionized gas in the interstellar medium, their polarization gets rotated by an effect called Faraday rotation. By measuring this rotation for radio waves from distant sources, astronomers can map the strength and direction of the galactic magnetic field along different lines of sight, gradually building up a 3-dimensional picture of the field's structure. Recent observations have revealed that the field is more complex than simple models predicted. There are reversals, regions where the field flips direction, and there are vertical components extending out of the galactic plane, possibly connected to the Fermi bubbles or other outflow structures from the galactic center. The field appears to be partly ordered, following the spiral arms, but also partly turbulent, with random fluctuations on smaller scales. This magnetic field plays a crucial role in the ecology of the galaxy. It influences how gas flows and where it accumulates, affecting star formation. It shapes the structure of supernova remnants, creating the filamentary patterns visible in some remnants. It guides cosmic rays, preventing them from escaping the galaxy immediately and keeping them trapped to interact with the interstellar medium. Without the magnetic field, the galaxy would look different, behave differently, perhaps evolve differently. The existence of such a large-scale, organized field is a testament to the galaxy's coherent rotation and the efficiency of the dynamo process. Over billions of years, the random motions of gas have conspired to create order from chaos, building up a magnetic structure that spans the entire disk. It's another invisible architecture supporting the visible galaxy, alongside dark matter, forces and fields we can't see directly, but which fundamentally shape the structure and evolution of our cosmic home. The Milky Way emits radiation across the entire electromagnetic spectrum: radio waves, infrared light, visible light, ultraviolet, X-rays, and gamma rays, each wavelength revealing a different aspect of the galaxy, like looking at the same landscape in different seasons or times of day. What you see depends on which wavelength you choose to observe in, and combining observations across wavelengths gives the most complete picture. In radio waves, the galaxy glows with the emission from cold hydrogen gas, tracing the spiral arms and revealing the large-scale structure. Radio observations can penetrate dust that blocks visible light, allowing us to map regions that are otherwise hidden. The galactic center, obscured in optical wavelengths, becomes visible in radio, revealing the central concentration of stars and gas surrounding Sagittarius A. In infrared, the Milky Way is dominated by thermal emission from dust grains heated by starlight radiating their energy in the infrared. This wavelength is ideal for studying star-forming regions, where dust is abundant and warm, and for seeing through the dusty disk to observe the galactic center and bulge. The infrared view reveals cool stars that don't shine brightly in visible light, like red giants and brown dwarfs. In visible light, we see the stars themselves, billions of individual points of light, with concentrations in the spiral arms and central bulge. This is the wavelength our eyes evolved to detect, optimized for seeing the sun's light reflected off objects, and it's the traditional view of the galaxy. But it's also limited. Dust obscures much of the disk, and many interesting structures are invisible in visible wavelengths. In ultraviolet, we see hot, young stars, massive blue stars that burn fiercely and die young. UV observations trace recent star formation, highlighting regions where massive stars have recently formed and are now illuminating their surroundings with intense ultraviolet radiation. These stars don't live long, so their presence indicates active or recent star formation. In X-rays, the galaxy reveals its violent side. X-rays come from extremely hot gas, millions of degrees, created by supernovae, by stellar winds from massive stars, by accretion onto neutron stars and black holes. X-ray observations show supernova remnants, binary systems where one star is stripping material from another, and the hot, diffuse gas pervading the galaxy and filling the Fermi bubbles. In gamma rays, the highest energy form of light, we see cosmic ray interactions, emissions from pulsars, and possibly signals from dark matter annihilation, though this last possibility is still debated. Gamma rays reveal the most energetic processes in the galaxy, events involving particles accelerated to nearly the speed of light, conditions of extreme temperature and energy. Each wavelength is like a different sense, revealing phenomena invisible to the others. An astronomer studying only invisible light would miss the structure revealed in radio, the star formation traced in infrared, the violence shown in X-rays. The complete picture comes from combining all wavelengths, building a multi-sensory portrait of the galaxy that encompasses its full complexity. This is why modern astronomy uses spacecraft and telescopes, observing across the entire spectrum. The Milky Way isn't just one thing. It's a superposition of phenomena, each operating on different scales and at different energies, all interacting to create the rich, complex structure we inhabit. To understand it fully requires seeing it in all its wavelengths, appreciating how each reveals a different facet of the whole. There are stars in the Milky Way traveling so fast they'll eventually escape the galaxy entirely. Hypervelocity stars, cosmic outcasts sentenced to exile in intergalactic space. These stars are moving at speeds of 300 to 1,000 kilometers per second, far faster than the typical orbital velocity of stars in the disk, fast enough to overcome the galaxy's gravitational pull and fly off into the void. Most hypervelocity stars were likely flung out by close encounters with Sagittarius A, the supermassive black hole at the galactic center. The mechanism involves a binary star system, two stars orbiting each other, that ventures too close to the black hole. The intense tidal forces from the black hole tear the binary apart. One star gets captured into a tight orbit around the black hole or falls in, while the other gets flung away at high speed, its orbital energy converted into velocity that sends it racing away from the galactic center. This process was first proposed theoretically and has since been observationally confirmed. Dozens of hypervelocity stars have been identified, most of them on trajectories leading back to the galactic center, exactly as predicted if they were ejected by the central black hole. Their velocities can be measured through Doppler shifts in their spectral lines, and their paths can be traced backward to determine their point of origin. Not all hypervelocity stars come from the galactic center. Some might have been accelerated by supernova explosions. If a star is in a binary system and its companion explodes, the sudden loss of mass can unbind the system, flinging the surviving star away at high speed. Others might have been ejected from the disk by gravitational interactions with massive star clusters or molecular clouds. These stars are now on one-way journeys into intergalactic space. Over millions of years, they'll travel farther and farther from the Milky Way, eventually crossing into the space between galaxies. They'll become isolated, wandering through the vast emptiness with no nearby stars, no galactic disk, just the distant view of the Milky Way, and Andromeda slowly receding as they drift into the cosmic void. Their fate is to become intergalactic travelers, free from any galaxy's gravitational embrace. They'll orbit in the larger gravitational potential of the local group, perhaps eventually falling into one of the other galaxies, but more likely just wandering the space between them. Isolated embers from the Milky Way's stellar population. If they have planets, and there's no reason they couldn't, those planets will orbit a star that travels between galaxies, an ultimate exile from galactic civilization. The existence of hypervelocity stars demonstrates the dynamical complexity of the galaxy. Stellar encounters, particularly near the supermassive black hole, can produce extreme outcomes. Stars captured into impossibly tight orbits, or stars flung away to escape the galaxy entirely. These are the outliers, the statistical tale of orbital dynamics, but they reveal the range of possible fates for stars in the Milky Way. Most orbit peacefully for billions of years. A few meet more dramatic destinies, consumed by the central black hole, destroyed in stellar collisions, or expelled into the intergalactic void, eternal wanderers carrying a piece of the Milky Way with them wherever they go. The galactic center occasionally flares with X-ray activity, possibly from the black hole swallowing passing asteroids or gas clouds. Sagittarius A, stirring briefly from its mostly sleeping state. These flares are dramatic increases in brightness, sometimes by factors of hundreds, lasting hours to days, before fading back to the baseline level. They're irregular, unpredictable, eruptions of energy from the galaxy's dark heart. The flares are detected primarily in X-rays and infrared, wavelengths that can penetrate the dust obscuring the galactic center. During a flare, the emission from Sagittarius A brightens suddenly, then gradually fades over several hours. The spectrum of the emission suggests it's from hot gas near the black hole, material that's been heated to millions of degrees as it spirals inward. What causes these flares? The leading theory is that they're triggered when small objects, asteroids, comets, or clouds of gas, fall into the black hole. As these objects approach the event horizon, tidal forces tear them apart, heating the material to extreme temperatures. The disrupted material forms a temporary accretion flow, spiraling inward and radiating energy before disappearing beyond the event horizon. Once the material is consumed, the flare subsides, and the black hole returns to its quiet state. Some flares might be caused by magnetic reconnection events in the accretion flow, the same process that creates solar flares on the Sun, but on a much larger scale. Magnetic field lines in the hot ionized gas near the black hole can become twisted and stressed until they snap and reconnect, releasing enormous amounts of energy in the process. This energy heats the gas and accelerates particles, creating the observed flare. The flares are brief windows into the black hole's feeding process. Most of the time, Sagittarius A is quiescent, accreting gas at a very low rate. But when something falls in, a gas cloud passing too close, an asteroid disrupted by tidal forces, we get to observe the black hole actively consuming material, a glimpse of the processes that shape its evolution over cosmic time. Observations of these flares help constrain models of how matter behaves in the extreme environment near a black hole. The timescales of the flares, how quickly they rise and fall, tell us about the size and structure of the emitting region. The spectrum of the emission reveals the temperature and density of the gas. By studying many flares, astronomers can build up a statistical picture of how the black hole accretes material and what triggers these episodic bursts of activity. Despite these flares, Sagittarius A remains remarkably quiet compared to supermassive black holes in other galaxies. Some active galactic nuclei shine with the luminosity of trillions of suns, powered by massive accretion flows feeding the central black hole. Sagittarius A, even during its brightest flares, is millions of times dimmer. It's a gentle giant, stirring occasionally but never rousing to full wakefulness, at least not in the current epoch. Its quiet nature is part of what makes the Milky Way's center a relatively benign environment, despite harboring one of the most extreme objects in the known universe. The Milky Way contains stellar streams, long trails of stars flowing through the halo, like rivers through space. The stretched-out remains of disrupted star clusters and dwarf galaxies that wandered too close and were torn apart by tidal forces. These streams are ghostly ribbons, sometimes stretching for tens of thousands of light years, marking the paths where smaller structures met their end. When a star cluster or dwarf galaxy orbits the Milky Way, it experiences tidal forces, the difference in gravitational pull between its near and far sides. If the object is small and the tidal forces are strong enough, these forces can overcome the object's own gravity, pulling stars away from the front and back. Over time, the cluster or galaxy gets stretched along its orbit, like taffy being pulled, until it's completely disrupted and spread into a long stream. The stars in these streams all move together, following similar orbits because they share a common origin. This coherent motion makes them detectable, even though they're mixed in with all the other halo stars. By measuring the positions and velocities of millions of stars, data that the Gaia spacecraft has made available, astronomers can identify groups of stars moving in lockstep, revealing streams that would otherwise be invisible against the background of the stellar halo. The Sagittarius stream is one of the most prominent examples. It wraps around the entire Milky Way multiple times, a consequence of the Sagittarius dwarf elliptical galaxy's repeated passages through the galactic disk. Each time the dwarf galaxy orbits, it loses more stars to tidal stripping, leaving behind a trail that traces its orbital path. By mapping this stream, astronomers can reconstruct the dwarf galaxy's orbit and predict where it will go next, watching a slow-motion disruption that's been unfolding for billions of years. Other streams have more exotic origins. The GD1 stream is thought to be the remnant of a globular cluster that was disrupted. Its stars now spread along a thin line, tens of thousands of light years long. The stream is so thin, just a few hundred light years wide, that it looks almost like a painted line across the halo, a delicate structure preserved by the orderly nature of orbital mechanics. These streams serve as probes of the galaxy's gravitational field. As stars move through the halo, their paths are affected by the distribution of mass, both visible and dark matter. Irregularities in streams, gaps, or kinks in their structure can reveal the presence of dark matter, clumps, or other massive objects that perturbed the stream as it passed. In this way, stellar streams become tools for mapping the invisible architecture of the galaxy. There's something elegiac about stellar streams. They're memorials to structures that no longer exist, galaxies and clusters that have been pulled apart and scattered. The stars themselves continue, still shining, still orbiting, but they're no longer part of a coherent whole. They've lost their collective identity, become part of the Milky Way's halo, their individual orbits preserving the memory of their origin, like mourners walking in a funeral procession. And the process continues. More satellites will be disrupted in the future. The streams we see today will gradually disperse, their coherent structure blurred by interactions with the galactic disk and by the natural spreading of orbital velocities. Eventually, the streams will fade into the general halo population, their stars indistinguishable from the background, except for chemical signatures that might persist long after the kinematic coherence is lost. They're transient structures, visible for a few billion years before dissolving, windows into the ongoing process of galactic assembly. The Milky Way produces cosmic rays, high-energy particles, mostly protons, that constantly bombard Earth from all directions, accelerated by supernova shocks and other violent events to nearly the speed of light. These particles carry enormous energy, sometimes exceeding the energy of particles produced in human-built accelerators, and they travel through the galaxy along twisted paths dictated by the galactic magnetic field. Cosmic rays are created primarily in supernova remnants. When a massive star explodes, the shock wave that propagates outward can accelerate nearby particles to tremendous speeds through a process called diffusive shock acceleration. Particles bounce back and forth across the shock front, gaining energy with each crossing, until they're moving at nearly the speed of light. These accelerated particles then escape into the interstellar medium, where they travel through the galaxy as cosmic rays. Because cosmic rays are charged particles, they don't travel in straight lines. The galactic magnetic field deflects them, causing them to spiral and zigzag through space. A cosmic ray that originated in a supernova remnant thousands of light years away might take millions of years to reach Earth, following a convoluted path that bears no resemblance to a straight line. By the time it arrives, there's no way to trace it back to its source. The particle has been so thoroughly scrambled by magnetic fields that its direction of arrival tells you nothing about where it came from. Despite this, cosmic rays are surprisingly uniform in their distribution throughout the galaxy. They're effectively trapped by the galactic magnetic field, bouncing around within the disk and halo for millions of years before eventually escaping into intergalactic space. This creates a relatively constant background of cosmic ray particles pervading the galaxy, constantly interacting with the interstellar medium and occasionally striking Earth's atmosphere. When a cosmic ray hits Earth's atmosphere, it collides with air molecules and creates a shower of secondary particles, pions, muons, electrons, photons, that cascade downward. Some of these particles reach the ground, where they can be detected by cosmic ray observatories. By studying these showers, physicists can learn about the original cosmic ray particle, its energy, its composition, even hints about its origin. Cosmic rays are also important for the chemistry of the interstellar medium. They ionize atoms in molecular clouds, creating charged particles that can participate in chemical reactions that wouldn't occur otherwise. Some complex organic molecules in space might owe their existence to cosmic ray-induced chemistry, reactions triggered by these high-energy particles passing through otherwise cold and dark regions. The highest energy cosmic rays, ultra-high energy cosmic rays, are particularly mysterious. These particles carry so much energy that they couldn't have been confined within the galaxy. They must come from outside, from sources we haven't identified yet. Perhaps they're accelerated in the jets of active galactic nuclei, or in galaxy mergers, or by some other exotic process. They're rare. Only a handful arrive at Earth each year, but each one carries energy equivalent to a baseball thrown at high speed, concentrated in a single atomic nucleus. Where they come from and how they're accelerated remains one of the great unsolved mysteries in astrophysics. For all the time humans have lived on Earth, cosmic rays have been raining down constantly, mostly unnoticed. These high-energy messengers from violent events scattered throughout the galaxy. They pass through our bodies, several per second, leaving no trace we can feel. Invisible particles from distant stellar explosions connecting us to the galaxy's most energetic processes. The Milky Way's spiral arms are not permanent structures, but density waves, regions where stars temporarily crowd together, creating patterns that persist even as individual stars flow through them. This is one of the more counterintuitive aspects of galactic structure. The arms look like solid features, but they're really more like traffic jams, where the cars change, but the jam persists. The density wave theory was developed in the 1960s to explain a fundamental problem. If spiral arms were made of the same stars rotating together, differential rotation would wind them up tighter and tighter over time until they disappear into a blur. But observed spiral galaxies have well-defined arms that haven't wound up excessively, suggesting the arms aren't rotating with the stars. Instead, the arms are pressure waves that rotate at a different speed than the stars themselves. Stars orbit the galactic center at velocities determined by the mass distribution, but the density wave pattern rotates at its own, slower speed. As stars orbit, they catch up to the spiral arm from behind, slow down as they pass through the denser region, then speed up again as they exit the arm on the other side. It's very much like traffic on a highway. Cars approach a congestion zone, the spiral arm, slow down as they enter the dense region, then speed up once through. The congestion itself, the pattern of high density, moves at a different speed than the cars, perhaps even backward relative to traffic flow if the jam is caused by an accident that isn't moving. The cars flow through, but the jam persists in the same location. This explains several observed features of spiral arms. They're sites of active star formation because the compression of gas as it enters the arm triggers collapse and star formation. Massive, short-lived stars form in the arms and die there, never making it through to the other side, so the arms are outlined by young, bright blue stars. Lower mass stars like the Sun live long enough to orbit through many arms over their lifetimes, spending most of their time in the interarm regions. The density wave pattern itself needs something to maintain it. Otherwise, it would gradually dissipate over cosmic time. The exact mechanism is still debated, but it likely involves interactions between the disk and the bar, resonances in the gravitational potential, or even the influence of satellite galaxies. The pattern is self-sustaining to some degree, with the enhanced gravity in the arms helping to maintain the density enhancement that creates the arms in the first place. This means the Sun has passed through spiral arms multiple times during its 4.5 billion year life. We're currently in the Orion Spur, but we won't stay here forever. Eventually, we'll drift out of this region and spend time in an interarm zone before entering another arm. The spiral arm you're in right now isn't a permanent address but a temporary location, a phase in the sun's long orbital journey around the galaxy. There's something elegant about this. The idea that persistent patterns can emerge from fluid motion, that structure doesn't require rigidity, but can arise from the organized flow of components through a standing wave. The spiral arms are like standing waves on a river, persistent features created by the interaction of flow and topography. Beautiful patterns that seem permanent, but are actually dynamic, existing only because of continuous motion rather than despite it. There are regions near the galactic center where stars orbit, so fast they complete a full orbit in just a few years, surfing the edge of the black hole's gravity well at incredible speeds, cosmic Formula One racers. These are the S-stars, a group of mostly young, massive stars in tight orbits around Sagittarius A, moving at velocities that would be incomprehensible in any other context. The most famous is S2, also called SR22, which orbits the black hole in just 16 years with a closest approach of about 120 AU, roughly 4 times the distance from the Sun to Neptune. At its closest, S2 reaches velocities of about 7,650 kilometers per second, roughly 2.5% the speed of light. This is fast enough that relativistic effects become measurable, making S2 an ideal test of Einstein's theory of general relativity in the strong field regime. Observations of S2 have confirmed several predictions of general relativity. Its orbit precesses, the ellipse rotates slowly over time, a phenomenon called perihelion precession, also seen in Mercury's orbit, but much more pronounced for S2. The star's light is gravitationally redshifted when it's deep in the black hole's gravitational well, exactly as general relativity predicts. These observations provide some of the best tests of general relativity in strong gravitational fields, conditions that don't exist anywhere in the solar system. Other S-stars have even tighter orbits. S4714 has an orbital period of just 12 years and reaches 8% the speed of light at closest approach. S62 orbits in about 9.9 years. These stars are living on the edge, orbiting in a region where gravity is so intense that space-time is significantly warped, where velocities approach relativistic speeds, where the tidal forces from the black hole are strong enough to distort the stars themselves. How did these stars end up in such extreme orbits? They're too young to have been there since the galaxy formed. Massive stars like the S-stars only live a few million years, far less than the age of the galaxy. The leading theory is that they formed in a disk of gas around the black hole, perhaps from gas brought in by a disrupted molecular cloud or smaller galaxy. Alternatively, they might have migrated inward from larger orbits through dynamical interactions with other stars, or a hypothetical intermediate mass black hole that has since merged with Sagittarius A. Watching these stars orbit provides direct dynamical evidence for the black hole's mass. By measuring the stars' orbits, their periods, their distances of closest approach, their velocities, astronomers can calculate the mass they're orbiting using Kepler's laws. The answer is unambiguous. There's something with about 4 million solar masses concentrated in a region smaller than the smallest S-star orbit. The only object that can be that massive and that compact is a supermassive black hole. These observations won Andrea Ghez and Reinhard Genzel the 2020 Nobel Prize in Physics, recognizing their decades of patient work tracking these stars with ever-improving telescopes and adaptive optic systems. The S-stars are natural laboratories for testing physics in extreme conditions, windows into the environment around a supermassive black hole, witnesses to the most extreme gravitational conditions in our galaxy. And they're orbiting right now, completing another lap around the darkness at the center of everything. Messengers from a realm where space-time itself is twisted into new geometries. The Milky Way experiences stellar quakes, oscillations that ripple through the disk like waves on a pond, disturbances that reveal the galaxy is more fluid than solid. These aren't literal earthquakes. Stars aren't rigid bodies that can crack and shift. Rather, they're collective oscillations of the stellar disk. Patterns of motion where stars move up and down or in and out in coordinated ways, creating waves that propagate through the disk. These oscillations were discovered through careful analysis of stellar positions and velocities from the Gaia spacecraft. When astronomers looked at the vertical motions of stars, how fast they're moving perpendicular to the galactic plane, they found patterns. Stars weren't just randomly bobbing up and down. There were coherent structures, regions where stars were systematically moving upward or downward together, organized into waves. The discovery suggests that something disturbed the disk in the relatively recent past, perhaps a satellite galaxy passing through, or a close encounter with a dark matter clump, or even the cumulative effect of multiple smaller perturbations. When the disk is disturbed, it doesn't just return to equilibrium immediately. Instead, it rings like a bell, oscillating for hundreds of millions of years before the waves gradually damp out. These stellar quakes tell us that the galactic disk is not in perfect equilibrium, but is dynamically active, responding to perturbations and evolving in response to external forces. The disk is more like a membrane or a sheet of water than a solid structure. It can support waves, ripples, collective motions that reveal its fluid nature. The waves also provide information about the galaxy's mass distribution, how fast the waves propagate, how they're damped, which modes are excited. All of these depend on the disk's properties, including its mass, thickness, and the distribution of dark matter. By studying the waves, astronomers can constrain models of the Milky Way's structure, using the oscillations as a diagnostic tool. One interpretation is that these waves are the lingering effects of the Sagittarius dwarf elliptical galaxy's passages through the disk. Each time Sagittarius plunges through, it sends a shock wave through the stellar distribution, exciting oscillations that gradually decay over time. We might be seeing the cumulative result of multiple such passages, the disk still ringing from encounters that happened hundreds of millions of years ago. The discovery of stellar quakes changes how we think about the Milky Way. It's not a static structure frozen in time, but a dynamic system, still responding to past disturbances, still settling from ancient collisions. The disk you're embedded in right now is oscillating, waving gently like a flag in a breeze, and you're participating in that motion, bobbing up and down as part of a collective pattern that involves billions of stars. You just can't feel it because the time scales are so long and the motion's so gradual that from your perspective, everything seems still. Our galaxy contains mysterious, high-velocity clouds of hydrogen moving at different speeds than the general rotation, some falling into the galaxy like rain from the cosmic void, others being expelled like exhalations. These clouds don't follow the orderly rotation of the disk. They're mavericks, moving on their own trajectories, and their origins and destinations are still being debated. Some high-velocity clouds are thought to be gas falling into the galaxy from the intergalactic medium, fresh fuel for future star formation. The Milky Way, like all galaxies, needs to continuously accrete gas to sustain star formation. Without new gas infall, the existing gas would be converted to stars or heated and expelled, and star formation would gradually cease. The high-velocity clouds might represent this accretion process in action, streams of gas condensing from the hot halo gas or the intergalactic medium and falling toward the disk. Other clouds might be material ejected from the disk by supernova explosions or stellar winds, gas blown out of the plane by energetic events and now falling back down under gravity. This is part of the galactic fountain model. Gas is heated and expelled upward, cools as it rises, then rains back down onto the disk, creating a cycle of material flowing out and back in over millions of years. The composition of high-velocity clouds provides clues to their origin. Some are metal-poor, suggesting they're relatively pristine gas from outside the galaxy that hasn't been enriched by stellar processing. Others are metal-rich, suggesting they originated in the disk and were expelled outward, carrying with them the chemical signature of stellar nucleosynthesis. One of the most famous high-velocity clouds is the Smith cloud, a large cloud of hydrogen heading toward the disk and expected to collide with it in about 30 million years. When it does, the collision will likely trigger a burst of star formation, compressing gas in the disk and causing it to collapse into new stars. The cloud contains enough material to form a few million stars, so the collision will be a significant event, at least on galactic scales. The existence of these clouds suggests that the boundary between the galaxy and the intergalactic medium is not sharp but fuzzy, with material flowing both ways, some falling in, some being expelled, creating a complex ecology of gas exchange. The Milky Way is not a closed system but an open one, interacting with its environment, breathing in and out, maintaining itself through continuous exchange with its surroundings. Studying high-velocity clouds helps us understand the circumgalactic medium, the halo of hot, diffuse gas surrounding the galaxy. This gas contains as much mass as all the stars in the disk, but it's so diffuse and so hot that it's almost invisible, detectable only through its absorption of light from distant background sources, or through the high-velocity clouds that condense from it. The circumgalactic medium is a reservoir of material, a resource the galaxy can draw on for future star formation, and the high-velocity clouds are windows into this hidden component of the galactic ecosystem. The Milky Way has a nuclear star cluster at its very center, a dense ball of millions of stars surrounding the supermassive black hole, one of the most extreme environments in the galaxy where stars orbit in a cosmic maelstrom. This cluster is distinct from the central bulge. It's much more compact, concentrated in the innermost few light years, a region where star density is millions of times higher than in the solar neighborhood. In the nuclear star cluster, stars are packed so tightly that the typical distance between them might be just a few light weeks. Still vast by solar system standards, but remarkably close compared to the light years that separate stars in the disk. In this dense environment, close encounters between stars become possible, and the gravitational interactions create a complex, dynamical system where stars can be flung into unusual orbits or even ejected from the cluster entirely. Many of the stars in the nuclear cluster are young and massive, which is puzzling because it's unclear how they formed there. The intense tidal forces from the supermassive black hole should make it difficult for gas clouds to collapse into stars in this region. One possibility is that the stars formed elsewhere and migrated inward through dynamical friction. Another is that they formed in a disk of gas around the black hole, protected from disruption by their collective gravity until they finished forming. The nuclear cluster also contains older stars, a population that's been there for billions of years, slowly orbiting the black hole. These stars have witnessed the galaxy's evolution from close range, circling the central black hole over and over, experiencing the intense gravitational environment at the galaxy's core. This central concentration of stars is common to many galaxies. Most large galaxies have nuclear star clusters, often accompanied by a supermassive black hole. The relationship between the two is still being studied. Did the cluster form first and later capture or grow a black hole? Or did the black hole form first and attract stars? Or did they co-evolve together? These are active areas of research, trying to understand how galactic centers assemble and evolve. Living in the nuclear star cluster would provide spectacular views if such a thing were possible. The night sky would be crowded with stars, far brighter and more numerous than from Earth. Dozens of stars would shine brighter than Venus, and the combined light from millions of nearby stars would create perpetual twilight. There would be no dark night, just a sky always glowing with stellar light, a permanently illuminated environment. But the radiation environment would be harsh. With so many massive stars in close proximity, the flux of ultraviolet light and stellar winds would be intense. The supermassive black hole, though currently quiet, occasionally flares when it consumes material, bathing the region in X-rays. And the gravitational environment is chaotic. Orbits are unstable over long timescales, and stars can be perturbed into crossing paths with the black hole or being ejected from the cluster. It's not a hospitable environment for planetary systems, at least not stable ones. The nuclear star cluster is the galaxy's inner sanctum, the densest concentration of stars, the closest approach to the central black hole that stars can sustain. It's a laboratory for studying stellar dynamics in extreme conditions, a window into processes that don't occur anywhere else in the galaxy, and a reminder that even in a galaxy of hundreds of billions of stars, the very center remains unique and extraordinary. Massive stars in the Milky Way produce stellar winds that blow at millions of miles per hour, carving bubbles in the interstellar medium, each massive star sculpting its surroundings before dying, shaping the galaxy's structure through the force of its radiation and expelled material. These winds are driven by radiation pressure, the force exerted by the star's intense light pushing on gas in the star's outer atmosphere. For the most massive stars, those tens or even 100 times the sun's mass, the radiation pressure is so intense it drives a continuous outflow of material. The star is essentially blowing itself apart, losing mass at rates that can reach a millionth of a solar mass per year or more. This might not sound like much, but over a few million years, the typical lifetime of a massive star, it adds up to a significant fraction of the star's total mass being expelled. These winds collide with the surrounding interstellar medium, creating expanding bubbles of hot, low-density gas. the stellar wind plows into the ambient gas, creating a shock front that heats the gas to millions of degrees. Inside the bubble, the gas is hot and diffuse, blown clear by the relentless wind. Outside, the gas is compressed into a dense shell, often visible as a glowing ring or filamentary structure in images. Multiple massive stars in a young cluster can create superbubbles, enormous cavities, hundreds of light years across, cleared out by the combined winds of many stars. When the most massive stars in the cluster explode as supernovae, they further energize the bubble, sometimes blowing holes in the galactic disk through which hot gas can escape into the halo. These processes regulate star formation. The winds and supernovae inject energy into the interstellar medium, heating it and dispersing gas clouds before they can collapse into new stars. This negative feedback limits how efficiently gas converts into stars. Without it, star formation would proceed much more rapidly, consuming the galaxy's gas in a fraction of the time it's actually taken. But winds also trigger star formation. The expanding shells of compressed gas can become unstable and collapse under their own gravity, fragmenting into clumps that form new stars. So massive stars both inhibit and promote star formation, creating a complex feedback loop that regulates the overall rate at which the galaxy produces new stars. The Sun produces a stellar wind too, though a much gentler one than massive stars. The solar wind is a stream of charged particles flowing outward at hundreds of kilometers per second, creating the heliosphere, a bubble of solar influence that extends beyond the orbit of Pluto. But compared to the winds from massive stars, the solar wind is a gentle breeze, barely noticeable against the hurricane-force gales that massive stars produce. These winds are also important for chemical enrichment. Massive stars produce heavy elements through fusion, and their winds carry these elements into the interstellar medium even before the star explodes. Wolf-Rayet stars, in particular, very massive stars that have lost their outer hydrogen layers, blow winds enriched with carbon, nitrogen, and oxygen, scattering these elements into space where they can be incorporated into future generations of stars and planets. So the interstellar medium is not passive, but actively shaped by the stars embedded in it. Massive stars carve out cavities, compress surrounding gas, heat the medium, and enrich it with heavy elements, all through the force of their winds and radiation. The galaxy is constantly being sculpted from within, reshaped by the very stars it contains. A self-modifying system where structure emerges from the collective action of billions of individual stars. The Milky Way exhibits a galactic fountain where gas is heated and expelled from the disk, then falls back down later, a cosmic breathing where material cycles out and in, driven by the energy released by supernova and massive stars. This process helps explain how gas moves vertically through the disk and how the galaxy maintains its chemical and energetic equilibrium. The mechanism begins with star formation in the disk. When massive stars form in clusters, their combined radiation and stellar winds heat the surrounding gas. When they explode as supernovae after just a few million years, they inject even more energy. All this energy heats the gas to temperatures of millions of degrees, causing it to expand rapidly, upward and downward out of the disk. This hot gas rises into the halo, propelled by the pressure from the continuous energy input below. As it rises, it cools, expanding into lower pressure regions, radiating energy, mixing with cooler gas in the halo. Eventually, it cools enough that it condenses back into clouds, which then fall back toward the disk under gravity, completing the cycle. The time scale for this fountain is millions to tens of millions of years. Gas is blown out, spends some time in the halo, then rains back down. During its journey, the gas can travel thousands of light years vertically, far above or below the thin disk where most stars reside. When it falls back, it can land in a different location from where it started, redistributing material across the galactic disk. This fountain has several important effects. It helps mix material, spreading heavy elements created in one region of the disk to other regions. It regulates star formation by removing gas from the disk temporarily, preventing all the gas from being converted to stars too quickly. And it helps maintain the thickness of the disk. The continuous circulation of gas prevents the disk from collapsing to an infinitesimally thin structure. Evidence for the galactic fountain comes from observations of high-velocity clouds, hot gas in the halo, and the distribution of different phases of the interstellar medium. X-ray observations reveal hot gas above and below the disk, consistent with the fountain model. Ultraviolet observations show absorption from gas at intermediate temperatures, likely gas in the cooling phase of the fountain. And radio observations of neutral hydrogen reveal clouds with vertical velocities, consistent with falling back toward the disk. The fountain is part of a larger picture of gas flows in galaxies. Gas doesn't just sit passively in the disk waiting to form stars. It's in constant motion, driven by stellar feedback, circulating through different phases and different regions of the galaxy. The Milky Way is a dynamic system with flows operating on multiple scales, from the small-scale turbulence in molecular clouds to the large-scale galactic fountain cycling material through the halo. This breathing, this cycle of expulsion and return, might be essential for sustaining star formation over cosmic time. Without the fountain, gas would either be consumed too quickly or remain locked in forms where it can't collapse into stars. The fountain helps maintain a balance, a steady state where gas is continuously being cycled through different phases, some of it forming stars, some being heated and expelled, some cooling and returning, creating the ongoing star formation that keeps the galaxy bright and alive. The Milky Way's rotation curve stays flat far beyond the visible disk, the clearest evidence that dark matter exists. Stars in the outer regions orbit at roughly the same speed as stars closer in, defying the expectations from the visible matter alone. This flat rotation curve was one of the first major clues that something invisible and massive pervades the galaxy. To understand why this is surprising, consider how planets orbit the Sun. Mercury orbits fast, Earth orbits slower. Neptune orbits much slower. There's a clear relationship where orbital velocity decreases with distance. This happens because the Sun's gravity weakens with distance, and objects farther out experience less gravitational pull, so they orbit more slowly. This is exactly what Newton's laws predict, and it's observed throughout the solar system. If the Milky Way's mass were concentrated at the center, we'd expect the same pattern. Stars close to the center orbiting fast, stars farther out orbiting slower. And indeed, this is what happens in the inner galaxy, where most of the visible matter is located. But beyond a certain radius, the rotation curve flattens. Orbital velocities stay roughly constant even as you go farther and farther out. This should be impossible if only visible matter were present. The stars in the outer disk are orbiting too fast. They should fly off into intergalactic space. The fact that they don't means there must be additional mass we can't see, providing extra gravitational pull to hold these outer stars in their orbits. This invisible mass must extend far beyond the visible disk, creating a gravitational potential that remains strong even at large distances. Measurements of the rotation curve come from observing gas and stars at various distances from the galactic center and measuring their orbital velocities through Doppler shifts. The result is unambiguous. The curve is flat out to the farthest distances we can measure, implying a dark matter halo that extends well beyond the visible galaxy. This observation has been replicated in hundreds of other galaxies. Flat rotation curves are the norm for spiral galaxies, suggesting that dark matter halos are a universal feature. The ratio of dark to visible matter varies, but the basic pattern is the same. Visible matter dominates in the inner regions, dark matter dominates in the outer regions, and overall total mass. The flat rotation curve tells us not just that dark matter exists, but something about its distribution. The dark matter can't be concentrated in a small central region. It must be in an extended halo, distributed smoothly throughout a large volume surrounding the galaxy. Models that fit the rotation curve suggest the dark matter density decreases gradually with distance, creating a halo that's much larger than the visible disk but less dense. Without the flat rotation curve and the evidence it provides for dark matter, our understanding of the universe would be fundamentally different. It's one of the key observations that forced us to accept that most of the matter in the universe is something we don't understand, something invisible and mysterious that makes its presence known only through gravity. The Milky Way's rotation curve is a window into this hidden majority, a measurement that reveals the invisible architecture supporting the visible cosmos. In 2020, astronomers discovered that the Milky Way's disk is rippling like water, possibly from a past collision. The ripples are so subtle it took analyzing millions of stars to see them, wrinkles in space recording ancient impacts. These ripples exist as vertical oscillations in the stellar disk, patterns where stars are systematically displaced above or below the midplane in waves that propagate across the galaxy. The discovery came from analyzing the three-dimensional positions and velocities of stars measured by the Gaia spacecraft. When astronomers mapped how stars were distributed vertically, how far they were above or below the galactic plane, they found patterns. Instead of a smooth distribution, there were corrugations, regions where stars were systematically higher or lower than expected, organized into wave-like structures. These ripples are thought to be the result of a perturbation. Something disturbed the disk, sending waves propagating through it like ripples, spreading across a pond after a stone is thrown in. The most likely culprit is the Sagittarius dwarf elliptical galaxy, which has passed through the Milky Way's disk multiple times over the past few billion years. Each passage sends a gravitational shock through the stellar distribution, exciting oscillations that persist for hundreds of millions of years. The ripples are remarkably coherent. They're not random fluctuations, but organized structures that extend across large portions of the disk. This coherence suggests they're the result of a specific event or series of events, not just the cumulative effect of many small disturbances. By studying the pattern of ripples, their wavelength, amplitude, phase, astronomers can work backward to constrain when and how the disturbance occurred. The discovery reveals that the galactic disk is more dynamic than previously thought. We tend to think of the disk as a stable structure, unchanging over millions of years. But the ripples show that the disk is responsive to perturbations, that it can support collective oscillations, that it has memory of past disturbances encoded in the motions of its stars. These ripples also provide a new way to probe the galaxy's mass distribution. How waves propagate through the disk depends on its properties, its mass, its thickness, the distribution of dark matter. By comparing observed ripples to theoretical models, astronomers can constrain these properties, using the disk's own oscillations as a diagnostic tool. There's something almost musical about this, the disk ringing like a drumhead, vibrations excited by past impacts still resonating through the structure. The galaxy has a natural frequency, modes of oscillation it prefers, and when disturbed it responds by oscillating in these modes, gradually damping over cosmic time, but leaving traces we can detect billions of years later. The ripples remind us that the Milky Way is not isolated, but interacts with its environment. The satellite galaxies orbiting the Milky Way aren't just passive companions. They disturb the disk, send waves through it, leave their marks on its structure. The galaxy we see today bears the scars of these interactions, written in the subtle motions of its stars, preserved in patterns that require sophisticated observations and millions of measurements to detect. The Gaia spacecraft has measured the positions and motions of over 1.8 billion stars with unprecedented precision, creating the most detailed three-dimensional map of the Milky Way ever made. A census of roughly 1% of the galaxy's stellar population, captured with extraordinary care. This represents one of the most ambitious astronomical surveys ever undertaken, transforming our understanding of the galaxy's structure, history, and evolution. Gaia achieves this by continuously scanning the sky, measuring each of its target stars dozens of times over several years. For the brightest stars, Gaia can measure positions to an accuracy of about 20 microarcseconds, roughly equivalent to measuring the width of a human hair from 1,000 kilometers away. This precision allows Gaia to detect not just where stars are, but how they're moving, measuring their proper motions, their apparent motion across the sky, and, for many stars, their distances and radial velocities as well. The result is a six-dimensional map, 3 dimensions of position, where the star is in space, and 3 dimensions of velocity, how it's moving. This complete phase space information allows astronomers to trace stellar orbits backward and forward in time, understanding where stars came from and where they're going, revealing the dynamical history of the galaxy. Gaia's data has led to numerous discoveries. It revealed the ripples in the galactic disk. It identified stellar streams from disrupted galaxies and clusters. It helped reconstruct the Gaia-Enceladus collision. It showed that the disk is warped and that the warp is more complex than previously thought. It discovered new satellite galaxies and star clusters. It measured the rotation curve to unprecedented accuracy. Each new data release brings fresh insights, as astronomers mine the catalog for patterns and anomalies. The catalog is also democratizing astronomy in a sense. It's publicly available, allowing anyone with the technical skills to download it and explore. Amateur astronomers, students, and professional researchers worldwide can access the same data, asking their own questions, making their own discoveries. The map belongs to everyone, a shared resource for understanding our galactic home. But 1.8 billion stars, as impressive as it sounds, is still only about 1% of the galaxy's total stellar population. The other 99% remain unmeasured, too faint, too distant, or too obscured by dust for Gaia to detect. The map is comprehensive but incomplete, a detailed view of our neighborhood and the brighter stars throughout the disk, but with vast regions still unexplored. Future missions might extend this map, pushing to fainter magnitudes, covering more of the sky, measuring more stars. But even with current data, Gaia has transformed galactic astronomy. Before Gaia, we had rough maps with millions of stars, positioned to modest accuracy. After Gaia, we have a precise census of billions of stars, each one measured carefully, their positions and motions recorded to extraordinary precision. It's the difference between a hand-drawn sketch and a high-resolution photograph, between guessing and knowing. The map will be used for decades, perhaps centuries, as a reference for stellar positions and motions. It's a snapshot of the galaxy in the early 21st century, a record of where the stars were and how they were moving at this particular moment in cosmic history. Future astronomers might compare new observations to Gaia's data, measuring how the galaxy has changed over the intervening time, using our catalog as a baseline for understanding future evolution. Scientists discovered in 2019 that our galaxy is warped like a potato chip, twisted at its edges. The warp is likely caused by the gravitational torque from the Magellanic Clouds, our galaxy being pulled out of shape by its orbiting companions. This discovery refined our understanding of the disk's three-dimensional structure and revealed that the Milky Way is more distorted than previous models suggested. The warp had been known about for decades, but its detailed structure was poorly understood. Earlier observations suggested a simple S-shaped warp, bending upward on one side and downward on the other. But the 2019 study using Cepheid variable stars as tracers revealed that the warp is more complex. It's twisted, with the orientation of the warp changing with distance from the galactic center. Imagine holding a flat disk and twisting it, like wringing out a towel. The inner parts remain relatively flat, but the outer parts twist upward on one side and downward on the other. And the axis of this twist itself rotates as you move outward. That's what the Milky Way's warp looks like. A progressively twisted structure where the outer disk deviates increasingly from the plane defined by the inner disk. The Magellanic Clouds are the likely culprits. These two satellite galaxies, particularly the large Magellanic Cloud, which contains about 10 billion solar masses, exert significant gravitational pull on the Milky Way's disk. As they orbit, they create a tidal force that torques the disk, pulling it out of alignment and creating the warp we observe. Computer simulations support this interpretation. When you model the Milky Way with the Magellanic Clouds orbiting around it, the disk naturally develops a warp that matches observations. The warp is a dynamic feature responding to the changing gravitational environment as the clouds orbit, slowly precessing, rotating, over timescales of hundreds of millions of years. The discovery also revealed that our understanding of where we are in the galaxy needed refinement. The Sun's position relative to the galactic midplane depends on how you define that midplane. If the disk is warped, then the midplane is different at different locations. Recent measurements suggest the Sun is currently about 60 light-years above the midplane, but this number depends on accounting for the warp correctly. The warp extends to the very edges of the galactic disk, affecting stars and gas tens of thousands of light-years from the center. It's not a subtle effect in the outer regions. The disk can deviate from the inner plane by thousands of light-years, a dramatic departure from flatness. Yet from our embedded position, the warp is difficult to perceive directly. We see its effects on stellar and gas distributions, but we can't step outside to view the warped structure from afar. This warping is common in spiral galaxies. Many show similar features, suggesting that interactions with satellites or the cosmic web of surrounding matter regularly distort galactic disks. The Milky Way is not unusual in being warped. If anything, a perfectly flat disk might be the exception rather than the rule. Galaxies are flexible structures, responsive to their gravitational environment, shaped by forces that extend far beyond their visible boundaries. The coldest known place in the galaxy is the Boomerang Nebula, where temperatures drop to just 1 degree above absolute zero. It's even colder than the cosmic background radiation, an island of extreme cold in a galaxy of burning stars. This nebula, about 5,000 light-years away in the constellation Centaurus, achieves this extreme temperature through a process involving the expansion of gas from a dying star. The Boomerang Nebula is a planetary nebula, a shell of gas expelled by a red giant star in its final stages of evolution. As the star shed its outer layers, the gas expanded rapidly into space, and this expansion caused extreme cooling, much like how compressed air cools when released from a spray can. The expanding gas has cooled to approximately 1 Kelvin, 272.15 degrees C, or 457.7 degrees C, making it the coldest naturally occurring location we've found in the universe. For comparison, the cosmic microwave background, the afterglow of the Big Bang that pervades all of space, has a temperature of about 2.7 Kelvin. The Boomerang Nebula is colder than this universal background, which seems impossible at first. How can something be colder than the ambient temperature of the universe? The answer is that the expansion of the gas has cooled it faster than it can be reheated by absorbing radiation from the cosmic background. It's out of equilibrium with its environment, temporarily achieving a temperature below the universal floor. This extreme cold won't last forever. Over time, the nebula will absorb radiation from surrounding space and from the central star, gradually warming up. Eventually, it will reach equilibrium with the cosmic background radiation, settling into the same temperature as the rest of intergalactic space. But for now, for a cosmically brief moment, it remains the coldest spot we know of. The central star of the Boomerang Nebula is evolving rapidly, transitioning from a red giant to a white dwarf. This transition happens quickly, over just a few thousand years, and the planetary nebula phase is even briefer. In perhaps 10,000 years, the nebula will have dispersed, its gas mixed back into the interstellar medium, and the extreme cold will be gone. We're observing it during a fleeting phase, a temporary state in the death of a sun-like star. Studying the Boomerang Nebula helps astronomers understand the late stages of stellar evolution and the physics of extremely cold gas. At 1 Kelvin, quantum effects become important. The gas doesn't behave classically, but follows quantum mechanical rules. Molecules are in their lowest energy states, moving sluggishly, barely vibrating. It's as close to absolute stillness as matter can get, a state where thermal energy is almost completely absent. There's something paradoxical about the Boomerang Nebula being the coldest place in the galaxy while also being heated by a dying star at its center. The star is hot, tens of thousands of degrees, but its expelled gas has expanded and cooled to near absolute zero. Life and death, heat and cold, all coexisting in the same structure, a reminder that the universe contains extremes in close proximity, that temperature is not a simple gradient, but can vary wildly over small distances, depending on the processes at work. In 2022, astronomers detected a star orbiting Sagittarius A in just 4 years, the fastest orbital period ever observed. The star, called S474, experiences such extreme gravity. It tests Einstein's theory of general relativity with every orbit. Actually, to correct the record, S4714 has an orbital period of about 12 years, but S4714 still represents one of the most extreme orbits known, with closest approaches to the black hole that bring it to within about 1.9 billion kilometers, roughly the distance from the Sun to Uranus. At its closest approach, S4714 reaches velocities of about 8% the speed of light, roughly 24,000 kilometers per second. At these speeds, relativistic effects are pronounced. Time dilation becomes significant. A clock on S4712 would run measurably slower than a clock farther from the black hole. The star's light is gravitationally redshifted, its wavelengths stretched by the intense gravitational field. And the orbit precesses, the ellipse rotates slowly over time, exactly as general relativity predicts. These S-stars are natural laboratories for testing general relativity. The gravitational field they experience is millions of times stronger than anything in the solar system, where general relativity's effects are tiny corrections to Newtonian gravity. Near Sagittarius A, general relativity's predictions differ significantly from Newton's, and observations can test which theory is correct. So far, general relativity has passed every test. The observed precession matches predictions. The gravitational redshift matches predictions. The star's orbits follow the trajectories that general relativity says they should, with no deviations detected. If general relativity were wrong, if it needed modification in strong gravitational fields, the S-stars would reveal it. But they don't. Einstein's theory, formulated over a century ago, continues to accurately describe nature even in these extreme conditions. The discovery of stars in such tight orbits also helps constrain the properties of Sagittarius A. By measuring the star's orbits, astronomers can determine the black hole's mass with high precision, about 4.1 million solar masses. They can also constrain the black hole's spin, though this is more difficult and requires longer observation baselines. And they can search for other massive objects near the black hole. If there were an intermediate mass black hole or a cluster of stellar mass black holes nearby, they would perturb the S-star's orbits in detectable ways. Living on a planet orbiting S474 would be a surreal experience, if such a thing were possible. The sky would change dramatically over the course of the 12-year orbit. At closest approach to the black hole, The sky would be filled with the glow from hot gas in the accretion disk and the relativistically beamed light from matter spiraling inward. The night sky would be warped by gravitational lensing, with background stars appearing in strange positions, their light bent by the black hole's gravity. Time itself would behave oddly. Clocks would run slower than those on a planet farther out, and communication with the rest of the galaxy would be subject to significant time dilation effects. But of course, no planets could survive in such an orbit. The tidal forces would be enormous, and the radiation environment would be lethal. The S-stars are likely too young to have planets anyway. They're massive stars with lifetimes of just a few million years, not enough time for complex planetary systems to develop and stabilize. They exist in this extreme environment as cosmic test particles, their orbits measured and analyzed not for their own sake, but for what they reveal about the black hole they orbit and the fundamental laws of physics that govern their motion. Recent observations suggest there might be thousands of black holes wandering through the galactic center. Stellar mass black holes that have sunk toward the center over time, creating an invisible graveyard around the supermassive black hole. These are the remnants of massive stars that formed, lived, and died in the central regions of the galaxy, their cores collapsing into black holes that now orbit invisibly in the dense stellar environment. When a massive star near the galactic center explodes as a supernova, if the core is massive enough, it collapses into a black hole rather than a neutron star. This black hole inherits the orbital motion of its progenitor star, continuing to orbit the galactic center, but now invisible, detectable only through its gravitational effects. Over millions of years, these stellar mass black holes sink toward the center through a process called dynamical friction. As they orbit, they gravitationally interact with nearby stars, transferring momentum. The net effect is that the black holes lose energy and spiral inward, gradually migrating toward the region around Sagittarius A. This process is more efficient for more massive objects, so black holes, which are typically more massive than stars, sink faster. The result should be a population of stellar mass black holes concentrated in the central regions of the galaxy, creating a cusp of black holes around the supermassive black hole. Estimates suggest there could be thousands to tens of thousands of such black holes in the central parsec, a region just a few light years across, making it one of the densest concentrations of black holes in the galaxy. These black holes are mostly invisible. Unlike the supermassive black hole, which has an accretion disk and occasionally flares, most stellar mass black holes in the galactic center are isolated, not accreting material, not producing radiation. They're purely gravitational objects, affecting their surroundings only through their mass, but occasionally one might reveal itself. If a stellar mass black hole passes close to a star, it can strip material from the star through tidal forces. This material forms an accretion disk around the black hole, heating up and emitting X-rays as it spirals inward. Astronomers have detected several X-ray binaries near the galactic center, systems where a black hole or neutron star is accreting from a companion star, and these might represent the visible tip of a much larger population of black holes lurking unseen. The population of black holes affects the dynamics of the galactic center. they contribute to the overall gravitational potential, influencing how stars orbit. They can scatter stars through close encounters, changing stellar orbits, and heating the stellar distribution. And when two black holes happen to pass close to each other, they can merge, producing gravitational waves, ripples in space-time that propagate outward at the speed of light. Detecting gravitational waves from these mergers is an active area of research. The LIGO and Virgo detectors have found gravitational waves from merging black holes, though most of these are likely from black holes in less dense environments. Future detectors like LISA will be sensitive to the lower frequency gravitational waves produced by more massive black holes, potentially detecting mergers in galactic centers like ours. The galactic center is, in a sense, a black hole graveyard, a collection point for the remnants of massive stars. An invisible population of compact objects dominating the mass distribution in the central region. It's a reminder that what we can see is only part of the story, that much of the galaxy's mass and many of its most extreme objects remain hidden, detectable only through their gravitational influence on the objects around them. The Milky Way's central bar may have formed as recently as a few billion years ago. Our galaxy's structure is not static, but evolving, changing on timescales we're only now learning to measure. This suggests that the Milky Way we see today is not the Milky Way of the distant past, and won't be the Milky Way of the far future. The galaxy is a work in progress, continuously reshaping itself. Galactic bars form through gravitational instabilities in rotating disks. When a disk becomes massive enough and has the right velocity distribution, it can spontaneously develop a bar-shaped perturbation. This bar then reinforces itself. The enhanced gravity in the bar attracts more matter, strengthening the bar, which attracts even more matter. The process is self-amplifying until the bar reaches a stable configuration. But bars aren't necessarily permanent. Simulations show that bars can dissolve if conditions change. For instance, if a galaxy accretes a lot of gas, or if the central mass concentration changes, or if the galaxy experiences a major merger. Some galaxies show evidence of having had bars that later dissolved. The bar is a phase in galactic evolution, not necessarily a permanent fixture. In the Milky Way's case, evidence suggests the bar is relatively young. Studies of stellar ages in the bar region show populations that are younger than the galaxy as a whole, suggesting the bar formed after many of the disk stars. The bar's current orientation and pattern speed, how fast it rotates, are consistent with the feature that formed within the last few billion years, rather than being as old as the disk itself. If the bar formed recently, this has implications for the galaxy's history. The formation of the bar would have reorganized stellar orbits throughout the disk, moving stars from their original locations to new ones. It would have affected gas flows, channeling gas toward the center, and possibly triggering bursts of star formation. It might have influenced the migration of planetary systems, including possibly the Sun's orbit. The bar's formation might even be linked to the Gaia-Enceladus merger 10 billion years ago. That major collision would have disturbed the disk, and the subsequent settling might have created conditions favorable for bar formation. Alternatively, the bar might have formed more recently due to internal instabilities as the disk evolved. The exact timing and trigger are still being studied. What's certain is that the Milky Way is not unchanging. The bar is evidence that large-scale restructuring can occur even in a mature galaxy. In the future, the bar might dissolve, or it might persist for the rest of the galaxy's life. When the Milky Way merges with Andromeda, the bar will certainly be destroyed, as both galaxies' structures are disrupted and blended. The bar is a transient feature on cosmic timescales, part of the galaxy's current configuration, but not a permanent aspect of its identity. Astronomers have found over 4,000 exoplanets in the Milky Way, with estimates of 100 billion planets or more. Nearly every star has planets, making our galaxy not just a collection of suns, but a vast population of worlds. This discovery has transformed our understanding of planetary systems from rare exceptions to common outcomes of star formation. The first confirmed exoplanet around a sun-like star was discovered in 1995. Before that, planets beyond our solar system were theoretical. We expected them to exist, but we had no proof. The 1995 discovery opened the floodgates. Better detection techniques, dedicated space missions like Kepler and TESS, and ground-based surveys have since found thousands of exoplanets, with more being discovered regularly. These planets come in astonishing variety. Hot Jupiters orbit closer to their stars than Mercury orbits the Sun. Their atmospheres heated to thousands of degrees. Super-Earths, rocky planets larger than Earth but smaller than Neptune, are common, representing a class of planet that doesn't exist in our solar system. Mini-Neptunes, ice giants, lava worlds, water worlds. The diversity of exoplanets far exceeds what we find in our own system. Many of these planets orbit in systems very different from ours. Some have highly eccentric orbits, swooping close to their star and then swinging far out. Some orbit binary stars, experiencing complex gravitational dynamics as they circle two suns. Some are in resonant configurations, where orbital periods are simple ratios, creating patterns of alignment that repeat over time. The estimate of 100 billion planets comes from extrapolating from the known exoplanet population. Surveys like Kepler observed a small patch of sky, found thousands of planets, and then astronomers scaled up to estimate how many planets exist throughout the galaxy. The result, roughly one planet per star on average, with many stars hosting multiple planets. This means the Milky Way contains more planets than stars, a population of worlds that far exceeds our ability to study individually. Most of these planets we'll never directly observe. They're too far away, too faint, too difficult to separate from their star's glare. We detect them indirectly, through the transit method, where the planet passes in front of its star and dims the light slightly, or through radial velocity, where the star wobbles due to the planet's gravitational pull. Only a handful of exoplanets have been directly imaged, and these are mostly young, massive planets orbiting far from their stars, where they can be distinguished from the stellar glare. But even indirect detection tells us a lot. We can measure a planet's size, mass, orbital period, and distance from its star. For transiting planets, we can analyze starlight passing through the planet's atmosphere, detecting the chemical signatures of molecules like water, methane, or oxygen. We're beginning to characterize not just that planets exist, but what they're like, their compositions, their atmospheres, their potential habitability. The abundance of planets has profound implications for the search for life. If planets are common, and rocky planets in habitable zones are a significant fraction, then potentially habitable worlds number in the billions in our galaxy alone. The universe might be teeming with planets where life could emerge, where evolution could unfold, where perhaps intelligence could develop, or perhaps we're alone despite the abundance of worlds. The planets are there. The question of life remains open. In 2019, astronomers captured the first image of the shadow of Sagittarius A, confirming it's a supermassive black hole. The image required coordinating radio telescopes across Earth, turning our entire planet into a single cosmic eye. This achievement represented decades of technological development, international collaboration, and patient observation, culminating in a direct visual confirmation of the black hole at our galaxy's heart. The image, released in May 2022, the observation was in 2017, shows a bright ring of emission surrounding a dark central region, the black hole's shadow. This shadow is about 52 microarcseconds across on the sky, roughly the size of a donut on the moon as seen from Earth. Resolving such a tiny angular size requires a telescope with a diameter comparable to Earth itself. No single telescope that large exists, but the Event Horizon Telescope, EHT, used a technique called Very Long Baseline Interferometry, VLBI, to effectively create an Earth-sized telescope. Multiple radio telescopes around the world observed Sagittarius A simultaneously, and their data was combined to create an image with resolution equivalent to a single telescope the size of the planet. This required exquisite timing. The observations had to be synchronized to billionths of a second using atomic clocks, and massive data processing, combining petabytes of data from different telescopes. The resulting image confirmed what decades of indirect evidence had suggested. Sagittarius A is a supermassive black hole with properties that match general relativity's predictions. The shadow size agrees with the expected size for a 4 million solar mass black hole. The asymmetry in the ring, one side brighter than the other, is due to Doppler boosting, where gas moving toward us appears brighter due to relativistic effects. Everything about the image is consistent with a rotating black hole accreting material from its surroundings. This was the second black hole ever imaged. The first was M87 TUG, the supermassive black hole in the galaxy M87, imaged in 2019. Sagittarius A was actually harder to image despite being much closer, 26,000 light-years versus 55 million light-years for M87 TUG. The reason is that Sagittarius A is much smaller, and the material around it orbits faster, completing a circuit in just minutes. During the hours of observation, the accretion flow changed significantly, making it harder to construct a stable image. The achievement represents a pinnacle of observational astronomy. Using the combined power of radio telescopes across the globe, advanced algorithms to process the data, and decades of theoretical work to interpret what we're seeing. It's a direct view of the event horizon environment, the closest we can get to seeing a black hole itself. The black hole remains invisible. We're seeing its shadow against the glowing background of hot gas. But that shadow is unmistakable proof of the black hole's existence. Future observations will refine the image, perhaps capturing changes in the accretion flow over time, measuring the black hole's spin more precisely, or detecting features like jets that might occasionally form. The EHT continues to observe, and more telescopes are being added to the array, improving resolution and sensitivity. The first image is a beginning, not an end, a proof of concept that such observations are possible, opening a new window onto the most extreme environments in the universe. The Milky Way is part of the local group of galaxies, which is itself part of the larger Virgo supercluster. Each level of structure nests within the next, galaxies within groups, within clusters, within superclusters, cosmic Russian dolls extending to the largest scales in the universe. This hierarchical structure reflects how gravity has organized matter since the Big Bang, building structure from the bottom up. The local group contains about 80 known galaxies, though most are small dwarf galaxies. The two dominant members are the Milky Way and Andromeda, with the Triangulum galaxy, M33, as a smaller but still significant member. These three spirals, along with their satellite galaxies, account for most of the local group's mass. The entire group spans about 10 million light years and is bound together by mutual gravitational attraction. Beyond the local group lies the Virgo cluster, a much larger collection of galaxies about 65 million light-years away, containing over 1,500 galaxies. The Virgo cluster is the dominant gravitational feature in our region of the universe, and the local group is actually falling toward it, pulled by its immense gravity. We're moving toward Virgo at about 200 kilometers per second, a motion that will continue for billions of years, though we'll never actually reach it because the expansion of the universe is carrying us away at the same time. The Virgo cluster, in turn, is part of the larger Virgo supercluster, a structure spanning about 110 million light-years, containing tens of thousands of galaxies. This is one of millions of superclusters in the observable universe, each one a concentration of galaxy clusters arranged in filaments and sheets surrounding vast voids where few galaxies exist. Recent mapping efforts have revealed even larger structures. The Laniakea supercluster, defined in 2014, contains the Virgo supercluster and several neighboring superclusters, spanning about 520 million light-years. Laniakea, which means immense heaven in Hawaiian, contains about 100,000 large galaxies and has a total mass of about 100 million billion suns. The Milky Way sits on the outskirts of this enormous structure. This nested hierarchy reflects how structure formed in the universe. Quantum fluctuations in the early universe were amplified by cosmic inflation, creating slight overdensities in the matter distribution. Gravity amplified these overdensities. Denser regions attracted more matter, becoming denser still. Over billions of years, this process created the cosmic web, filaments of galaxies surrounding vast voids with clusters at the intersection of filaments and superclusters spanning the largest scales. The Milky Way's address, then, is nested: Earth, Solar System, Orion Spur, Milky Way, Local Group, Virgo Supercluster, Laniakea Supercluster, the Cosmic Web. Each level is embedded in the next, each one shaped by gravity and the large-scale distribution of matter, all the way up to the observable universe itself, the final container that holds everything we can in principle observe. Understanding this hierarchy changes our perspective on cosmic significance. The Milky Way is vast by human standards, but tiny compared to superclusters. It's gravitationally bound to its local group neighbors, but disconnected from most of the universe due to cosmic expansion. We inhabit a small corner of a small group in a small part of a supercluster that's itself just one among millions. The universe is structured at scales far beyond anything we can directly experience, nested layers of organization extending to distances light has barely had time to cross since the universe began. scientists discovered vast lobes of hot gas extending above and below the galactic plane, possibly from past black hole activity. These Erosita bubbles suggest our galaxy's center was once far more violent, perhaps when the black hole feasted more greedily. These structures were discovered in 2020 by the Erosita X-ray telescope and roughly align with the Fermi bubbles discovered a decade earlier, but they're larger and detected at different energies. The Erosita bubbles extend about 45,000 light-years from the galactic center, spanning a significant fraction of the galaxy's diameter. They're filled with hot gas at temperatures of several million degrees, emitting X-rays that reveal their presence. The symmetry of the bubbles, one extending above the disk, one below, suggests they were created by a single energetic event or series of events centered on the galactic nucleus. The leading explanation is that these bubbles were inflated by activity from Sagittarius A several million years ago. During this active period, the black hole might have consumed a significant amount of material, perhaps a gas cloud, or even a smaller black hole or star that wandered too close. This feeding frenzy would have released enormous amounts of energy, some of it channeled into jets perpendicular to the accretion disk. These jets, blasting outward at nearly the speed of light, would have plowed through the surrounding gas, pushing it aside and creating the cavities we now see as the Erosita bubbles. The process would have been similar to how radio galaxies create lobes of emission through their jets, but on a smaller scale and now mostly inactive. The bubbles we observe are the remnants of this activity, still hot and glowing in X-rays, even though the jets have long since shut off. An alternative or complementary explanation involves star formation. A burst of intense star formation in the galactic center could have produced numerous massive stars, which then exploded as supernovae in quick succession. The combined energy from these explosions could have driven a galactic wind, blowing hot gas outward and creating the bubbles. This scenario doesn't require the black hole to have been active, just a period of unusually intense stellar activity. The truth might involve both processes. Star formation could have driven gas toward the center, feeding the black hole, which then produced jets that further energized the outflow. The two mechanisms working together could create larger, more energetic bubbles than either process alone. The discovery of the Erosita bubbles reinforces the idea that the galactic center has been more active in the recent past than it is today. The bubbles are relatively young, a few million years old perhaps, which is recent on galactic timescales. This suggests that Sagittarius A goes through cycles of activity and quiescence, quiet for long periods, and then briefly rousing to consume material before settling back into dormancy. These bubbles also affect the galaxy's ecology. The hot gas they contain was blown out of the disk, removing it from the reservoir available for star formation. The energy they represent, enough to create and maintain such enormous structures, came at the expense of other processes. When the galactic center is active, it can regulate star formation throughout the galaxy by heating and expelling gas that might otherwise collapse into new stars. The Erosita bubbles are visible reminders that the galaxy is not a static backdrop, but an active system with its own weather, its own cycles of activity. The center occasionally erupts, blasting energy and material into the halo, then quiets down again, leaving behind structures that glow for millions of years, before fading into the background. We're observing the aftermath of such an eruption, a cosmic belch that happened millions of years ago, its effects still visible in the X-ray sky. The Milky Way is currently absorbing the Sagittarius dwarf elliptical galaxy, a slow-motion collision happening now. This dwarf galaxy has orbited through the Milky Way's disk several times, being pulled apart strand by strand like cotton candy. The process has been ongoing for billions of years, and within another billion years or so, the Sagittarius dwarf will cease to exist as a distinct entity, its stars fully integrated into the Milky Way's halo. The Sagittarius dwarf was discovered in 1994, making it one of the more recent discoveries, despite being relatively close. It's about 70,000 light-years from the Sun but hidden behind the dense star fields of the galactic bulge, making it difficult to detect against the background. Once identified, astronomers traced its orbital history and realized it's in the process of being tidally disrupted. Each time the dwarf galaxy orbits through the Milky Way's disk, tidal forces, the differential gravitational pull across the galaxy's extent, stretch it, pulling stars away from the front and back. These stripped stars don't disappear. They continue orbiting, but now as part of long streams that wrap around the Milky Way. The Sagittarius stream has been mapped, wrapping around the galaxy multiple times, a ribbon of stars marking the dwarf galaxy's orbital path. Computer simulations can reconstruct this process by modeling the dwarf galaxy's orbit and the tidal forces it experiences. Astronomers can trace where stripped stars should be and compare to observations. The match is excellent. The observed streams align with predictions, confirming our understanding of how the disruption is occurring. The Sagittarius dwarf has contributed significantly to the Milky Way's stellar halo. Some estimates suggest that as much as 1/3 of the halo stars in certain regions came from this single dwarf galaxy. In a sense, a significant fraction of the Milky Way's outer structure is recycled Sagittarius dwarf, its identity as a separate galaxy gradually being erased as its stars are scattered and mixed with the general halo population. This process is not unique. It's happening to other satellite galaxies as well, though Sagittarius is the most prominent current example. The Canis Major dwarf, if it's confirmed to be a separate galaxy rather than part of the disk, is also being disrupted. The Magellanic Clouds might eventually meet a similar fate, though they're more massive and will take longer to consume. Watching this disruption gives us a real-time view of how galaxies grow through accretion. We're seeing the process that has been occurring throughout cosmic history. Larger galaxies consuming smaller ones, building up their mass piece by piece. The Milky Way's current mass is the sum of its original formation, plus all the smaller galaxies it's absorbed over billions of years. And Sagittarius is one of the most recent additions to that tally. There's something melancholic about watching a galaxy die, even a small one. The Sagittarius dwarf was once an independent structure, its stars gravitationally bound together, orbiting in a coherent whole. Now it's being pulled apart, its stars scattered, its identity dissolving into the larger structure of the Milky Way. Its stars continue. They haven't been destroyed, but they're no longer part of a galaxy. They've become immigrants, former citizens of Sagittarius, now residents of the Milky Way. Their origin recorded only in their orbits and chemical compositions. Recent studies show that spiral galaxies like the Milky Way stop forming stars from the outside in, like a fire dying at its edges. The outer regions run out of gas first, while the center continues to birth new stars, a gradual dimming across billions of years. This process, called galaxy quenching, is one of the ways galaxies transition from active, star-forming systems to passive, quiescent ones. The mechanism involves the availability of gas. Star formation requires cold, dense gas that can collapse under its own gravity. In the outer regions of galaxies, this gas is more susceptible to being heated and expelled by stellar feedback, supernova explosions, and stellar winds that inject energy into the interstellar medium. The lower gas density in the outer disk means that once gas is heated or expelled, it's harder to replace, and star formation gradually ceases. In the inner regions, gas density is higher, and the gravitational potential is deeper, making it easier for gas to accumulate and resist being expelled. Star formation can continue in the center even after it's ceased in the outskirts. Over time, the star-forming region shrinks inward, like a pond drying from its edges toward the center. Observations of nearby galaxies at different stages of this process confirm the pattern. Younger galaxies show star formation throughout their disks. Older galaxies show star formation concentrated in the center, with the outer regions dominated by old, red stars that indicate star formation ceased there long ago. The Milky Way is somewhere in the middle, still forming stars throughout its disk, but with the outer regions showing lower star formation rates than the inner regions. This outside-in quenching has implications for the long-term evolution of the galaxy. Eventually, if no new gas is accreted, star formation will cease everywhere. The galaxy will transition from a blue, star-forming spiral to a red, quiescent spiral or elliptical, depending on whether it merges with other galaxies in the meantime. The stellar population will age, and without new stars to replace those that die, the galaxy will gradually fade. But this process takes a very long time, billions of years at current rates. The Milky Way still has substantial gas reserves and is still accreting gas from its surroundings, so star formation will continue for billions of years yet. The outside-in decline is happening, but slowly, imperceptibly on human timescales, a gradual evolution that spans epochs. The pattern also affects where in the galaxy you might find different types of stars and planetary systems. The outer regions are increasingly dominated by older stars, formed long ago when gas was still abundant there. The inner regions contain a mix of old and new stars, with ongoing star formation adding fresh stellar populations. If you were searching for young planetary systems with newly formed worlds, you'd look toward the inner galaxy. If you wanted old, stable systems where life had billions of years to evolve, the outer regions might be better candidates. This outside-in star formation decline is part of the larger story of cosmic evolution, how structures form, mature, and eventually fade. Galaxies aren't eternal engines of star formation, but have finite lifetimes of activity, eventually exhausting their fuel and settling into quiescence. The Milky Way is still in its active phase, but the clock is running, and eventually, in the distant future, the galaxy will go quiet. Its star formation ceased, its stellar population aging gracefully into the cosmic twilight. The Milky Way's stellar halo contains some of the most metal-poor stars known, pristine remnants from the early universe. These ancient stars are like time capsules, their composition revealing what the universe was like before heavy elements existed. Some have metallicities 1/10,000th that of the Sun, meaning they formed from gas that had been enriched by only a few supernovae. These stars are called population 2 or even population 3 candidates, though no confirmed population 3 stars have been found yet. They're characterized by very low abundances of elements heavier than helium: iron, carbon, oxygen, silicon, all present in trace amounts compared to younger stars. This low metallicity tells us they formed very early, from gas that hadn't been through many cycles of stellar processing. Finding these stars requires dedicated surveys. They're faint, scattered throughout the halo, and rare compared to more metal-rich stars. Projects like the Hamburg ESO survey, the Pristine survey, and observations with large telescopes like the Very Large Telescope and Keck have identified hundreds of metal-poor candidates. Spectroscopic follow-up can measure their detailed compositions, revealing not just overall metallicity, but the abundances of individual elements. These abundance patterns are particularly informative. The ratios of different elements, carbon to iron, oxygen to magnesium, etc., depend on what kinds of supernovae enriched the gas they formed from. Core collapse supernovae from massive stars produce different element ratios than type Ia supernovae from white dwarf explosions. By measuring these ratios, astronomers can reconstruct the early history of star formation and nucleosynthesis in the protogalaxy. Some metal-poor stars show unusual abundance patterns that suggest they formed from gas enriched by a single supernova or a small number of supernovae. These stars preserve the chemical signature of individual stellar explosions from over 13 billion years ago, frozen in their atmospheres like fossils in amber. Studying them is the closest we can come to observing the first generations of stars, even though those first stars themselves are long gone. The most metal-poor star yet discovered is SMSS J031300-66708-393, with an iron abundance about 100,000,000th that of the Sun, essentially no iron at all. This star likely formed from gas enriched by a single, unusual supernova that produced very little iron but significant amounts of lighter elements, like carbon and oxygen. It's a second-generation star at most, perhaps even the direct descendant of one of the universe's first stars. These ancient stars also provide constraints on theoretical models of the first stars. Population 3 stars, the very first generation formed from pristine Big Bang gas, are predicted to have been very massive, hundreds of times the Sun's mass, burning bright and dying young in pair instability supernovae. These explosions would have had distinctive nucleosynthetic signatures. By comparing metal-poor star abundances to theoretical predictions, astronomers can test models of how the first stars lived and died. The continued existence of these metal-poor stars is somewhat remarkable. They're low-mass stars, red dwarfs, or stars similar to the Sun, which is why they've survived for 13 billion years. More massive stars from the same generation died long ago. These survivors are the smallest, faintest members of their generation, still shining dimly in the halo, carrying in their atmospheres the primordial chemistry of the early universe, patiently waiting for us to find them and read the history they preserve. Astronomers have detected mysterious, fast radio bursts coming from various locations in the galaxy, These millisecond flashes of radio energy are still poorly understood. Enigmatic signals from processes we're only beginning to explain. Most fast radio bursts, FRBs, come from distant galaxies billions of light years away, but a few have been detected from sources within the Milky Way, allowing closer study. The first galactic FRB was detected in 2020 from a magnetar, a neutron star with an incredibly strong magnetic field, called SGR 1935+2154. The burst lasted just a few milliseconds but released as much energy as the Sun emits in several days, all concentrated in radio wavelengths. The simultaneous detection of an X-ray burst from the same source confirmed the magnetar as the origin. This discovery was significant because it established that at least some FRBs come from magnetars, settling a debate about their origins. Magnetars are neutron stars with magnetic fields a quadrillion times stronger than Earth's. These extreme fields can occasionally reconfigure catastrophically, releasing enormous amounts of energy in the process. When this happens, the magnetar produces bursts of emission across multiple wavelengths, including the radio bursts we detect as FRBs. But not all FRBs may have the same origin. The extragalactic FRBs show diverse properties. Some repeat, others appear to be one-time events. Some are associated with specific types of galaxies. Others seem to occur in various environments. This diversity suggests there might be multiple mechanisms that can produce FRB-like signals, with magnetars being one, but perhaps not the only source. The galactic FRB from SGR 1935+2154 was much weaker than typical extragalactic FRBs, which raised interesting questions. If all FRBs are produced by magnetar flares, why are the ones from distant galaxies so much more energetic? Perhaps we're observing selection effects. We only detect the most powerful bursts from distant galaxies, while weaker bursts go unnoticed. Or perhaps the distant FRBs are produced by a more energetic version of the same process. Magnetars in particularly extreme states. FRBs have potential uses beyond understanding their origins. Because radio waves passing through ionized gas experience dispersion, different frequencies travel at different speeds, the amount of dispersion in an FRB signal tells us how much ionized material the waves pass through. This can be used to probe the intergalactic medium, the diffuse gas between galaxies, providing information about its density and distribution. The study of FRBs is still in its early stages. Hundreds of bursts have been detected, but we're still cataloging their properties, searching for patterns, trying to understand what they tell us about the extreme physics that produces them. Some might come from magnetars, some from other neutron star processes, some possibly from more exotic scenarios, like colliding neutron stars or black hole interactions. For the Milky Way, FRBs from our own magnetars provide opportunities to study these events in detail, impossible for distant sources. We can observe the source before and after the burst, measure its properties across multiple wavelengths, correlate the radio burst with other emissions. Each galactic FRB is a rare opportunity to observe extreme physics in action. Neutron star magnetic fields undergoing catastrophic reorganization, releasing in milliseconds energy that would power human civilization for millions of years. We don't fully understand what causes spiral arms to form and persist in galaxies like the Milky Way. Despite decades of study, the exact mechanism remains debated, a reminder that even nearby structures hold mysteries. The density wave theory explains many observations, but questions remain about how the waves are generated and maintained over cosmic time. The basic puzzle is this: if spiral arms were material structures rotating with the disk, differential rotation would wind them up tightly within a few galactic rotations, and they'd disappear. But observed spiral galaxies have well-defined arms that persist for billions of years. The density wave theory solves this by making the arms patterns rather than material structures, but it doesn't fully explain where the patterns come from or what maintains them. Several mechanisms might contribute. The galactic bar, if present, can drive spiral structure through resonances. Specific distances from the center, where the orbital frequency of stars matches the bar's pattern frequency. At these resonances, small perturbations can amplify into large-scale structures. The bar effectively forces the disk to adopt a spiral pattern, the way a tuning fork forces nearby air to vibrate at its frequency. Self-gravity might also play a role. The disk can sustain spiral density waves as self-gravitating oscillations, similar to sound waves in air. These waves can grow from small perturbations, irregularities in the mass distribution, disturbances from satellite galaxies, or quantum fluctuations amplified over billions of years. Once established, they can persist as long-lived modes in the disk. Tidal interactions with satellite galaxies can trigger or enhance spiral structure. When a satellite passes by, its gravity perturbs the disk, exciting waves that propagate and organize into spiral patterns. The Magellanic Clouds might contribute to the Milky Way's spiral structure through their gravitational influence, their passages stirring the disk and reinforcing the arms. Gas dynamics adds another layer of complexity. Gas, unlike stars, can dissipate energy through collisions, allowing it to respond differently to spiral perturbations. Gas flows in the spiral pattern can become shocked and compressed, triggering star formation that lights up the arms. The feedback from these newly formed stars, radiation, winds, supernovae, then affects the gas flows, creating a coupled system that's difficult to model. Recent simulations suggest spiral arms might be more transient than once thought. Rather than permanent features, arms might form, persist for a few galactic rotations, and then dissolve, only to reform elsewhere due to new perturbations. This would explain why different galaxies show different numbers and shapes of arms. They're catching the galaxy in different phases of a quasi-periodic process. The debate reflects the difficulty of studying galactic dynamics. We can't run controlled experiments on galaxies or watch their evolution over millions of years. We observe snapshots, individual galaxies at single moments in their long histories, and try to infer processes from statistical samples and from comparing observations to simulations. Progress is being made, but slowly, as better observations and more sophisticated models gradually clarify what's happening. The persistence of this mystery is actually encouraging in a way. It reminds us that the universe still holds surprises, that not everything is understood, that there's still work for future astronomers. The Milky Way's spiral arms have been observed for centuries, studied intensively for decades, and yet they still pose questions we can't fully answer. They're beautiful, structured, mathematically elegant, and still, in important ways, mysterious. The nature of dark matter, which dominates the Milky Way's mass, remains one of physics' greatest unsolved mysteries. It could be exotic particles, modifications to gravity, or something else entirely. We grasp its effects, but not its essence. a fundamental component of the universe that refuses to reveal itself except through the gravity it exerts. The evidence for dark matter is overwhelming from multiple independent sources. Galactic rotation curves show that stars orbit too fast for the visible matter alone to hold them. Gravitational lensing reveals mass concentrations where nothing visible exists. The cosmic microwave background contains patterns that require dark matter to explain. Large-scale structure formation doesn't work without dark matter. All of these observations point to the same conclusion. There's about 5 times more dark matter than ordinary matter in the universe. But what is it? The leading hypothesis is that dark matter consists of weakly interacting massive particles, WIMPs, hypothetical particles that have mass and interact through gravity, but barely interact through any other force. These particles would have been created in the early universe and would still be around today, pervading the galaxy in a diffuse halo. Experiments have been searching for WIMPs for decades, trying to detect the rare occasions when a WIMP scatters off an ordinary atom. But so far, no convincing detection has been made. Axions are another candidate. Extremely light particles propose to solve a different problem in particle physics, but which could also serve as dark matter. Axions would behave differently from WIMPs, forming ultra-lightweight fields rather than discrete particles, but they would still contribute mass and affect the galaxy's dynamics. Experiments searching for axions use different techniques than WIMP searches, looking for their conversion into photons in strong magnetic fields. Sterile neutrinos, hypothetical particles related to the known neutrinos, but which don't interact through the weak nuclear force, are a third candidate. They would be extremely difficult to detect directly, but might leave signatures in X-ray emission from dark matter-rich regions as they slowly decay. Some physicists have proposed modifying our theory of gravity instead of invoking new particles, modified Newtonian dynamics, MAO-ND, and related theories suggest that gravity behaves differently on galactic scales than predicted by general relativity, producing effects we interpret as dark matter without actually requiring additional mass. These theories can explain rotation curves, but struggle with other observations like gravitational lensing and the cosmic microwave background. The fact that we don't know what dark matter is after decades of searching is frustrating, but also exciting. It's one of the biggest open questions in physics, a gap in our understanding of fundamental nature. When we finally identify dark matter, whether through direct detection, particle accelerators producing it, or some other means, it will be a revolutionary discovery, answering questions about the universe's composition and opening new questions about why dark matter has the properties it does. For now, we live in and move through an ocean of dark matter, utterly surrounded by it. More dark matter passing through our bodies every second than ordinary matter, and we feel nothing. It's the ultimate ghost, invisible and intangible, yet undeniably real, shaping the cosmos while remaining hidden from every sense and every detector we've yet devised. The galaxy owes its existence to dark matter. Without it, the Milky Way wouldn't hold together. Yet what dark matter actually is remains one of the universe's deepest secrets. We don't know exactly how supermassive black holes like Sagittarius A formed in the early universe. They appeared too soon after the Big Bang to grow normally, suggesting unknown processes in the universe's first billion years. This is one of the major unsolved problems in astrophysics, a puzzle that challenges our understanding of how black holes grow and evolve. The issue is one of timescales. Supermassive black holes are observed in galaxies less than 1 billion years after the Big Bang, some already containing billions of solar masses. But black holes grow by accreting matter, and there's a limit to how fast they can do this. The Eddington limit, where radiation pressure from infalling material becomes strong enough to push new material away, limiting the accretion rate. If a black hole starts with stellar mass, say 10 to 100 solar masses from a single star's collapse, and grows at the Eddington limit, it takes hundreds of millions to billions of years to reach supermassive black hole scales. But the earliest supermassive black holes existed when the universe was only 500, 800 million years old. Not enough time to grow from stellar seeds unless they were accreting much faster than the Eddington limit, or started from much larger seeds. Several scenarios have been proposed. Direct collapse black holes would form from the collapse of enormous gas clouds early in the universe's history, creating black holes of 10,000 to 1,000,000 solar masses without ever forming stars. These massive seeds could then grow to supermassive scales more quickly. But direct collapse requires specific conditions: pristine gas that hasn't been enriched with heavy elements, and ways to prevent the gas from fragmenting into stars before collapsing. Another possibility is that black holes in the early universe somehow accreted faster than the Eddington limit, perhaps through super-Eddington accretion enabled by special conditions in the early universe, or perhaps multiple stellar mass black holes merged rapidly in dense stellar clusters, building up mass through collisions rather than accretion. The discovery of intermediate mass black holes with masses between stellar and supermassive scales, would help clarify this puzzle, providing evidence for pathways between the two regimes. But intermediate mass black holes are difficult to detect, and confirmed examples are rare. Their scarcity is itself puzzling. If they're the bridge between stellar and supermassive black holes, we'd expect to find more of them. Sagittarius A itself, while supermassive, is relatively small compared to the black holes in some other galaxies. How did it grow to 4 million solar masses? Was it born large, or did it start small and accumulate mass over billions of years? Did it grow smoothly through gas accretion, or episodically through mergers with other black holes when smaller galaxies merged with the Milky Way? The answer probably involves multiple processes. Some black holes might form through direct collapse, others from stellar seeds that grow through accretion and mergers. The early universe might have had conditions that allowed faster growth than possible today. Different galaxies might have grown their central black holes through different pathways, depending on their formation history. Solving this puzzle requires observations of the very early universe, finding and characterizing the first supermassive black holes, and understanding the conditions that allowed them to form so quickly. The James Webb Space Telescope is designed to observe these early galaxies, and its findings might provide crucial clues. But for now, the existence of supermassive black holes in the early universe remains one of the great mysteries of cosmic evolution, a phenomenon we observe but don't fully understand. The Milky Way's ultimate fate depends on dark energy, which we don't fully understand. Will the universe's expansion eventually tear even our galaxy apart, or will gravity keep it together eternally? We don't yet know. The answer hinges on the nature of dark energy and how it evolves over cosmic time. Currently, the universe is expanding, and this expansion is accelerating due to dark energy, a mysterious component that makes up about 70% of the universe's energy density and exerts a kind of negative pressure that drives cosmic expansion. On small scales, within galaxies and galaxy clusters, gravity still dominates, holding structures together despite the cosmic expansion. The Milky Way isn't expanding, it's gravitationally bound, but dark energy's influence grows as the universe expands. If dark energy remains constant, cosmological constant behavior, the expansion will continue accelerating, but bound structures like the Milky Way will remain intact. The local group will stay together, eventually merging into a single galaxy, Milky. But the expansion will carry distant galaxies beyond our cosmic horizon, eventually leaving the local group isolated in an increasingly empty universe. If dark energy strengthens over time, a scenario called phantom dark energy, the expansion could accelerate to the point where it overcomes even the gravitational binding of galaxies and eventually stars and atoms. In this Big Rip scenario, the Milky Way would eventually be torn apart, then star systems, then stars themselves, then atoms, as the expansion overpowers all forces holding structures together. This would happen in the far future, tens of billions of years, but it would be inevitable if dark energy behaves this way. Alternatively, dark energy might weaken or even reverse, potentially leading to a big crunch where the universe's expansion stops and reverses, everything collapsing back toward a singularity. In this scenario, the Milky Way's ultimate fate would be to merge with everything else in the universe in a final cosmic collision. Or dark energy might decay away entirely, leaving the universe to expand forever, but at a decelerating rate. In this case, the Milky Way would persist indefinitely, slowly aging as its stars exhaust their fuel, eventually becoming a dark, quiet collection of white dwarfs, neutron stars, and black holes, cold and inactive, but still gravitationally bound. The most likely scenario based on current observations is the cosmological constant model. Dark energy remains constant. The universe expands forever, and the Milky Way, merged with Andromeda, remains intact but increasingly isolated as distant galaxies recede beyond the cosmic horizon. In this future, astronomers trillions of years hence would see only their own galaxy, the rest of the universe invisible, having been carried away by expansion beyond the distance light can travel. But uncertainty remains. We don't know what dark energy is or how it will evolve. Our observations cover a relatively short cosmic time span, and extrapolating billions or trillions of years into the future requires assumptions that might not hold. The universe has surprised us before. The discovery of cosmic acceleration was unexpected, and it might surprise us again as we learn more about dark energy's nature. For now, the Milky Way seems secure, gravitationally bound and stable against cosmic expansion. But its ultimate fate, whether it persists eternally or is eventually torn apart by accelerating expansion, depends on questions we can't yet answer about the fundamental nature of the universe and the mysterious force driving its expansion. Every atom in your body except hydrogen was forged in the Milky Way's stars over billions of years. You are not just in the galaxy, you are of the galaxy, assembled from its stellar alchemy into something that can contemplate it. This is one of the most profound connections between human existence and cosmic processes, a literal truth that we are made of stardust. Hydrogen is primordial, created in the first few minutes after the Big Bang, when the universe was a hot, dense plasma of protons, neutrons, and electrons. As the universe cooled, protons captured electrons to form hydrogen atoms. This hydrogen makes up about 10% of your body's atoms, though less by mass, since hydrogen is so light. Everything else, every carbon atom, every oxygen, every nitrogen, calcium, iron, phosphorus, was created in stars and scattered into space when those stars died. Carbon forms in the cores of stars through helium fusion. Oxygen and nitrogen form in massive stars through more advanced fusion stages. Iron forms in the final moments before a massive star explodes as a supernova. Elements heavier than iron form in the supernova explosion itself, or in neutron star mergers, created by rapid neutron capture processes that only occur in these extreme events. When these stars died, whether gently as planetary nebulae or violently as supernovae, they scattered their fusion products into the interstellar medium. This enriched gas then participated in new rounds of star formation, incorporating the heavy elements into new stellar systems. The Sun formed from such enriched gas 4.6 billion years ago, and the planets formed from the same material. The Earth contains all these elements because the solar nebula contained them. The rocky planets formed from the heavy elements, silicon, oxygen, iron, magnesium, while the gas giants incorporated more hydrogen and helium along with their cores. The Earth's composition reflects billions of years of cosmic recycling, elements created in long-dead stars now assembled into a planet. Life on Earth uses these elements. Carbon forms the backbone of organic molecules. Oxygen is essential for respiration. Nitrogen is in amino acids and DNA. Calcium builds bones. Iron carries oxygen in blood. Phosphorus is in ATP and DNA. Every element essential for life was created in stars, scattered into space, collected into the solar nebula, incorporated into Earth, and eventually organized into living things. This means your body is a collection of atoms with diverse histories. Some of the hydrogen might be truly primordial, dating back 13.8 billion years to the Big Bang. The carbon might have formed in a red giant star 8 billion years ago, ejected gently in a planetary nebula, incorporated into a molecular cloud, and eventually finding its way into the solar nebula. The iron in your blood might have formed in the final seconds before a massive star exploded 6 billion years ago, blasted into space at thousands of kilometers per second, then gradually slowing and mixing with the interstellar medium. Each atom has traveled its own path through cosmic time and space, cycling through multiple stars, perhaps, spending billions of years in the interstellar medium before ending up in you. You are an assembly of the galaxy's history, a temporary arrangement of atoms that have been through stellar cores and supernova explosions, that have drifted through space for billions of years, now organized into a pattern complex enough to think about its own origins. The galaxy didn't make you, deliberately of course. You're an accidental outcome of physical and chemical processes operating over cosmic time. But you are nonetheless a product of the galaxy, made from its material, shaped by its history, existing because billions of years of stellar evolution created and distributed the elements necessary for complexity. You are the galaxy become conscious, the cosmos observing itself through the temporary lens of human awareness, stardust contemplating stars. We may never be able to see most of the Milky Way in visible light due to intervening dust clouds. There are regions of our own galaxy forever hidden from our sight, cosmic horizons we can only infer from indirect evidence. This is a fundamental limitation imposed by our embedded position within the galactic disk, surrounded by the very material that obscures our view. The galactic center is the most dramatic example. About 26,000 light-years away, it's relatively close by galactic standards, yet it's completely invisible in optical wavelengths. Thick clouds of dust between us and the center absorb and scatter visible light so effectively that the extinction, the reduction in brightness, amounts to about 30 magnitudes. This means that for every trillion photons of visible light emitted from the galactic center, only one reaches our telescopes. The rest are absorbed by dust grains along the way. This is why early astronomers had no idea where the galactic center was. Looking in visible light, they saw dense star fields in the direction of Sagittarius, but nothing to indicate that this was the galaxy's core. Only with the advent of infrared and radio astronomy, which can penetrate dust, did the central regions become observable, revealing the dense concentration of stars and the supermassive black hole at the very center. But the galactic center isn't the only obscured region. There are molecular clouds throughout the disk, dense concentrations of gas and dust where new stars are forming, that block our view of whatever lies behind them. Some of these clouds are thousands of light-years across, creating vast shadows in our view of the galaxy. Stars on the far side of these clouds might be just a few hundred light-years away, yet they're completely invisible to optical telescopes, hidden behind curtains of cosmic dust. This means our map of the Milky Way is fundamentally incomplete in visible light. We see clearly in some directions, perpendicular to the disk, where we look through relatively little dust into intergalactic space. But other directions are heavily obscured. We're like cartographers trying to map a continent while sitting in a forest. We can see the nearby trees clearly, and we can see the sky above, but our view of distant features is blocked by the vegetation around us. Infrared and radio observations help compensate for this limitation, revealing what visible light cannot. Different wavelengths penetrate dust to different degrees, so by observing at multiple wavelengths, we can build up a more complete picture. But even with these tools, some regions remain difficult to observe, and our view of the galaxy is inherently limited by our position within it. There's a certain poetry to this, that we live inside a structure we can never fully see, that parts of our own galaxy are forever hidden from our direct observation, accessible only through indirect measurements and inferences. It's a reminder of the constraints imposed by our perspective, the limitations of being embedded observers rather than external ones who could view the whole from a distance. Future observations might improve our view, better infrared telescopes, more sophisticated radio interferometry, observations from space above Earth's atmosphere. But they won't eliminate the fundamental limitation imposed by dust. As long as we observe from within the Milky Way, parts of it will remain veiled. Cosmic mysteries, not because they're inherently unknowable, but because we're positioned where we cannot see them directly. The galaxy keeps its secrets, not through any intent, but simply through the geometry of dust and light, and our location within the structure we're trying to observe. The Milky Way is moving through space at about 1.3 million miles per hour relative to the cosmic microwave background. We're falling through space toward the Great Attractor, pulled by gravity toward a region of unknown density, billions of light years away. This motion is the result of large-scale structure in the universe, the gravitational pull of immense concentrations of mass that organize galaxies into flows and streams. The cosmic microwave background, CMB, is the closest thing we have to a universal reference frame. The afterglow of the Big Bang, radiation that fills all of space uniformly, with small fluctuations. By measuring the temperature of the CMB in different directions, we can detect our motion relative to it through the Doppler effect. In the direction we're moving, the CMB appears slightly warmer. In the opposite direction, slightly cooler. This measurement reveals that the local group, the collection of galaxies including the Milky Way and Andromeda, is moving at about 600 kilometers per second, roughly 1.3 million miles per hour, relative to the CMB. This motion isn't random. It's directed toward a region called the Great Attractor, a gravitational anomaly located about 150 million light-years away, in the direction of the constellations Hydra and Centaurus. The Great Attractor isn't a single object, but a region of enhanced mass density, possibly a supercluster of galaxies, or a particularly dense region of the cosmic web. It's difficult to observe directly because it lies behind the zone of avoidance, a region of sky obscured by the Milky Way's disk. But its gravitational influence is clear. Galaxies for hundreds of millions of light years around are flowing toward it, including our own. But the motion doesn't end there. Recent observations suggest that the Great Attractor itself is being pulled toward an even larger structure called the Shapley supercluster, a massive concentration of galaxies about 650 million light-years away. And the Shapley supercluster is part of the larger-scale flows in the Laniakea supercluster, the immense structure of which the Milky Way is a tiny part. All of this motion is the result of gravity on cosmic scales. The universe isn't uniform. Matter is distributed in filaments, sheets, and clusters, separated by vast voids. These density variations create gravitational fields that guide the motion of galaxies, creating flows and streams on the largest scales. The Milky Way is caught in these currents, falling toward regions of higher density along with thousands of other galaxies, all of us participants in a cosmic dance choreographed by gravity over billions of years. This motion has consequences. It affects how we observe distant galaxies. Their apparent velocities relative to us include both the cosmic expansion, Hubble flow, and these peculiar velocities due to large-scale structure. It shapes the local distribution of galaxies, determining which galaxies we might eventually collide with, like Andromeda, and which will be carried away by cosmic expansion. And it means we're not static. We tend to think of the Milky Way as our fixed home, a stable platform from which we observe the universe. But the galaxy itself is in motion, hurtling through space at over 1 million miles per hour, falling toward distant attractors, participating in flows that span billions of light years. Every moment we're traveling vast distances through the cosmos, carried along by momentum older than the solar system, falling through space toward regions we can barely observe, guided by gravity toward an ultimate destination we'll never reach, because cosmic expansion is carrying it away even as we fall toward it. If intelligent life exists elsewhere in the Milky Way, we haven't detected it yet, the Fermi paradox asks. With billions of potentially habitable planets, why haven't we heard from anyone? The silence itself is a profound mystery. The galaxy is vast and ancient, with billions of stars and at least as many planets. If life is common, and if a small fraction of living worlds develop intelligence, and if a fraction of those develop technology, there should be many technological civilizations in the galaxy. Where are they? Several categories of answers have been proposed, each with different implications for humanity's place in the cosmos. Rare Earth hypotheses suggest that life, especially complex life or intelligent life, is extremely rare. Perhaps the conditions needed for life are far more specific than we realize. Perhaps the Earth's history involved improbable events, the moon-forming impact, plate tectonics, the timing of mass extinctions, Jupiter's protective influence, that are necessary for complex life but rarely occur together. If so, habitable. Planets might be common, but living worlds rare, and technological civilizations vanishingly rare. We might be alone, not because the universe is hostile to life, but because the path from chemistry to consciousness is extraordinarily improbable. Great filter hypotheses suggest there's a barrier, a filter, that prevents most civilizations from reaching the stage where they're detectable across interstellar distances. This filter might be behind us, something that's difficult to pass, like the origin of life or the evolution of complex cells, which we've already overcome. Or it might be ahead of us, something that destroys civilizations before they spread beyond their home planet, like nuclear war, ecological collapse, or artificial intelligence. If the filter is ahead, then every silent star system might represent a civilization that destroyed itself. A sobering thought. Isolation hypotheses suggest that technological civilizations exist but don't or can't communicate. Perhaps interstellar travel is practically impossible, leaving every civilization isolated on their home world. Perhaps communication across light years is too difficult, too slow, or too expensive to maintain. Perhaps civilizations mature beyond the desire to communicate with strangers, pursuing their own interests in their own stellar systems, indifferent to whether others exist. We might be surrounded by civilizations, each quietly existing, none bothering to shout into the void. Zoo hypotheses suggest that advanced civilizations know about us, but deliberately avoid contact, perhaps observing us from a distance, waiting for us to reach some threshold of development before making contact. This seems anthropocentric. Why would anyone care about us? But it's a logical possibility. They're already here. Hypotheses suggest that evidence of extraterrestrial intelligence exists, but we haven't recognized it. Perhaps they operate at scales, or in ways we don't expect. Perhaps they're digital consciousnesses living in computers, or they've dispersed into cosmic structures we'd interpret as natural. Perhaps they've been here and left, or are observing quietly, waiting. Where early hypotheses suggest that technological civilizations are rare, not because they're improbable, but because the universe is still young. Star formation in the Milky Way continues, and will for billions of years. Perhaps we're among the first civilizations to arise, with most technological species yet to emerge in the galaxy's future. If so, the silence is temporary. A billion years from now, the galaxy might be crowded with civilizations, but we're living in its relative youth when intelligent life is still rare. Each explanation has different implications for our future and our significance. If we're alone, we carry a unique responsibility as perhaps the only consciousness in the galaxy. If we're early, we might be the ancestors of galactic civilization. If we're surrounded by silent neighbors, we might one day join their quiet community. If a filter lies ahead, our survival depends on navigating challenges that have destroyed countless others. The Fermi paradox remains unsolved. We continue searching. SETI programs scan the skies for artificial signals. Exoplanet studies characterize potentially habitable worlds, and astrobiologists explore what life might look like beyond Earth. But for now, the galaxy remains silent, billions of stars shining without apparent inhabitants, and we're left to wonder whether we're alone, early, isolated, or simply not looking in the right way. The question hangs over us, unanswered, one of the great mysteries of cosmic existence. The Milky Way will eventually run out of gas for new star formation, slowly fading over trillions of years. Long after humanity is gone, the last stars will be born, flicker, and die, the galaxy growing dark and cold. This is the long-term fate of all galaxies that don't merge or experience dramatic changes, a gradual exhaustion of fuel, a slow dimming into quiescence. Star formation requires cold, dense gas that can collapse under its own gravity. The Milky Way has a finite reservoir of this gas, molecular clouds in the disk, atomic hydrogen in the outer regions, gas that can cool and condense from the hot halo. Currently, the galaxy converts about 1 to 2 solar masses of gas into stars each year. At this rate, the existing gas supply will last for billions of years, but it's finite. Without new gas infall, the reservoir slowly depletes. Some gas goes into stars, where it's locked up for billions of years, for low-mass stars, or quickly recycled through supernovae, for massive stars. Some gas is heated by supernovae and stellar winds and expelled from the galaxy entirely, lost to the intergalactic medium. Some gas remains but becomes too hot or too diffuse to collapse into new stars. The merger with Andromeda will trigger a burst of star formation as gas clouds from both galaxies collide and compress, using up a significant fraction of the remaining gas. After the merger, Milky will have less gas available for star formation than either progenitor galaxy has now. Star formation will continue for a while, but at a decreasing rate. Eventually, perhaps 5 to 10 billion years from now, though timescales are uncertain, star formation will essentially cease. The last giant molecular clouds will collapse, fragmenting into a final generation of stars. These final stars will include massive blue giants that live just a few million years, and low-mass red dwarfs that will burn for trillions of years. When the last massive star dies, there will be no more supernovae to enrich the galaxy with heavy elements. When the last intermediate mass star dies, there will be no more planetary nebulae lighting up the interstellar medium. What remains will be an aging stellar population. Sun-like stars will gradually evolve into red giants and then white dwarfs. Red dwarfs will slowly brighten over trillions of years before eventually fading. White dwarfs will cool, becoming black dwarfs, cold, dark remnants no longer producing energy. Neutron stars and black holes will remain, invisible and inert. The galaxy will darken, Without new star formation, there will be no young, bright stars to illuminate the gas and dust. The integrated luminosity of the galaxy will decline as stars age and fade. Over trillions of years, the Milky Way, or Milkomeda, will transform from a blue-white spiral to a red elliptical to a dim collection of brown dwarfs, white dwarfs, neutron stars, and black holes, barely emitting any light at all. This is sometimes called the degenerate era in cosmic eschatology, the period from about 1 trillion years to a Google 100 years after the Big Bang, when the universe consists primarily of degenerate matter, white dwarfs, neutron stars, and black holes. Stars as we know them will be gone, their fuel exhausted, the universe dark and cold. Eventually, even the compact remnants decay. Protons might decay on timescales of 1035 years or longer, causing white dwarfs to slowly evaporate. Black holes evaporate through Hawking radiation, with supermassive black holes taking 1,000 years or more to disappear. In the ultimate end, if current physics is correct, the universe becomes a thin soup of radiation and elementary particles, all structure erased, all complexity gone, the cosmos approaching maximum entropy. But that's so far in the future it's almost beyond comprehension. For now and for billions of years to come, the Milky Way will continue forming stars, the galaxy still bright and active, still renewing itself with each generation of stellar birth. The end is written in thermodynamics, but it's distant enough that it feels more like cosmic philosophy than imminent fate. We're living in a special time when we can see other galaxies. In the far future, cosmic expansion will push them beyond our view, and future astronomers in a distant era will think the Milky Way is alone, unable to see the universe we can see. This sobering realization was first articulated by physicist Lawrence Krauss and astronomer Robert Caldwell, exploring the implications of accelerating cosmic expansion. Currently, we can observe galaxies billions of light years away. The light from these galaxies left long ago and has been traveling toward us ever since, gradually redshifted by cosmic expansion, but still detectable. Our observable universe contains trillions of galaxies, a vast cosmic community visible in our telescopes, but cosmic expansion is accelerating due to dark energy. Distant galaxies are receding faster than the speed of light, not moving through space that fast, but carried away by the expansion of space itself. Eventually, these galaxies will cross our cosmic horizon, the distance beyond which light can no longer reach us because space is expanding too fast for it to make progress toward us. As this happens, the number of observable galaxies gradually decreases. Galaxies on the edge of our current observable universe are already disappearing, their light stretched to wavelengths so long we can no longer detect it. In the far future, hundreds of billions of years from now, only the gravitationally bound local group will remain visible. Every other galaxy will have been carried beyond the cosmic horizon. Future astronomers in that era, observing from a planet orbiting a star in Milkomeda, the merged Milky Way and Andromeda, will see only their own galaxy. They'll observe stars, nebulae, star clusters, all within their galaxy, but when they look beyond, they'll see nothing. No other galaxies, no distant structures, no evidence that the universe contains anything beyond their own cosmic island. If these future astronomers are clever, they might deduce that the universe is expanding from observations within their own galaxy. measuring cosmic background radiation, studying the abundances of light elements, looking for other clues. But without seeing distant galaxies, they won't have the direct evidence we have for the Big Bang, for cosmic expansion, for the large-scale structure of the universe. Much of cosmology as we know it will be inaccessible to them. This has profound implications for the nature of knowledge. Some facts about the universe are only observable from certain times and places. We happen to exist during an era when distant galaxies are visible, when the evidence for the Big Bang and cosmic expansion is direct and clear. Future observers won't have this privilege. They'll live in a dark cosmos, their view limited to their own galaxy, much of cosmic history hidden from them. It also raises uncomfortable questions. What facts about the universe are hidden from us because we exist at the wrong time or wrong place? What evidence has already crossed our cosmic horizon, forever out of reach? What features of the early universe or distant regions are we unable to observe because of the timing of our existence? This is called the cosmic horizon problem in a broader sense. Not just that there are regions we can't see because light hasn't had time to reach us, but that cosmic evolution changes what's observable, creating windows of visibility that open and close over cosmic time. We're lucky to live during a window when much of the universe is visible. Our descendants, if they exist trillions of years hence, won't be so fortunate. It's a reminder to appreciate what we can see, to observe and study the universe while it's available to us, to record our findings for future generations who won't be able to replicate our observations. We're living in a cosmologically special time, witnesses to a universe still young enough to reveal its secrets. Observers in an era before dark energy erases the evidence of cosmic community from the sky. The question of how many technological civilizations currently exist in the Milky Way remains unanswered. We might be one among millions alone in our corner, or the only ones asking the question across the entire galaxy. This uncertainty is encapsulated in the Drake equation, a framework for thinking about the number of detectable civilizations, even if we can't plug in reliable numbers. The Drake equation multiplies several factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, the fraction where life emerges, the fraction where intelligence evolves, the fraction that developed technology, and the length of time civilizations remain detectable. Multiply all these together, and you get an estimate of the number of civilizations we might detect. The problem is that most of these factors are highly uncertain. We know the star formation rate and the fraction of stars with planets fairly well now, thanks to exoplanet surveys. But the probability of life emerging? Unknown. We have one example, Earth, and you can't determine a probability distribution from a single data point. Life might be nearly inevitable given the right conditions, or it might be so improbable that Earth is the only living world in the galaxy. Intelligence is similarly uncertain. Life on Earth existed for 3.5 billion years before anything resembling human intelligence emerged. Is intelligence an inevitable outcome of evolution, or is it a rare fluke? We don't know, and even if intelligence emerges, does it inevitably develop technology? Dolphins are intelligent, but have no technology. Octopuses are remarkably clever, but have short lifespans and no culture to transmit knowledge across generations. The longevity of civilizations might be the most important and uncertain factor. If most technological civilizations destroy themselves within centuries or millennia through nuclear war, climate collapse, artificial intelligence, or other catastrophes, then even if they're common, most exist for such a short time that the galaxy contains only a few at any given moment. If civilizations typically survive for millions of years, then the galaxy could contain many simultaneously. Estimates for the number of civilizations in the Milky Way range from 1 US to millions. This huge uncertainty reflects our profound ignorance about most factors in the equation. Every few orders of magnitude change in any factor shifts the estimate dramatically. Some researchers argue that the apparent absence of detectable civilizations, the Fermi paradox, suggests the number is very low, perhaps just one. If civilizations were common, they argue, at least some would have spread through the galaxy by now, and we'd see evidence of their presence. The silence suggests we're alone or nearly so. Others point out that we've barely searched. We've examined a few thousand stars for radio signals, a tiny fraction of the galaxy's hundreds of billions. We've only recently gained the technology to detect exoplanets and analyze their atmospheres for biosignatures. Perhaps civilizations are common, but we haven't looked hard enough or in the right ways. The answer matters profoundly. If we're alone, we carry unique significance as perhaps the only consciousness in the galaxy. The future of intelligence in this corner of the universe depends on us. If we're one among many, we're part of a galactic community, and our future might involve contact, communication, even cooperation with other civilizations. For now, we can't answer this question definitively. We can search, using ever more sophisticated techniques. We can explore Mars and Europa and Enceladus for signs of past or present life, testing whether life arises readily or is rare. We can study exoplanet atmospheres for biosignatures, looking for oxygen, methane, and other gases that might indicate biological activity. We can continue SETI efforts, scanning the skies for artificial signals, hoping to detect the whisper of another civilization among the cosmic noise. But until we find definitive evidence, whether a microbial fossil on Mars, an oxygen-rich exoplanet atmosphere, or a radio signal clearly artificial, the question remains open. How many civilizations exist in the Milky Way? We don't know. It might be one. It might be millions. Both possibilities are staggering, each in its own way, and we're living in the uncertainty between them. The Milky Way structure suggests galaxies are not random, but follow predictable patterns of formation and evolution. Yet each galaxy is unique, shaped by its particular history of collisions, mergers, and environmental conditions. This balance between universal laws and individual circumstances is a recurring theme in astronomy. The basic process of galaxy formation is well understood in outline. Dark matter, halos collapse from initial density fluctuations in the early universe. Gas falls into these halos, cools, and forms stars. Smaller halos merge to form larger ones, building up mass hierarchically. Feedback from stars and black holes regulates star formation, preventing gas from converting too efficiently into stars. The result is structures we recognize as galaxies. This process is universal, governed by gravity, thermodynamics, nuclear physics, and produces recognizable patterns. Spiral galaxies have flat disks and spiral arms. Elliptical galaxies are approximately spheroidal with old stellar populations. Dwarf galaxies are small and often irregular. These classifications work because galaxies really do fall into distinct categories, suggesting that similar physical processes shape them. But within these broad categories, there's enormous variety. Some spiral galaxies have prominent bars, others don't. Some have two spiral arms, some have many. Some are tightly wound, others loosely wound. Each variation reflects the galaxy's particular history, whether it experienced mergers, how much gas it retained, interactions with neighbors, even chance fluctuations amplified over billions of years. The Milky Way is recognizably a barred spiral galaxy, similar to many others we observe. But it's also unique. Its bar formed relatively recently. Its warp is caused by the specific gravitational influence of the Magellanic Clouds. Its stellar streams preserve the memory of particular dwarf galaxies it consumed. The Sun's location in the Orion Spur is an accident of where the gas cloud that formed the solar system happened to be 4.6 billion years ago. This tension between predictability and uniqueness applies throughout the universe. Stars follow predictable life cycles determined by their mass, yet each star's environment and history makes it unique. Planets form through universal processes, yet each planetary system is distinct. Even atoms of the same element are identical, but their paths through space and time differ. For the Milky Way, this means we can learn from studying other galaxies, their structures, their evolution, their properties. But we can't simply assume the Milky Way is exactly like them. It's a barred spiral galaxy, yes, but its particular configuration, history, and current state are products of its specific circumstances. Understanding it requires both general theory and detailed observation of this particular galaxy. This also means the Milky Way contains surprises. Even though we understand galaxy formation in general, the Milky Way's specific features, its ripples, its streams, its detailed merger history, continue to reveal new information as observations improve. General principles guide our expectations, but the details surprise us, reminding us that while the universe follows laws, those laws play out in infinitely varied ways. Perhaps this is part of what makes astronomy compelling. The interplay between universal patterns and particular instantiations, between law and history, between what must be and what happens to be. The Milky Way is both typical and unique, both predictable and surprising, both an example of general principles and a specific outcome of billions of years of particular events. It's one galaxy among trillions, yet it's also the only Milky Way, shaped by its own unrepeatable history into the structure we inhabit and study. Looking at distant stars in the Milky Way is a form of time travel. We see them not as they are, but as they were, with each star showing you a different moment from the past. This is an inescapable consequence of the finite speed of light. It takes time for light to travel, and during that time, the object we're observing might have changed. For nearby stars, the time delay is small. Alpha Centauri, the nearest star system, is 4.37 light-years away, so we see it as it was 437 years ago. Sirius, one of the brightest stars in the sky, is about 8.6 light-years away. We see it as it was when you were probably a child, or perhaps not yet born, depending on your age. These delays are modest, and the stars probably haven't changed noticeably in such short times. But for more distant stars, the delays become significant. A star 1,000 light-years away appears as it was when the Vikings were exploring the North Atlantic, when the Song dynasty ruled China, when Leif Erikson reached North America. A star 10,000 light years away appears as it was during the last ice age, when humans were still hunter-gatherers, before agriculture, before cities, before writing. Stars on the far side of the galaxy, 50,000 or 100,000 light years away, appear as they were before modern humans existed, when Neanderthals still lived, when the Earth was in a different climate regime. The light we see from those stars left before anatomically modern humans evolved, traveled across the galaxy for 100,000 years, and is just now arriving at our telescopes. This means the Milky Way we observe is not the Milky Way as it exists now. It's a patchwork of different times, each region showing a different moment from the galaxy's past. The nearby stars show the recent past. The more distant stars show the deeper past. The galactic center, 26,000 light years away, appears as it was when woolly mammoths roamed the Earth, when the last ice age was approaching its peak. Some of the stars we see might not even exist anymore. A massive star, 10,000 light years away, might have exploded as a supernova 5,000 years ago, but its light hasn't reached us yet. For all we know, it's been dead for millennia, but we still see it shining in the sky because we're still receiving light it emitted before it died. The news of its death travels at the speed of light and won't arrive for another 5,000 years. This temporal patchwork makes studying galactic structure complicated. We're not seeing a snapshot of the galaxy at a single moment, but rather a composite of many moments, each region of the galaxy frozen at a different time. For most purposes, this doesn't matter. Galaxies evolve slowly, and the differences over tens of thousands of years are usually negligible. But for transient phenomena, supernovae, stellar motions, variable stars, the time delays must be accounted for. The same principle applies beyond the Milky Way. When we observe Andromeda, 2.5 million light years away, we see it as it was 2.5 million years ago. Distant galaxies appear as they were billions of years ago, when the universe was younger, showing us not the current universe, but its past. The deeper we look into space, the farther back in time we see, until at the edge of the observable universe we see light from galaxies, as they were just a few 100 million years after the Big Bang. This makes astronomy uniquely historical. Unlike other sciences, where we study phenomena as they exist now, astronomers routinely observe the past. Every telescope is a time machine, every image a glimpse into history. The Milky Way is no exception. When we map its structure, we're mapping not just its spatial distribution, but its temporal structure, each measurement capturing a different moment from the galaxy's long history, all of them arriving together in the present to form our composite picture of home. The Milky Way exists at a scale that challenges human comprehension, vast enough to dwarf our solar system, yet tiny compared to the universe. We are precisely sized to find both wonder and terror in the galaxy's scale, small enough to be humbled, large enough to understand. This particular position in the hierarchy of scales shapes how we relate to the cosmos. Consider the range of scales involved. A human is about a meter tall. The Earth is about 10,000 kilometers in diameter, roughly 10 million times larger. The solar system, measuring to Neptune's orbit, is about 10 billion kilometers across, a million times larger than Earth. The distance to the nearest star is about 40 trillion kilometers, 4,000 times farther than Neptune. The Milky Way is about 1 billion kilometers across, 100,000 light years. This is about 25 million times the distance to the nearest star, or about 100 billion times the Earth's diameter. The numbers become almost meaningless. We can say them, write them, but can we comprehend them? 1 billion kilometers? What does that mean experientially? Yet the observable universe is far larger still, about 93 billion light years across, roughly 1 million times the diameter of the Milky Way. In the cosmic hierarchy, we're about halfway between atoms and galaxies on a logarithmic scale, small compared to planets and stars, enormous compared to cells and molecules. This middle position might not be accidental. We're large enough to build instruments that can detect individual atoms, and small enough that the cosmic scale is accessible to our technology. If we were much smaller, insect-sized, say, building telescopes large enough to resolve stellar features might be impractical. If we were much larger, planet-sized, we might not be able to exist as unified organisms, and our perspective might be so different that astronomy would develop along unrecognizable lines. Our size also shapes our intuitions. We evolved to navigate environments measured in meters and kilometers, to think about time scales of seconds to years. We're not naturally equipped to comprehend light years or billions of years. These scales require abstraction, mathematics, models, tools we've developed culturally to extend our understanding beyond our native scale. The galaxy's scale challenges us, but doesn't overwhelm us. It's large enough to inspire awe, but not so large that it defeats comprehension entirely. We can map it, model it, understand its structure and evolution. It sits at the edge of what our minds can grasp, vast and humbling, yet ultimately knowable. Perhaps this is the right scale for wonder. Too small, and it becomes mundane. Too large, and it becomes abstract, losing its emotional impact. The Milky Way is vast enough to remind us we're small, intimate enough that we can feel we belong to it. It's comprehensible yet mysterious, knowable yet full of surprises, familiar yet strange. And perhaps there's wisdom in sitting with this scale, in letting it humble us without crushing us, in accepting that we're small parts of something vastly larger, yet still able to understand it, map it, contemplate it. The galaxy doesn't care that we're here, doesn't notice our existence, but we can notice it, study it, find meaning in our small corner of its immense structure. That's enough. That's more than enough. Every question we answer about the Milky Way seems to reveal new mysteries waiting to be explored. Our galaxy is an inexhaustible source of wonder, each discovery a new door opening onto unknown rooms in the cosmic mansion we inhabit. This is perhaps the most important fact of all, the one that ensures astronomy will never be complete, that there will always be more to learn. When Galileo first resolved the Milky Way into individual stars, he answered an ancient question, but created new ones. What were all these stars? How far away were they? Were they suns like ours? Each answer led to more questions. When we discovered the galaxy's spiral structure, we learned what it looked like, but had to ask, why is it spiral? How do the arms form? How long do they last? When we discovered the supermassive black hole at the center, we gained understanding but faced new puzzles. How did it form? When did it form? What controls its activity? The discovery of dark matter resolved the mystery of rotation curves, but created perhaps the deepest mystery in modern physics. What is dark matter? The mapping of stellar streams explained features of the halo, but revealed a complex merger history we're still piecing together. The detection of exoplanets answered whether planets exist around other stars, but raised questions about planetary formation, migration, and the possibility of life. Each new telescope, each new wavelength, each improvement in observational capabilities reveals phenomena we didn't know existed. The Fermi bubbles weren't discovered until we had a gamma-ray telescope sensitive enough to detect them. The galaxy's ripples weren't seen until Gaia provided precise enough measurements. The Rosetta bubbles required X-ray sensitivity we only recently achieved. This pattern suggests that our current understanding, as sophisticated as it seems, is probably incomplete in ways we can't yet imagine. There are almost certainly large-scale structures or phenomena in the Milky Way we haven't detected because we haven't built the right instruments or looked in the right ways. There are probably entire classes of objects or processes we haven't discovered yet. And beyond what we can observe, there are deeper questions. Why does the universe have the laws it does? Why do these particular physical constants lead to galaxies and stars and planets, and apparently life? Is the Milky Way typical or unusual in ways we don't recognize? What is the nature of time, space, consciousness, existence itself? These questions might never be fully answered. Each answer seems to reveal new layers of mystery, new depths to explore. This isn't frustrating, it's liberating. It means there will always be work for curious minds, always new phenomena to discover, always deeper understanding to seek. The Milky Way, which seemed like a simple band of light to ancient observers, has revealed itself to be extraordinarily complex. A barred spiral galaxy with hundreds of billions of stars, pervaded by dark matter, shaped by mergers, wrapped in stellar streams, breathing gas through a galactic fountain, occasionally erupting from its center, warped by satellite galaxies, host to planets beyond counting, possibly even host to other life, other minds, other observers looking up at their own night sky and wondering. And we've only just begun to understand it. Future observations will add detail, correct errors, reveal surprises. Future theories will provide better frameworks for understanding what we see. Future generations will look back at our current knowledge, the way we look back at Galileo's first telescope observations. A crucial step, an important beginning, but only a beginning. So perhaps this is where we can rest, at least for now. The Milky Way is home, a vast structure of stars and gas and dark matter, shaped by gravity and time, ancient and evolving, comprehensible yet mysterious. We're inside it, made from it, trying to understand it, finding that each answer leads to new questions, that the more we learn, the more we realize how much remains unknown. And that's perfect. That's how it should be. The universe doesn't owe us easy answers or complete understanding. It simply exists, vast and complex and beautiful, waiting for curious minds to explore it, to ask questions, to seek understanding, to marvel at what they find. The Milky Way is home. It's where we are. It's where we've always been. And there's so much more to discover. And that brings us to the end of tonight's journey through the Milky Way. 100 facts, 100 glimpses into our galactic home, from its ancient origins to its far future, from the supermassive black hole at its heart to the dark matter halo that holds it together. We've traveled through time and space tonight, back to the galaxy's formation 13.6 billion years ago, forward to its eventual merger with Andromeda, outward to its warped edges, inward to the nuclear star cluster surrounding Sagittarius A. We've contemplated dark matter and stellar streams, exoplanets and hypervelocity stars, cosmic rays and gravitational waves, all of it part of the vast structure we call home. The Milky Way is many things. It's a barred spiral galaxy, one among trillions. It's a collection of hundreds of billions of stars, most of which we'll never see. It's the context for everything we are. Every human who has ever lived has lived here, orbiting this star in this galaxy, looking up at the same river of light that ancient peoples named for spilled milk. It's humbling to realize how small we are against this cosmic backdrop. The solar system is a tiny speck in the galactic disk. The Earth is a microscopic fragment of that speck. You, lying there listening to this, are a temporary arrangement of atoms that will someday return to the cosmic recycling stream, scattered back into the interstellar medium to perhaps become part of future stars, future worlds, future minds wondering about their place in the cosmos. But it's also empowering. Despite our smallness, we can understand the Milky Way. We can map its structure, trace its history, predict its future. We're made of stardust and supernova ash, assembled by billions of years of cosmic evolution into patterns complex enough to think about where we came from and where we're going. We're the galaxy contemplating itself, temporary but conscious, brief but aware. Perhaps that's enough. Perhaps being small parts of something vast, participants in a cosmic story billions of years long, witnesses to a universe that doesn't require our presence but allows it anyway. Perhaps that's all the meaning we need. The Milky Way will continue long after we're gone. The stars will keep burning, new ones being born as old ones die. The galaxy will keep rotating, slowly spiraling its way through the cosmos. In 4 billion years, it will collide with Andromeda, creating something new. In trillions of years, it will fade as its fuel exhausts and star formation ceases. But for now, in this moment, it's bright and active and beautiful, and we're here to see it. So rest easy. You're home. You're inside a galaxy 100,000 light-years across, orbiting a supermassive black hole at 514,000 miles per hour, made of atoms forged in long-dead stars, temporary but real, small but conscious, part of something so vast it challenges comprehension, yet intimate enough to feel like home. Sleep well. The galaxy will still be here tomorrow, spinning through space, ancient and patient, full of mysteries and wonders, waiting for us to explore it. Good night.